Welcome to week 11, Recurrent Neural Networks, RNNs, and Sequence Modeling. This week, first, we will look at Introduction to Sequence Modeling and RNNs. Day 2 will show us understanding RNN architecture and backpropagation through time, which is BPTT. Day 3 will be covering long short-term memory or LSTM networks. Day 4 will look at gated recurrent units, which are GRUs. Day 5 we will be looking at text preprocessing and word embeddings for RNNs. Day 6 will do sequence to sequence models and applications. And finally, for day 7, our RNN project will be on sentiment analysis. So let's get started with week 11. Welcome back to week 11. This week we will start our day 1 with the introduction to sequence modeling and RNNs. Now let's go over the overview of sequence modeling. What is sequence modeling? Sequence modeling involves predicting or generating outputs based on sequential data. Unlike standard models, which assume independence between inputs, sequence models capture temporal or contextual dependencies. Why is sequence modeling important? First, NLP, natural language processing. Tasks like language modeling, machine translation, and sentiment analysis depend on understanding sequential relationships in the text. Time series analysis. Sequence models are essential for tasks like stock price prediction, weather forecasting, and sensor data analysis. Next, let's go over the introduction to recurrent neural networks or RNNs. What are RNNs? RNNs are specialized neural networks for sequence modeling. They include recurrent connections that allow them to maintain a memory of previous inputs. The structure of RNN has input layer, which processes sequential data one step at a time. Then it has a hidden state, which maintains information about past inputs. And it has recurrent connections, where we pass hidden states from one time step to the next. Let's look at the key concepts in RNNs. First, we have hidden states. These represent memory at each time step. Recurrent connections enable information sharing across time steps. Vanishing gradient problem. Challenges in training long sequences due to diminishing gradients. Let's look at some of the key applications of RNNs in machine learning. We have text generation, which generates new text based on learned patterns. We have language translation, which converts text from one language to another. Stock price prediction, which predicts future stock prices using historic data. Another application is speech recognition, which understands spoken words and phrases. We have video frame prediction, which anticipates future frames in video sequences. With all this in mind, let's jump into hands-on exercise, where our objective today is to pre-process a text dataset for use in RNNs and set up an environment in TensorFlow and PyTorch for building RNNs. I know I mentioned or here, TensorFlow or PyTorch, but we're going to look at both the options today. So let's jump in. First, I'm going to go over TensorFlow. So I'm going to start a new file, Python, save it as day1 underscore, I'll call it TensorFlow. Let's start with some of the libraries that we need. So I'm going to go ahead and say from TensorFlow, TensorFlow dot keras dot datasets import IMDb. Since this is the first day of the week, I'm going to go ahead and explain each line. You can just forward this if you don't like it, but I'll probably go over each and every line. So this line imports the IMDb dataset, a standard dataset for sentiment analysis, where each review is represented as a sequence of integers, and that's our data set that we're going to use. Next, from TensorFlow dot keras dot preprocessing, I am dot sequence, I am going to import pad underscore sequences. Now this imports the pad sequences function used to ensure all sequences which are reviews are of the same length by padding or truncating them. Okay, so that takes care of it. Just make sure that there's no typos, because that comes back and bites us later on. Next, I'm going to go import TensorFlow as TF. This will import the TensorFlow for deep learning operations. Now next, I'm going to say from TensorFlow dot keras dot models, I am going to import sequential. Now we have used this before. This imports the sequential class used for building a sequential, which is layer by layer model. Next, I'm going to say from TensorFlow dot keras dot layers, I am going to import embedding, and I'm going to import another one, simple RNN, and I'm going to import dense. So these import specific layers. Embedding converts word indices to dense vectors. Simple RNN implements a basic RNN layer, and dense is fully connected layer for output. So let's go ahead, and now next I'm going to set up some hyperparameters. Let's say vocab size equal to 10,000. This is the vocabulary size that I want. The top 10,000 most frequent words will be used here. Next, I have max underscore length equal to 200. This is the maximum sequence length. Reviews will be truncated or padded to 200 words. So every review is 200 words. Next, I'm going to go ahead and load the data using the imdb dot load underscore data function, and I'll say number of words that I want here will be equal to vocab underscore size. I don't want the entire thing, but just 10,000 words, which I'm defined in line number 7. Now this will give us x underscore train, y underscore train, comma, x underscore test, comma, y underscore test. So this will give us the training and testing data for us. Next, so again, just loads the IMDb data set. Number of words, as I mentioned, restricts the data set to the top 10,000 words, most common words, and then x train, y train, x test, y test, these lists of integers representing word indices, and binary label 0 for negative and 1 for positive for the y items. So next, let's go ahead and pre-process the data. So I am going to say x train equal to pad underscore sequences, as I mentioned earlier. I'm going to use that function for, anyway, first I'm going to type this max length equal to max underscore length, and padding equal to, I'll set it as post. Here what I'm doing is I'm ensuring that all the reviews have the same length, which is max length of 200, and then the pad sequences with zeros at the end, which that's why I mentioned post. So padding happens at the end, and truncates reviews longer than 200 words if it's more than 200 words. So that's what this does. Now I'm going to do the same thing for our test data set. So here, test max length, perfect. So this is good. Now next thing I'm going to do is print the data set just to check it out. So I'm going to say print f of training data shape, and for that I'll specify x underscore train dot shape, and then for my test data shape, keep a space here, x underscore test dot shape. Perfect. So I have that. I'm going to move all the way to the top. So this kind of prints the shape of the padded data set for confirmation. So you can run this application. I can go here and say Python day 1 TensorFlow, or dat1 underscore TensorFlow. This will get the data and show me my 25,000 by 200, 25,000 by 200. So that's what I have. So perfect. So I have my training and test data set available. Now next, I am going to build the model. Now to build the model, I'm going to say model equal to sequential, and here I will pass embedding, which is with input dimension of equal to vocab underscore size and output underscore dim equal to 128. Here what I'm doing is first I'm using sequential, which is a model built for stacking layers sequentially, and in with embedding I'm setting input dim equal to vocab size, where input vocabulary size is 10,000 words, and output dim equal to 128, where each word index is mapped to a 128 dimensional vector. Next, I'm going to use simple RNN, and to this I'm going to pass 128 comma activation equal to, I'll use tan h this time, and I will say return underscore sequence equal to false. So what I'm doing here is I am creating a initializing simple RNN, where I'm giving the number of RNN units to be used is 128. I'm saying activation function for the RNN is tan h, and I am saying that this outputs only the last time steps results. That's why I say return sequence equal to false. Next, I'm going to create a dense layer, where I'm going to say 1 comma activation equal to sigmoid. And then finally, I'm creating a fully connected output layer using dense. The one is the outputs a single value for binary classification, and then finally we have the activation equal to sigmoid, which ensures the output is between 0 and 1 probability. So perfect. So that kind of created my model. Now next, let's go ahead and compile this model. So to compile it, I'm going to call the compile function model.compile, and I'm going to pass the optimizer equal to, use same what we used before, Adam. I'm going to say loss equal to binary underscore cross entropy, since we are looking at binary data, and metrics that I'm interested is, as usual, accuracy. So here we are compiling with optimizer Adam, which is optimizer for training. Loss binary cross entropy is loss function for binary classification, and metrics accuracy evaluates the model's accuracy during the training process. So now once I'm done with this, I can just say model dot summary. This displays a summary of the model architecture, including layers, parameters, and output shapes. So now let's go ahead and train this model. To train this model, I'm going to create a history variable, and I'll say model dot fit and pass it x underscore train. I'll pass y underscore train. Number of epochs that I want to run it for is 5. I'm going to keep it small so it doesn't take much time. Batch size equal to 32, and I'm going to say validation split equal to, so this is how much validation split I want to give. I want to give a 0.2, so 20-80% split. So again, x train, y train is the training data and labels. Then we gave trains for 5 iterations over data set. That's why epochs is 5. Batch size 32 processes 32 samples at a time, and validation split is 0.2, uses 20% of the training data for validation. So next, let's go ahead and evaluate the model. So I'm going to say loss comma accuracy equal to model dot evaluate evaluate, and to that I'll pass x underscore test and y underscore test, which I've done before. This tests the model on the unseen test data set. Outputs for this will be loss, which is the final loss on the test set, and accuracy will be accuracy on the test set. Now finally, let's go ahead and print this off, these things. So f test loss is loss colon 0.4 f, and next I'll also display test accuracy, which is accuracy 0.4f. Perfect. So I'm gonna go ahead and run this. I'll clear this out and run this again. Okay, there's probably some typo or something that I missed, so I'm gonna go ahead and check here. Looks like it's on return sequence false, where I have mentioned instead of return sequences, return sequence, and that's why it's giving me an error saying unrecognized keyword. So I'm going to save that, clear it out, run again. And now it's going to give me the model summary and it's going to run for 5 epochs. So while it is running, let's go ahead and start our process to code in the similar thing in PyTorch. So I'm going to go ahead, create another file, save it as day1 underscore pytorch.py. For this, first I'll import torch, import torch nn dot nn as nn. Next I need to import torch dot optim as optim. Next I want to from torch dot utils dot data I will import data loader and tensor dataset. So what I'm doing here is first the core PyTorch library for tensor operations, which is torch. I'm importing that. Torch.nn, that is the module for building neural networks. We have torch.optim, which is optimizers for training neural networks. And finally, torch.utils.data. These are utilities for working with dataset, which includes data loader for batching and tensor dataset for packaging data. So once I have that, next things that I need is from TensorFlow dot keras dot datasets. I am going to import IMDb. That's the dataset. That's why I'm using TensorFlow right now. TensorFlow dot keras dot pre-processing dot sequence import pad underscore sequences. So these we have just used, which impose the IMDb dataset and the pad sequences function from TensorFlow for pre-processing. Next, let's go ahead and build some hyperparameters, same as last time. I'm going to say vocab size equal to 10,000. And then I'll say max underscore length equal to 200. So this is again same as vocabulary size is 10,000 and maximum sequence length is 200. The vocab size, what I'm trying to do is I'm trying to get only the top 10,000 most frequent words are used, and max length is each review is padded or truncated to 200 words. Next, I am going to go ahead and load and pre-process the data. I'm going to use same thing that we did before, xtrain, comma y train, and then x test and y test. I am going to say IMDb dot load underscore data, load data, number of words equal to vocab underscore size. So this again loads the IMDb dataset, and each review is a sequence of integers representing word indices, and ytrain and ytest contains the binary sentiment labels of 0 and 1. Next, pad the sequences. So that is x underscore train equal to pad underscore sequences, and I'll give x train comma max length equal to max length, and padding, I want to pad at the end of the, if it's not enough, I'm going to say not enough data in there, I'm going to add padding of zeros at the end. Same thing I'll do for x underscore test. Do the same thing here. Perfect. So that takes care of that. So that's again pads or truncates reviews to have a fixed length of 200 using the pad sequences. Now let's go ahead and prepare the data for PyTorch. So till now whatever we did was same as earlier code, but now I'm going to say train data set equal to tensor dataset torch dot tensor x underscore train torch dot tensor y underscore train. So this line converts NumPy arrays into PyTorch tensors and creates a data set of paired inputs and labels. Same thing for train, or not same thing, train loader equal to data loader. To this I'll pass the train data set, and I'll say batch size equal to 32 and shuffle equal to true. So what this does right now here is it batches the data set into groups of 32 and shuffles the data for training, which means our next step is to define the RNN model. So I'm going to say class RNN model, use the nn.module as input. Now first is our initializer method, so I'm going to say init underscore, pass it self, comma, vocab size that I want to use. Next I'm going to say embedding underscore dim. I want to use hidden underscore dim. I will use output underscore dim here. Then call the super method RNN model, pass RNN model and self to it, and call the initializer function. Perfect. Next, self dot embedding equal to nn dot embedding, and then pass the vocab size to it and embedding dim to it. Next, for self dot rnn, I will pass nn dot call rnn and pass it embedding dim, hidden dim. It needs whatever I mentioned during the slides, it needs hidden dim, and batch first equal to true. And then finally I'll say self dot fc equal to nn dot linear hidden dim and output dim. So here what this init function does is it defines the model architecture. nn.embedding embeds the input word indices into dense vectors. Then nn.rn is a simple recurrent neural network layer, and nn.linear is a fully connected layer mapping the RNN outputs to the final binary sentiment prediction. Next, let's create the forward function. def forward self and x. Now in here I am going to say embedded equal to self dot embedding of x. Next, for output and hidden, I will use self dot rnn and pass it embedded, and then I'll return torch dot sigmoid self dot fc of hidden dot squeeze of 0. So here what I'm doing in the forward function is I embed the input sequences, passes the embedded sequences through the RNN, hidden contains the RNN's last hidden state, and finally applies the fully connected layer to the hidden state and uses the sigmoid activation to output the probabilities. So that's what we're doing here. Now once I'm done with this, I'm going to go ahead and initialize the model by calling that class that I've created, RNN model, and pass it. We'll have to pass the vocab size, which we already have set to 10,000, but I'm going to specify here. I'm going to say embedding dim equal to 128. I'm going to say next one is hidden dim equal to 128. Next, I have the output dim to provide, and I'll say output dim that I'm expecting is of 1. So here what I'm saying is I'm initializing the RNN model with the specified parameters, with vocabulary size is 10,000, embedding dimension is 128, hidden dimension is 128, and output dimension finally is 1 for binary classification. So it will be 0 or 1. Now let's go ahead. Our next step here is to define the loss and optimizers. For that, I'm going to use criterion variable equal to nn dot bce loss is what I'm going to call. This is the binary cross entropy loss function. Next, I'm going to call optimizer equal to optim dot, I'll use Adam as usual, and I'll say model dot parameters is the first parameter that it needs. Next, I'll say learning rate equal to 0.001. So again, what I'm doing here is criterion is what computes the binary cross entropy loss for the predictions, and optimizer optimizes the model using Adam with a learning rate of 0.001. Next step here is to train the model. So I'm going to create a function called as train RNN, and this will take inputs as model train underscore loader. I think I've created that, but I don't see it. Train underscore loader. Next, I'll use criterion. Next, I'll use optimizer. And finally, I'll say epochs equal to 5 by default. So if you're not specified, and I want to keep it minimum, just like a TensorFlow. Talking of TensorFlow, let's look at the results over there. So it went through the 5 epochs. It gave me the test accuracy, test loss here. 85% is the test loss. Accuracy is 53%. So there you go. That's how it shows. Now let's compare this with PyTorch that we have. Should be almost same. First, I'll start the training process by calling model.train. And now for each epoch in range of epochs, depending on how many epochs we pass, if not, it's 5. Epoch loss, I'll create a variable where I'll set it to 0 initially. And then I'm going to go from batch by batch, take X batch and Y batch in train underscore loader. And then for each of them, first I'll use the optimizer dot 0 underscore grad, so 0 out the gradients for the optimizer. Then I'm going to say predictions that I am looking for equal to model of x underscore batch dot squeeze, so it can properly fit in to 1 of loss equal to criterion, and then to this I'll pass the predictions, and y underscore batch dot float if it's not in float value, loss dot backward, so that's first, and then I'll have to optimizer dot step it up, and I'll now do epoch underscore loss plus equal to loss dot item, as we have done before. So this model dot train sets the model to the training mode here, and then for each epoch we initialize the cumulative loss initially to 0. For each batch in the train loader, I am saying optimizer 0 grad, which clears the previous gradients that has been calculated. Then we get predictions, which makes the predictions here. Then loss equal to criterion, it calculates the loss. I am computing the gradients here, and then this one optimizer.step updates the model weights, and I am adding the add batch loss to epoch loss here and keep on incrementing. And finally, let's go ahead and print for each epoch. I'll say epoch plus 1 comma loss is epoch underscore loss slash divide by length of train loader and 0.4 f. So that will display, print me the epoch loss. I'm going to save this. Next thing is I'm going to call the training function. I'm going to go outside and say train underscore RNN, and I'll pass it the model. I have the model. I have the train loader. I'll pass the train loader. Next, I can pass the criterion. I have that. And next, it needs optimizer. Now, if you want to pass epoch, you can pass epochs, but I'll leave it because I'll use 5. So this will train the RNN for 5 epochs using the training data. Finally, once it's trained, let's go and create the evaluation loop. Evaluate underscore RNN. To this I'll pass model x underscore test and y underscore test. Inside this I'll say model dot eval. So this will set the model to evaluation mode. Now next, with torch dot no underscore grad. So this disables gradient computation for efficiency, and I am going to say predictions equal to model and pass it torch dot tensor x underscore test dot squeeze of 1. So this will give us predictions. Now for loss, I will say criterion, and to that I'll pass the predictions, and it needs the torch converted into tensor of y underscore test dot float. Perfect. So that will give me my loss. And now finally for accuracy, I will say predictions, if predictions is greater than 0.5 is equal to torch dot tensor at the particular location y underscore test dot float cos dot float. Then so this will give me the float value. Then I can just go ahead and get the mean of this particular item, mean item. So this will give me the accuracy for that. Now finally, let's go ahead and print our f test loss is, what is our test loss? Loss dot item, and I'll say 0.4 f. Now for test accuracy, I will say accuracy 0.4 f. So this will give me the loss and accuracy printed out. So that kind of finishes our entire loop. Now the only thing left is to call evaluate RNN and pass the model, pass x underscore test, our data set xy underscore test. So I pass that. This will finally evaluate the model on the test data set and print the loss and accuracy for us. So this is saying something is wrong. Maybe I did not predications. Okay, whatever it is, just make sure that you follow along. I hope there's no other typos. These are the TensorFlow warnings, so that's fine. They're already there. I'm gonna go ahead, clear, or no, not clear it out, but I'm gonna say, actually, let me clear it out. I'm gonna say Python day1 underscore pytorch.py. Let's hope there is no errors. There is pad sequences. Where is that? So in my pad sequences of x train, max length of max length, and my max length is here. Max length looks like the parameter is not max underscore length but max length. Again, you can check here, max length equal to max length. Yeah, perfect. I used underscore. That's not right, so I fixed that, clear it and run it again. And it, as you can see, it's running for epoch 1, so it's going to take some time. So we'll come back to it once it gets over. So as you can see, it ran through the 5 epochs and then gave me the epochs and loss. I think I pressed something here, that's why it gave me this thing here. But it went through 5 of the epochs and gave me the loss. And you can see the test loss is 0.67 and this test accuracy is 0.56. So this is how you can pre-process a text data set using for use in RNNs and set up an environment in both, as we saw, TensorFlow and then PyTorch for building RNNs. I hope you were able to follow along. And just to summarize, we understood the importance of sequence modeling in NLP and time series analysis. We learned the structure and functioning of recurrent neural networks. We gained hands-on experience setting up environments and preparing datasets for RNNs. And we finally built a foundational knowledge for advanced sequence modeling tasks. If you had any issues while implementing this, saw some errors, or have any questions, do let me know in my messages and I'll get back to you. Day 2. Understanding the RNN architecture and backpropagation through time, which is BPTT. So first, we're going to look at detailed architecture of RNN. The different components of RNN include first the input layer, which takes sequential data, example words, characters, or time series values as input at each time step. Hidden layer, which maintains a memory of the past inputs through recurrent connections. The hidden state at time t of ht is calculated as h of t equal to f of wh times h of t minus 1 plus wx times xt plus bh, where wh is the weight matrix for recurrent connections, your wx, which is the weight matrix for input connections, bh is the bias term, and f is the non-linear activation function. X can be a tan h or ReLU. For the output layer, it produces output yt based on the hidden state of ht, which is yt equal to g of wy times ht plus by, where g is the activation function, can be softmax for classification. Now next, let's talk about backpropagation through time, which is BPTT. Now what is BPTT? BPTT is an extension of standard backpropagation to handle sequential data in RNNs. It calculates gradients for each time step and propagates them backward through the sequence. Steps for BPTT include unroll the RNN across the sequence for a fixed number of time steps, then compute the loss for each time step, then backpropagate the errors across all time steps to update the weights. Challenges in BPTT include first is vanishing gradient problem. Gradients diminish exponentially as they are propagated back through time. This leads to difficulty in learning long-term dependencies. Then we have exploding gradient problem, where gradients grow exponentially, causing numerical instability during the training process. What are the solutions? First, use gradient clipping to handle the exploding gradients problem. Then, use architecture like long short-term memory LSTM or gated recurrent units GRU to mitigate the vanishing gradient problems. And we'll look at both of these solutions later in this week. Next, let's talk about limitations of the vanilla RNNs. First is the short-term memory, struggle to learn dependencies in long sequences due to the vanishing gradients. Second is the sequential computation. It cannot parallelize training across time steps, making them computationally expensive. And third is the sensitive initialization. The performance depends heavily on proper weight initialization and learning rates. With all this in mind, let's look at our today's hands-on exercise, which is much similar to yesterday's, where we will be building a simple RNN model for text classification using TensorFlow and or PyTorch. We're going to use both, and then train the RNN and observe how it captures sequence patterns. We'll be using our dataset as IMDb movie reviews dataset for sentiment analysis. That's what we did in the yesterday's video too. I'm not going to go into complete details of each and every line, but I'm going to go just roughly over what I'm doing. You can follow along and code with me for this particular exercise. So again, I'm going to start with a new file, Python file, save it as day2 underscore. First, I'm going to implement TensorFlow, so I'm going to call it TensorFlow. In here, first, I'm going to import the necessary libraries. So I'm going to say from TensorFlow dot keras dot datasets, I will import IMDb. Next, from TensorFlow dot keras dot pre-processing dot sequence, I will import pad underscore sequences. Next, I will import TensorFlow as TF. Next, I will import from TensorFlow dot keras dot models. I will import sequential. Next, from TensorFlow dot keras dot layers, I will import my layering tools, which is embedding, simple RNN, and dense. Perfect. So I have all my imports in place. Next step that we did was loading the data set. So I will say first vocab size equal to 10,000. This is the vocabulary size that I want. And then I want the max length equal to 200. Next, I'm gonna get the data set into x underscore train, comma, y underscore train, x underscore test, comma, y underscore test equal to imdb dot load underscore data, and I am going to specify number of words that I want to load from here equal to vocab underscore size. So this will pick the top 10,000 words from there. Next, I will pad the sequences to ensure uniform length. For that, I'll say xtrain equal to pad sequences, pass it our xtrain, and max len equal to max underscore length, padding equal to post padding. So I'm going to make sure that everything, if it's not 200, it will pad at the end. X underscore test pad sequences to x test, where I'll say max length equal to max underscore length, and again padding equal to post padding. Next, I have to print these shapes of training and test data set. So I'm going to say print of f training data shape is x underscore train dot shape, not function. Next, I will say the testing or test data shape equal to x underscore test dot shape. Next, I will go ahead and build and train the RNN model. Now first I'll define the RNN model. So I'm going to say model equal to sequential, and inside sequential I'll pass first embedding, and this needs input dimensions equal to vocab size. Next, I'm going to say output dimension, output dim equal to 128. Next, I will create a layer with simple RNN where the input will be 128 in this case. Activation equal to ReLU. Oh, sorry, I want to use tan-h. And then I'll say return underscore sequences. Last time I did this error, but this time, nope, false. And then finally the output layer, dense 1 activation equal to sigmoid for our binary classification. So perfect. So now next I'll compile the model. I'll say model dot compile. To this I'll pass the optimizer as Adam, loss equal to binary underscore cross entropy, and metrics equal to accuracy. So we have our compiled model here. So let's go ahead and print how it looks like. At this point I'll say model dot summary, so we'll see the model, and once we have that I can go ahead and train the model. I'll create a parameter where a variable history and say model dot fit, and inside this pass the x train, we need y train, we need epochs equal to 5. I need the batch size of how much to take once, and I'll be using 32. And then I'll say validation split equal to 0.2. So 20% of the data is for validation. Next, I am going to get I'm going to create this loss and accuracy. That will come from model dot evaluate method, and I'll pass x underscore test and y underscore test to it. to get the accuracy. So now to print the accuracy, I can say printf test loss is loss 0.4f and test accuracy equal to accuracy, and this is again 0.4f. So this will display my loss and accuracy. Now that I have this, let's go ahead and say, let's say I'm in the right place. Okay, python day 2 underscore py TensorFlow. I'll run it, and while it's running, I can also run create the PyTorch example. So it's running through our epochs. So I'll go ahead, create a new file, save it as day 2 underscore PyTorch. Okay, I'll have to rename this. So now that I've renamed it as .py, I'm going to go ahead and first say import torch. So these are my necessary libraries. Let's go through one of them, each one of them. Import torch nn.nn as nn. Next, I need import torch.optimizer optim as optim. Next, I need from torch.utils.data. I need to import our data loader, and I need the tensor data set. Perfect. Now I have that. I'll go ahead from TensorFlow dot keras dot datasets. I need to import the IMDb database. Once I have that, next is again from TensorFlow dot keras dot preprocessing dot sequence. I will import our pad sequences. Okay, so once that is done, I can first load the data. I can use the same code that I used here. Go here, vocab 10,000, max length 200, xtrain, xtest, ytest, IMDb load, and pass the vocab size here. Next, I want to do the pad sequences, which is same as this. And do this pad sequences. Once that is done, next I need to prepare the data loader. Now is actual for PyTorch, where I can say train dataset equal to tensor dataset. This will convert from TensorFlow to PyTorch. I'm going to say tensor x underscore train. So that's done for x train. Next, I'll need torch dot tensor for y underscore train. So that looks good. Next thing that I want to do is get the train loader, or training loader, which is coming from data loader, and to this I'll give the train data set. I'll set what batch size I want of 32, and I'll say shuffle equal to true. I want the data to be shuffled. So I have that thing ready. Now next we'll have to go ahead and define the RNN model. So I'm going to say class RNN model nn.module. I pass that as the parameter. I'll create my initializer function, pass itself. It needs vocab size. I need embedding. Did I spell it wrong? Embedding. Okay, there you go. Dim. Next, I need the hidden dimension. Next, I need output underscore dimensions, and I think that's all that's all my initializer needs. So now first step is to call the super with RNN model and self and initialize it. Perfect. So once that is initialized, I can now use the embedding equal to nn.embedding, pass it the vocab size, and it needs the embedding dimensions. So I have that. I'll pass the embedding dim. Okay, self, not slef. Next, we need self.rnn equal to nn.rnn, capital RNN. In this case, I need the RNN needs first embedding dimension, then it needs the hidden dimension, and then it needs the batch first equal to true parameter. Next, I'm going to say self.fc. For this, I need nn.linear, and linear will have hidden dimensions and it needs output dimensions. That's about it. So that's my initializer function. Next, we write the forward function, which needs myself and x. And for first, I'm going to say embedded equal to self dot embedding with the value of x. Perfect. Next, for output and hidden, I will say self dot rnn and pass it the embedded. And finally, we return torch dot sigmoid and pass it self dot fc of hidden layer, and then we'll squeeze it, squeeze with 0 as a parameter. Perfect. So that's forward is done. Now that is done, let's go ahead and initialize the model. To do that, I'm going to say model equal to RNN model, and to this we'll pass first is vocab size of 10,000. Next we have the embedding dim, which is 128. We'll say hidden dim equal to 128, and then we give the output dim of 1. So these parameters is what we pass to create our model. Now let's go and define the loss and the optimizers. For that, say criterion equal to nn dot, and we have used nn dot bce loss, which is the binary cross entropy. Next, I'm going to set the optimizer equal to optim dot adam and pass it the parameters of the model. So parameters. Next, I'll say the learning rate equal to 0.001. Perfect. So that takes care of our loss and optimizer. Now let's go ahead and write the function to train the model. So to that, train RNN, it needs model, it needs train loader, it needs criterion, optimizer, and our final epochs equal to 5. Let's set the default to 5. Now that is done, let's put the model in training mode by calling the train function, and then write our for loop to go through each and every epoch in the range of epochs. And for each of them, let's go ahead and first initialize our epoch loss equal to 0. And then let's go over each and every for x underscore batch, comma, y underscore batch. These are my batches of images and labels. So I'm going to say train loader. I will say initially optimizer dot, zero out the gradient from the previous ones for every single optimizer. Next, I'm going to say predictions equal to model with x underscore batch and squeeze with 1. Next, I will calculate the loss equal to criterion and then pass it predictions, comma, y of batch dot float value. Convert that into float. Next, I will have loss dot backward. Next, I'll do optimizer dot step 1. Okay, so that's steps. Next, finally, I'll say epoch loss. Let's increment that based on the current values item. So that will increment that. So that kind of takes care of everything. And I'm going to say print which epoch is it. Epoch plus 1 because it starts from 0. Loss and epoch loss divide by length of I think it's train loader. There you go. So divide by that, and that's my 0.4f data to display. So that will display my loss at the end of every single epoch. Next I want to do is let's go ahead and call the training function. So to do that, I'm going to just say train RNN, pass it our model. We have our train loader available. We have the criterion available. We have our optimizer available. The only thing we don't have is epochs, which will use the default 5. Now that is done, let's go ahead and evaluate, right? The evaluate loop. I'm going to say evaluate RNN. It needs 3 items: model, X test, and Y test. And in here, first we'll put the model in evaluation mode. Next, open the torch dot no grad. So make sure there is no gradients, and then let's start with predictions equal to model and pass it torch dot tensor, convert the X test into tensor, to torch, so it can understand, and then squeeze it with a parameter of 1. Perfect. I think I closed it at the wrong place. Okay, that's good. Next, let's calculate the loss equal to criterion and pass it predictions and torch dot tensor, so tensor that we have in y underscore test format dot so convert into float to float. Perfect. So that's that. Now we need to calculate the accuracy. For accuracy, I will say predictions. If predictions is greater than 0, then let's make sure using the same parameter greater than 0, then torch dot tensor of y underscore test dot float and of the entire float, and then I will have to get a mean of that for the end item of that mean. Perfect. So I have my accuracy. Once I have accuracy, let's go ahead and print this out. F of test loss is loss dot item and display it in 0.4f. Next, I want to get the test accuracy, which is accuracy in 0.4f. Perfect. So I've displayed both loss and accuracy. Now the only thing that is left is evaluate RNN, pass the model, pass the X underscore test, and pass Y underscore test, and it'll do the rest for you. So perfect. So while this is we were coding that, it ran our TensorFlow model. Now I'm going to run the PyTorch one. Say Python day2 underscore PyTorch. 68 and 58 for TensorFlow. Let's wait for a little while, let it run, and then we can compare both of them. And there you go, it ran. And if you see the comparison between TensorFlow and PyTorch, it's a little bit different. If you see, the loss is 68 and this is 67, accuracy is 58%, this is 50%. So probably I'll use TensorFlow in this particular case. But again, depending on how many epochs you use, it might get better and better over time. So play around with different options and see how it all works. Just to summarize, today we gained a deep understanding of RNN architecture, including the hidden states and recurrent connections. We learned the concept and challenges of backpropagation through time, which is BPTT. We understood the limitations of vanilla RNNs and why they struggle with long sequences. And we developed hands-on skills in implementing RNNs in TensorFlow and PyTorch for sequence-based tasks. So if you have any questions or had any problems while following along or implementing this, let me know in the messages and I'll get back to you. Day 3. Long Short-Term Memory or LSTM networks. Today, let's start with introduction to LSTMs and how they address RNN limitations. Now first, what are LSTMs? Long Short-Term Memory LSTM networks are a type of recurrent neural networks RNN specifically designed to handle long-term dependencies. LSTMs mitigate the vanishing gradient problem by using specialized gates to manage the flow of information. Some of the key features of LSTMs include memory cells, which maintains a long-term memory state across sequences. It has gated mechanisms, which is which regulates how much information to keep, update, or forget at each time step. Effective for long sequences. It handles sequential data with dependencies across many time steps. Now, what are the advantages of LSTM over vanilla RNNs? First, it retains long term dependencies. Next, it prevents gradient related issues during training. And it outperforms RNNs on tasks like language modeling, speech recognition, and time series forecasting. Now, let's look at LSTM's cell structure, which is input, forget, and output gates that it has. First, for the forget gate, it decides what information to discard from the cell state. Its formula is defined as Ft equal to sigma of Wf dot of Ht minus 1 comma Ht plus B of f, where Wf is the weight matrix for the forget gate, Ft is the forget gate output, Xt is the input, and Ht minus 1 is the previous hidden state. Now let's look at the input gate. This decides what new information to add to the cell state. And the formula for this is It equal to sigma of Wi times Ht minus 1 comma H of t plus Bi, where sigma is the sigmoid activation function, Wi is the weight matrix for the input gate, and Ht minus 1 is the hidden state for the previous time step. Xt is the current input. Bi is the bias for the input gate. Next, let's look at cell state update. This combines the forget gate and the input gate results to update the cell state. And the formula is C of t equal to f of t dot of ct minus 1 plus I of t dot c of t dash. Now next, let's look at the output gate, which decides what information to output at each time step. The formula for this is Ot equal to sigma of W of O times H of t minus 1 comma x of t plus Bo, where Wo is the weight matrix for the output gate, Bo is the bias for the output gate. That's it. So I hope you understood these formulas and what they are used for. And let's go ahead and look at applications of LSTMs. First is the natural language processing, NLP. Here we can use it for sentiment analysis, machine translation, and text generation. Next is for time series forecasting. It can be used for predicting stock prices, weather patterns, or sales trends. And in speech recognition, it can be used for converting spoken words into text. It can be used for anomaly detection, where you can use for identifying unusual patterns in sequential data. With all this in mind, let's jump into our hands-on exercise for today, where the objective is to build an LSTM model for sentiment analysis on the IMDb movie reviews dataset and compare its performance with a basic RNN model. I'm just going to use TensorFlow today. You can try this out in PyTorch too. And if you had any issues in PyTorch, let me know. And I'm going to go ahead and start with the TensorFlow project. So first, let's create a new file. I'll save it as day3 underscore exercise.py. Here, first step is to import the necessary libraries. So I'm going to go ahead and import TensorFlow dot keras dot datasets, and I will import from there IMDb. Next, from TensorFlow dot keras dot preprocessing dot sequence, I will import sequential. Next, I will import TensorFlow as TF. Next, from TensorFlow dot keras dot models, I will import sequential. Wait 1 second. From sequence, I want to import paired sequences. here is where sequential is from models. Next, from TensorFlow dot keras dot layers, I will import embedding. Next, simple RNN. I'll also get LSTM this time and dense. So there you go. So we have that. Now let's go ahead and load the data set. So for that, I will first set my vocab underscore size equal to 10,000. If you remember from last, this is the vocabulary size that we want. Max length for each input should be 200. If not, we pad it, or if it is, we'll cut it short. X underscore train, comma Y underscore train, comma X underscore test, Y underscore test. I will say imdb dot load underscore data, and the number of words that I want in this case is vocab underscore size. Perfect. So that will load my data. Next, I'm going to pad the sequences to ensure uniform length among all the sequences. For that, if you remember from last 2 days, xtrain equal to pad underscore sequences. I'll pass it xtrain. I'll pass it max length of max underscore len, and I'll say padding equal to post padding. So at the end of it, add padding. If not, if it has enough value, just trim it. Next, xtest equal to sequences, xtest, max length, padding, post. Perfect. Next, I'm going to go ahead and print the shapes of the training and test set. So for that, I'm going to say print f training data shape x underscore train dot shape. Now same thing for, I'll do test data shape equal to test shape. So this will display those. Perfect. Now that we have this, next step will be to build and train the basic RNN model. For that, I'm going to start with RNN underscore model equal to sequential, and in here I will set the values with starting with embedding, and I'll pass input underscore dim equal to vocab underscore size, our output underscore dim equal to 128 with this layer. Our next layer, I'm going to say simple RNN, give it the input 128, activation equal to tan of h, and then return underscore sequences equal to false. Next, our final output layer, dense with 1, activation equal to sigmoid. So there you go, our model, RNN model is ready. Our next step is to compile the RNN model. So I'm going to say RNN dot model, or sorry, RNN underscore model dot compile. Optimizer I want to use in this case, same as what we always use, Adam. I'm going to say loss equal to, since it's binary data, binary underscore cross entropy, and metrics I'm interested is accuracy. So that's done. Next, let's go ahead and let's run the model. I'm going to say RNN model, or display the model summary. So I have my model code here. Perfect. Next step is to get the train the model actually. So let's go ahead, RNN history equal to RNN, RNN underscore our model dot, let's fit the data, x train, y train, we need epochs equal to 5. I will have a batch size of 32, and finally I need to say the validation split underscore split equal to 0.2. So these are all my parameters for my model to run. Next, I'm going to go ahead and evaluate the model. That will give me RNN loss, comma RNN accuracy. For that, I'm going to say RNN underscore model dot evaluate, evaluate, and I'll pass x underscore test, y underscore test. So that's evaluated. Let's go ahead and print our f of RNN test loss is RNN underscore loss 0.4f test of test accuracy of RNN is RNN underscore accuracy 0.4f. So now we just have created our model and evaluated the model after training. So next step is to build and train the LSTM model. So LSTM underscore model equal to sequential, and this will take, first I'm going to take copy from above because most of it is same. So we need embedding input dim equal to vocab size and output dim equal to 128. Instead of this, I'm going to say LSTM now. 128 activation is 10h, return sequences false, tense 1. As I mentioned, LSTM is nothing but an advanced RNN. So that's why it's pretty much almost same. Next, I am going to go ahead and compile. I'm going to do the same things. So I'm going to just go ahead and copy this entire stuff here. So first is to compile. So this time I'm going to say LSTM model dot compile Adam binary cross entropy metrics equal to accuracy. Then next step is LSTM model summary. Next I'm going to do instead of RNN history, I'm going to say LSTM history, and this time I'll run the LSTM model fit xtrain ytrain epochs equal to 5, batch size 32, validation split is 0.2. Next I am going to go ahead LSTM loss and LSTM accuracy is equal to LSTM model dot evaluate x test and y test, and then finally let's display LSTM test loss is LSTM loss and accuracy is LSTM accuracy of 0.4f. Now if I want to print them separately, the test accuracy, I can do that too, but we can just look through here and then compare the test accuracy of RNN and LSTM together. So I'm going to go ahead and open my terminal and say Python, project name is day3 exercise.py, and I'll give it some time. I'll come back to this in a couple of minutes to see how it does after all the 5 epochs for both RNN and LSTM. So it took around 10 to 15 minutes or so, I guess, because when you're staring at it, running through the different iterations, it's kind of painful. But here you go, we have our sequence, the model RNN, and then we have our LSTM model here. And these are the RNN test loss is 66 and 58, whereas this one loss is 34 and accuracy is 85. If you see, much better as compared to RNN, LSTM is based on the data that we have provided. So in this case, I will be using LSTM for sure. So I hope you are able to get this working. If not, let me know what happened. If you had any issues or problems, let me know and I'll get back to you. And just to summarize, today we went and understood the architecture of LSTMs, including input, forget, and output gates. We learned how LSTMs address limitations of vanilla RNNs. We gained hands-on experience building LSTM for sentiment analysis, and we compared LSTM performance with RNN and interpreted the results. So if you had any questions, if you had any issues, let me know and I'll get back to you. Day 4, gated recurrent units or GRUs. Let's go over introduction to gated recurrent units, GRUs. Now what are GRUs first? Gated recurrent units or GRUs are a simplified variant of long short-term memory LSTM networks. GRUs are designed to retain long-term dependencies while reducing computational complexity by having fewer parameters. Some of the key features of GRU include simpler architecture. GRUs have two gates, update and reset, compared to LSTM's three gates, input, forget, and output. Efficiency. Fewer parameters make GRU computationally faster and less prone to overfitting on smaller datasets. And it retains performance comparable to LSTMs in terms of capturing sequential dependencies. Now let's talk about GRU's cell structure, update, and reset gates. First, let's talk about update gate. It determines how much of the previous hidden state to retain and how much to update with the new information. Reset gate controls how much of the past information to forget when combining with new input. Hidden state update. It combines the new information and the past hidden state based on the reset and update gates. Now, when to use GRUs versus LSTMs? Now, depending on the feature, for example, if you have gates, for LSTM you use input, forget, and output. For GRUs, we have update and reset. As compared to parameters, LSTM has more parameters and GRU has fewer parameters. As per performance, it's better for complex longer sequences, and its GRU is comparable for shorter sequences. For training speed, slower due to complexity, whereas GRU is faster due to simpler structure. Use cases for LSTM include NLP and speech recognition. For GRU, it's time series data and small data sets. Now, let's talk about our hands-on exercise. Today, our objective is to build a GRU-based model for the IMDb Movies review dataset and compare its performance with the LSTM model. What we are going to do is we're going to pick the same exercise from yesterday where we did comparison with RNN and LSTM. Now, we're going to add one more to it, which is LSTM model. So let me pick that up. So I'm going to go here. I am going to create a new file, Python file, save it as day4_ex4.py, and I'm going to also open yesterday's file, which is our day3 file, which is day3ex. Copy this code from yesterday, paste it here. So this one now has both RNN and LSTM. Now our next step here will be, so we have these two. I'm going to just copy paste this here. Also, we might need some libraries above. So we have here IMDb, we have the pad sequences, TF sequential, we have embedding, simple RNN, LSTM. The only thing that is missing is GRU. So I'm going to add that GRU here. Next, I think rest of the stuff stays exactly same, but here at the bottom where we just copy pasted this code, I'm going to say GRU sequential, embedding input dimensional this thing, output dimension 128. Here I'll say GRU of 128, activation tanh, return sequence false, dense 1, everything else remains same. Again, now this is GRU model. So I'm going to say GRU model dot compile optimizer Adam loss binary and cross entropy and metrics equal to accuracy. For my GRU history, I'm going to use my GRU model dot fit, and inside this I will use xtrain, ytrain, epochs 5, batch size 32, and validation split is 0.2. Next, I'm going to get my GRU loss and GRU accuracy, and then get my GRU model dot evaluate xtest ytest and print GRU test loss, say GRU loss and GRU accuracy. So perfect, GRU test loss and test accuracy for GRU. I'm displaying it here. Now we can go ahead and compare all of them together by running them. So I have all three. Perfect. Now let's open terminal and let's make sure I'm in the right folder. Yes, I am. And I'm going to say Python day exercise 4 run it. And now, since it's running through three different models, I'm going to give it some time and come back to this video after around 15-20 minutes, maybe more, because RNN will run faster, LSTM takes longer time, and GRU is much more faster, as you can see. So I am going to stop here and come back in some time. It took around 20-30 minutes. I don't know. I stopped count after a particular time, and when I came back, I saw that it was all run. This is our RNN, which has 67% loss and 59% accuracy. Our LSTM has 38% loss and 86% accuracy, which we've seen already, and it's much better than LSTM. Now let's compare GRU to it. Our GRU is a loss of 46%, which is higher than LSTM in this particular case because the data set is much bigger, and 86% accuracy versus 86% accuracy. So accuracy is slight better in LSTM, but it's very close. Maybe if we run for more epochs, we can see much better improvement in either of these. So try to play with it and let me know how it goes. And just to summarize, today we understood the structure and functionality of GRUs, including update and reset gates. We learned when to choose GRUs over LSTMs for sequence modeling tasks. We gained hands-on experience building GRU-based models for NLP tasks. And finally, we compared GRU performance with LSTM models to identify the trade-offs. If you had any issues while following along and building this application or have any questions, let me know in messages and I'll get back to you. Day 5. Today, let's start looking at importance of text pre-processing. Now first, what is text pre-processing? Text pre-processing involves cleaning and preparing raw text data to make it suitable for machine learning models. It is a critical step for achieving high performance in natural language processing tasks. Some of the key steps involve tokenization, which splits the text into individual units. Example, it can be words or sentences. Here is an example where I love NLP is kind of split into I, love, and NLP, three different words. Next is stemming. It reduces words to their root form by removing suffixes. For example, running or runner becomes run. Then we have lemmatization, which converts words to their base form using a vocabulary. For example, better becomes good. Now, why is pre-processing important? First, it reduces noise in the data. Second, it standardizes the input for models. And third, it improves feature extraction and model accuracy. Now, let's talk about introduction to word embeddings. Now, what are word embeddings? Word embeddings are dense vector representations of words that capture semantic meaning. Unlike one-hot encoding, embeddings represent words in a continuous vector space. Some of the popular word embedding models include, we have word2vec. The models are continuous bag of words or CBO and skipgram. It captures word relationship based on context. Then we have glove, which is global vectors for word representation. This uses word co-occurrence statistics to generate embeddings, and it represents global semantic relationship. We'll be using this in today's exercise. Next, we have pre-trained embeddings in frameworks. Frameworks like TensorFlow and PyTorch offer pre-trained embeddings for quick integration. Let's look at some of the benefits of word embeddings. One, it reduces dimensionality, it captures semantic similarity, and it improves the model generalization. Now let's look at using some of the pre-trained embeddings for NLP tasks. Now, why use pre-trained embeddings? One, it saves computational resources. Second, it leverages large, well-trained models. And third, it boosts the performance for downstream tasks. Some of the popular pre-trained embeddings involve Glove, which is pre-trained on datasets like Wikipedia and Common Crawl, and as I mentioned, we're going to use that today. Fast Text handles out of vocabulary or OOV words through subword embeddings. And then we have embedding layers in deep learning frameworks like TensorFlow and PyTorch. Now with this, let's jump into our hands-on exercise where the objective is to pre-process a text dataset and integrate word embeddings, example glove, into an LSTM model for sentiment analysis. So let's get started. First, I'm going to create a new file, Python file, save it as day5 underscore ex.py. Now you'll see one file already in there. Let's talk about that file before we do that. So for glove embeddings, you can go to this website nlpstanford.edu projects glove, or just search for glove and this should show up. In here, you'll probably say download pre-trained word vectors, and there will be a zip file right here which you can download. Now once you download this glove.6b.zip file, what you're going to get is, I'm going to show my downloads folder. It will give you this glove.6b zip file. Inside that, you'll have a bunch of different embeddings, 300D, 200D, 100D, 6p, and this is pretty huge. It's around 800 some MB. So once you have that, take the 100D and put it in your folder. In my day 5 folder, I put that file over there, which has all the word embeddings in here. So that's what we'll be using. So next step, I'm going to go to the file and first import the necessary libraries. So I'm going to say TensorFlow dot keras dot datasets. Again, I'm going to use the same dataset from before, which is IMDb. Next, from TensorFlow dot keras dot preprocessing dot text, I am going to import tokenizer. Next, from TensorFlow dot keras dot preprocessing dot sequence, I will get pad underscore sequences. So these are three things that I need right now. Let's go ahead and load the data set. So I'm going to say load data set. First one, I'm going to say, first I'll say vocab underscore size equal to same as what we used before, 10,000. Next, we are going to set the max length to 200. Was it 100 or 200? I'll set 200. Next, I'm going to say x underscore train, comma, y underscore train, and x underscore test, comma, y underscore test equal to imdb dot load underscore data, number of words that we need equal to vocab size. So once I have that, next step is to decode reviews to text for pre-processing, which is what we're going to do is I'm going to say word underscore index equal to imdb dot get underscore word underscore index. So I get word index. Next, I'm going to say reverse the word index variable equal to, I'm going to say value is key for key value in word index, whatever I've created above, dot items. So this will give me the reverse word index. Next, I'm going to get my decoded reviews equal to, I'm going to create a string concatenation where I'll say join, and I will say reverse underscore word index dot get I minus 3 comma question mark for I in review in x underscore train up till 5. I am missing in review, for review in x underscore train. I don't need this, and I think I have extra closed, or let me try again. So I said reverse word index dot get I minus 3 for I in review for review in, oh I forgot, to close this one in review for review in X train colon. Okay, perfect. So that looks perfect to me. So that will give me my decoded reviews. Next step is to pad the sequences. So I'm going to say pad sequences. Now here I'm going to first do pad X train equal to pad sequences, pass it X train. We've done this bunch of times. Max length equal to max underscore length, and then we give padding at the end. So I say padding equal to post. Same thing I'm going to do for X test padding, pad sequences, X test, max length, post. Perfect. So that takes care of it. Now let's look at the shapes. Print f of training data shape is equal to x dot underscore train dot shape comma y underscore train dot shape. Perfect. Now next I will do it for test data shape, which is x test and y test dot shape. Perfect. So this it completes our first step where we load and pre-process the data set. Our next step is to load the pre-trained glove embeddings. Now this is new, so we're gonna go through this very carefully. First, for this we need numpy, so I'm gonna go ahead and import numpy as np. Next, we're gonna load the glove, just say glove embeddings, even though the official way to write it is with capital V. Next, I'm going to say embeddings underscore index equal to empty, and then I'll get the glove file that is in my same directory as this, and the name of the file is glove.6b.100d.txt file. If you want to cross check, you can just cross check here 6b100d txt. Perfect. So that's the path. Now next I'm going to say with open glove file in read format. I don't have to write anything, just reading. Encoding equal to utf-8 tf-8. So this is how I read a file as file, if you remember from our first week where we learned how to open files. Now for line in this file, for each line I'm gonna say values equal to line dot split. I'm gonna split them into words, so I'm gonna say word equal to values of 0. Next I'm gonna say coefficients equal to np dot as array, and this I'm gonna pass values of 1 colon, and then data type that I want is of float 32. So that will give me my coefficients, and then finally embedding underscore index of a particular word is equal to coefficients. Okay, that's perfect. So I think I have everything that I need. Embedding index any. Okay, I think that's right, but let's see. Print next I'll say f of loaded length of embedding index word vectors. So let's see, embeddings index, that's why it was causing problem. Embeddings in the word vectors. Perfect. So I have loaded my glove embeddings. Next step is to prepare the embedding matrix. So to start with, I'm going to create a variable embedding dimensions equal to, set it to 100. Next I'm going to say embedding underscore matrix equal to, I'm going to create a matrix of zeros, dot zeros, and I'll pass to that our vocab size and our embedding data. Oops, where is my embedding? Oh, sorry, embedding dim. So once I pass that, next I'm going to go and go through for each word and I in our word index of items. So for each and every word here, I am going to check if I is less than vocab size. So to make sure that it doesn't exceed that. As long as it's less, what I'm going to do is I'm going to say embedding underscore vector variable that I'm creating here is embedding underscore index embeddings index dot get the word. That doesn't sound right, embeddings index, because it's actually embedding index. So I'm going to change that everywhere. So that's good. So that's done. Now next I'm going to check if embedding vector, whatever we got above, is not none. Then I'm going to say embedding matrix of I is equal to embedding vector. So I am embedding, I'm preparing my embedding. This kind of gets me my embedding matrix. Now next step is to build an LSTM model with these glove embeddings. To do that, first let's go ahead and import some things we need from TensorFlow Keras models. We need the same thing that we used before, sequential. Next I need layers, so I'm going to say Keras dot layers. I need embedding LSTM, and I'm going to use dense. So these three. So now I have these, let's go ahead and here let's define the LSTM model with glove embeddings. So to do that, I'm going to say model equal to sequential. Next, I'm going to say embedding is input underscore dim equal to, that was our vocab size. Next, our output dim is embedding dim right now, and then weights equal to I will use the, here is where I'm adding the embedding matrix. So I'm going to say embedding matrix, this is new for us. And then finally I'm going to say trainable equal to false. So that's good. Now that I'm done with embedding, the rest of the stuff is pretty much same. LSTM 128 by activation equal to tan h. I'll return sequences equal to false. Make sure the type, there's no typos. Activation, okay, return. Next I'm going to create our final output layer, dense 1 equal to activation equal to sigmoid is what we use, so that's what I'll use. Now once this is done, next step, as we know, is to compile the model. Now to compile the model, I just say model dot compile optimizer equal to Adam. Next I need loss equal to, we use binary underscore cross entropy. Next for metrics I will use accuracy. Next let's go ahead and display this model. So I'm going to say model dot summary. Now once we display this, our next step is to train and evaluate the model. So to train, I'm going to say train the model. Let's say history equal to model dot fit, and to this I'll pass x underscore train, y underscore train. I'll give a validation split of 0.2. I will say epochs equal to 10. I'm feeling very adventurous today. Batch size equal to 64, and I'll say verbose equal to 1. Now this will train the model. Next, go ahead and evaluate it. So I need loss and accuracy. Model dot evaluate x underscore test, y underscore test, and verbose equal to 0. Now let's print the LSTM model with glove test accuracy is accuracy 0.4f. Perfect. So that will give my LSTM accuracy. Now, if you want to compare the performance with the non-embedded LSTM, so I'm going to probably get the code that we wrote earlier to get the get the LSTM without glove embeddings. So I'm going to just paste it here, which is LSTM model sequential embedding input dem vocab size. Output is this LSTM usual and dense. Next we said model.compile. This is what we did. Then we created this. I want to make sure it's as same as this. Validation size of 0.2. Batch size is 32. I'm going to change this batch size to be same 64. And epochs I'll make both of them 5 since I'm running 2 of them. Okay, so I have all the data as same as this. Next, LSTM, evaluate this, and then we can look at the LSTM test accuracy only. So that will give me LSTM test accuracy without glove embedding, and this is with glove embedding. So I'll see both of them next to each other. I am going to cut this and put it here, and this one I'll say accuracy LSTM without glove. Ignore my typos here. I'll try to fix whatever I can. Again, this is glove. So this is what I get. Next, I can also do one more thing to display it. Let's go ahead and import matplotlib, and I am going to plot both of them side by side. To do that, I am going to say models equal to, so what are the two models that I have? LSTM with no embeddings, and the next one is LSTM with glove. So these are my two models. I'm going to say accuracies for these equal to accuracy. One is accuracy, this is LSTM, so LSTM accuracy, and the next one I'm just using accuracy because that was the first one that I wrote. Then I'm going to say plot dot bar models comma accuracies. So I'm going to plot these. I'll say color. I'll give two different colors. For my LSTM, I'll give blue color, and for glove, I'll give green, just to compare. Plot dot title. Now again, these might not be like LSTM might turn out better than glove, but we never know. Comparison of LSTM with and without word embeddings. As I said, these models work based on how much data you give or what type of data you give. So it's always difficult to know unless you use it if it's good or bad or which option is better for you. I say plot.show. So I have all that thing that I need. So I'll go ahead and run it. I'm going to save it, open my terminal and say Python day 5 and run it. It's going to take some time. So I'm going to stop here and come back once it completes the entire run. It looks like I have given a wrong word here. Value key for this is a reserved word. So I need to make sure that I don't use, where is that I've used? It did try to tell me that use value, but okay, perfect. Clear it out. Let's see if there's any more errors before we stop this video and pause it for the moment. Okay, it's working. So I'll wait for it to run, and once it's done, I will record again. So here we go, and after running for 5 iterations for our data with glove and without glove, this is the output that we see. And as you can see, the accuracy for LSTM is more than 80%, 86%, whereas with glove test accuracy is 53%. So looks like it added more data than it needed then, and kind of made the accuracy much worse as compared to with LSTM. So that might happen sometime depending on your data set. So you have to always try with different combinations to see which model and with what technique it works perfectly fine. So just to summarize, today we understood the importance of text pre-processing in NLP tasks. We learned the role and benefits of word embeddings like word to vec and glove. We gained practical experience using pre-trained embeddings in deep learning models, and we compared and interpreted the performance of models with and without embeddings. So if you had any problems implementing this or didn't find the files or had any issues or have any questions, just let me know in the messages and I'll get back to you. Day 6, sequence to sequence models and applications. So let's start with sequence to sequence or sec to sec models and their architecture. Now, what are sec to sec models? Sec to sec models map an input sequence to an output sequence of different lengths, widely used for tasks like language translation, text summarization, speech to text, and chatbots. The architecture involves an encoder which processes the input sequences and encodes it into a fixed length vector, also called as a context vector. Then we have a decoder which takes the context vector as input and generates the output sequence step by step. Let's get into encoder decoder framework for sec to sec tasks. How does it work? The encoder sequentially processes the input sequence using RNN, LSTM, or GRU, and then it produces a context vector representing the entire input sequence. The decoder initializes its hidden state with the encoder's context vector, generates the output sequence one token at a time, and predicts the next token using the previously generated tokens. Next, let's talk about attention mechanism overview. Now, why attention? Standard sec to sec models compress the entire input sequence into a fixed length vector, which can lead to information loss for long sequences. Now, this attention mechanism dynamically focuses on different parts of the input sequence when generating each output token. Now, how does attention work? It calculates a weight or score for each input token based on its relevance to the current decoder state, and then outputs a weighted sum of the encoder outputs, creating a context vector for each decoder step. Let's look at our hands-on exercise for today, where the objective is to build a basic sec-to-sec model using LSTM for translation and experiment with the hyperparameters. So let's get started. Today I'm going to use PyTorch for our project. So I'm going to start with new file and I'm going to save it as day6 underscore exercise. And again, this today we're going to start with PyTorch. So first let's import the libraries. I'm going to say import libraries. First one that we need is import torch. Next we want to import torch.nn as nn. Next I need to import for optimizers optim torch.optim as optim. Next I want to get from torch.utils.data import. We'll get our data loader and we'll get our data set. So we have that. Next, finally, we'll go and import numpy as np because we might need to do some array operations here. Now, for simplicity, we'll use a small manually created English to French translation dataset, and I have that ready. So I'm going to just use that and paste it here. Now, this one has some English sentences like hello, how are you, good morning, thank you, and good night. Now, my French is not good, but based on Google Translate, I got these French sentences. Hello is bonjour, how are you is this, good morning is this, thank you is this, and good night is this. I'm not going to even try to speak French right now. But anyway, so we have this here. Next step is vocabulary and tokenization. That's what we're going to do. Here, I am going to create a function called as build underscore vocab. And for that, I'll pass my sentences. And once I have this, I'm going to create my vocab equal to. In here, we'll add some padding. And so for that, first is pad of 0. Next, we have SOS of 1. Next, we'll add end of EOS, which is 2. Next, I'll add UNK, unknown, as 3. So these are different vocab key value pairs that I have. Now, for sentences that I'm getting in, for actually sentence in sentences that I've been passed, I'm going to run through each and every sentence, and I'm going to say for word in sentence dot split. I'm going to check if word not in vocab, if this word doesn't exist in my vocab, I'm going to say vocab word equal to length of vocab. And then I will return this vocab outside my for loop. So this is my, this will create my vocabulary and tokenization. So next step is, let's create the English vocabulary. To do that, I'm going to say build underscore vocab. I'm going to call that. And then to that, I'll pass my English sentences here. I'm going to pass it here. And then when I want to create my French vocabulary, equal to build vocab. So this is how translations can be done using AI these days. So you got an idea of where we are heading. So now let's go ahead and next I want to tokenize and pad the sentences. To do that, I'm going to create a function called as tokenize. And to that, I will get my sentences, I will get my vocab, and I will get what is the max length that I want to use here as inputs. Now first, I'm going to say tokenized equal to an empty list. So I'm going to initialize with an empty list. And then I'm going to say for sentence in sentences, I'm going to run through each and every sentence, and I'm going to say token equal to vocab dot get word for vocab of, oops, I think I put a little bit extra, UNK. And then for word in sentence dot split. So that will be my tokens. Next, I'm going to say tokens equal to vocab SOS, close this, plus tokens plus vocab of EOS. Next, I'm going to say tokens plus equal to vocab of next, now padding, pad, close this, times, oops, times max underscore len minus length of tokens. And then finally, I'll say tokenized dot append, that's my list here. I'm going to append whatever tokens I created into that. Then finally, I'll return my np dot array of tokenized. So I'll pass my tokenized array back to whoever called it, along with so whoever called it with sentences vocab max. I'm going to return back that. Next, what I'm going to do is I'm going to get the max length for English and French. So for that, I'm going to say max length of English equal to max of length of sentence dot split. Now where does this come from? Again, this is something that I'm going to do here for sentence in English sentences plus 2. So that will give me the max length for English. Same thing, I can do it for French. I can say fr max length sentence or split for sentence in French sentences. There you go, plus 2. So that will give me the max length for French sentences. Now when I want to create the database for my English sentences, I'm going to say English data equal to tokenize, and to this I'll pass the sentences first, then it needs the vocab. So I already created the vocab, I'm pass the English vocab, and the max length I'll pass max length English. Similarly, now I can do, okay, I think there is some problem here. English sentences, not just sentence. Okay, next one for my French data is my tokenize. I pass my French sentences. I'll pass my French vocab. I'll pass my max length of French. Perfect. So this will create, this will have my sample data set created. Now that I have my data set, let's define data set and data loader. So for that, I'm going to create a class called as translation data set. So this is my translation data set, which takes the data set as input. And here I am going to define a initializer first. Initializer which takes self, which take the source data, whichever data it is, either English or French, and my target data. So that's my initializer function. I'm going to say self dot source src data equal to the source data that was passed to me. Next, I'm going to say self dot target data is whatever target data that was passed to me. So that is initialized. So my initial object gets initialized here. Next, I'm going to call the underscore length, and I'll pass self as an object here. And here I will say return whatever the length of self dot source data is. So that will give me the length of the source data. Next, I can say if I want to get a particular item, I'll create a get item function, and to this it needs self and id x and index. So this will return back torch dot tensor self dot src underscore data at that particular index idx. So I'm converting that into a tensor here, and it needs torch dot tensor for self dot target data with that particular index that is passed here. Perfect. So this will return back my target tensor, sorry, source tensor and target data tensor back to whoever called it. Now let's go ahead and create those data set elements. So I'm going to say data set equal to call this translation data set, and to this I'm going to pass English data and French data. That's about it. Next, I'm going to create my data loader. Now data loader, I can use the data loader class and pass a data set, something that we've done with data loaders earlier. Comma, I need a batch size of how big batch sizes you want. I'll set the batch size to 2, keep it small enough. And I'll say shuffle equal to true. I don't have that much data, so why not shuffle it? So that kind of creates our data set and data loader. Now the next step is to define the sec to sec model components, which is encoder and decoder. So first, let's create our encoder. Now to create encoder, I will use nn.module in here, and then first the initializer it needs self, and the arguments that it needs, I'm gonna enter it here. Arguments that it needs is input underscore dimensions. I need to pass embed underscore dimensions. I need to pass hidden underscore dimensions and number of layers that it needs, because we are going to use LSTM eventually, that's why. And then here I am going to say super encoder is what the class name, self, and initialize with empty set. Perfect. So that super is called. Next I'm going to say self dot embedding. If you remember from first few days of this week, this is what we did in for embedding in embedding layer. I'm going to say it passed the input dim and it needs embed dim. So if you want to refresh some of these things, you can just look at some of the earlier day of this week. Self.lstm, for that I will say I want to create nn.lstm, and to this I will pass this needs embed dim, then it needs our hidden dim, hidden dimension, number of layers. I need batch first equal to true. So this will create our encoder initializer class. Next we need the forward function. Oops. Forward function which takes self and x as inputs, and this will create my embedded object which is self dot embedding and pass it the value of x. Next it will create outputs, and it will also create our hidden and cell object. This will be coming from self.lstm and pass it the embedded that we got in the previous step. And then we'll return, we don't care about the output, so we'll just pass hidden and cell back. Perfect. So that's our class for encoder. Now let's go ahead and create the class for decoder. So class decoder, again nn.module. Next step is to create our initializer method init. Oops, I don't know, sometimes I feel like it's easier to handwrite it. Self, we need output dim underscore dim, output dimensions. We need embedding dimensions, embed underscore dim. We need hidden dimensions, same as our encoder, and we need the number of layers that we need. Next I will call the super class super, and then to this, as before, we will pass decoder and self. Perfect. So that creates a super. Next I'm going to call the embedding equal to nn dot embedding, and this will embedding needs output dimensions and embed dimensions. Perfect. So once this is done, next thing is our LSTM layer. LSTM needs nn dot LSTM, and I will have to pass the embed dimensions. Next we need to pass the hidden dimension. Next we need the number of layers, and next we need batch first equal to true. So this is takes care of ls. Now my fc function is equal to nn dot linear, and then this needs our hidden dimensions and my output dimension. Perfect. So this takes care of that. Next I'm going to call my forward function, and to this I'll pass self, x, hidden, and cell. So my forward function now will say x equal to x dot unsqueeze first, unsqueeze with 1. So this will add the time dimension. Next I'm going to say embedded equal to self dot embedding and pass it the value of x. Next I'm going to say outputs comma hidden comma cell equal to self dot lstm and pass it embedded. This time we need to also pass the hidden and cell, so I'll pass hidden and cell in a tuple. Perfect. So that's passed. Next, let's get our predictions. So predictions, I'll say self.fc. I'll have to take the outputs from above and squeeze them with the parameter of 1. And now finally I can return my predictions, I can return my hidden, and I can return my cell items back in this decoder class. So I have my decoder class ready. Now finally, let's create our sec to sec class. Now move it up all the way. And I'll start with sec to sec, and I'll pass the nn dot module to it. Now inside here first goes the initializer method. So I'm going to create that init underscore underscore. I am not going to use the autocomplete. Encoder, I need the decoder and it needs the device. So these are the parameters that we need here inside the initializer for sec to sec. So again, we call the super, pass sec to sec. Next is we'll pass self dot underscore underscore init. There you go, call this function. Perfect. So super is called. Now I'll have to assign the values for encoder equal to whatever was passed as encoder. I'll say decoder equal to whatever was passed as decoder, and finally self dot device is equal to whatever the device that was passed in this particular initializer function. So that will create our basic initializer function. Now let's go and write the forward. This is a little bit complicated because it has a lot of different elements in here. Self, src, target, source, target. Now after target, I'll say teacher forcing ratio. This is used to teach a particular element at 50% is what I'm gonna set. Next, first start with the batch size. Batch size equal to the source dot size at index 0. So that's my batch size. My target length parameter will be, or variable is target dot size at index 1. Next thing is target underscore vocab size. For this, I will set it based on self dot decoder dot fc dot out features. So that's what our target vocab size is. So that should work. Our next step is let's get the outputs. Now outputs in this case is first I'll have to zero out torch dot by calling torch dot zeros and pass it. It needs batch size as the first parameter. If you see in the help here, it will tell you what all different things you need, but I've done it enough times that I remember. Next I need the target length. Next I will need the target underscore vocab size, and that I'll convert dot to self dot device. So there you go. That should take care of the outputs. That will give me the outputs. Next, I need the hidden and cell. That is coming from self dot encoder. If you remember the function that we wrote over there, I pass src to it above. So that will give me hidden and cell. Now next I need is input, and that I can get from tgt target from colon to 0. That will give me my targets. Now let's go ahead and for t in range of 1 to target underscore length, so I'm going to run through this particular range based on the target length. I will get first output comma hidden comma cell by calling the decoder. So I'm going to say self dot decoder, and decoder needs input, it needs hidden, and it needs cell. If you remember, that's what how we created the decoder, which needs all these items, and that's what we'll get output, hidden, and cell from this. Once I get that, I'm going to say outputs colon comma t comma colon. I will assign output to that. So that those are my outputs parameter. Next thing I'm going to do is I'm going to go ahead and why is it moving me? Okay, there you go. Top 1 equal to output. So from my output dot argument max, I'm going to get the first element, and that will be my top one, which will be used inside the input by saying tgt colon comma t if torch dot random of one dot item is less than teacher forcing ratio, else, so if it's less than the teacher ratio, which is 0.5, it will set that, or else we'll say top 1 is the value for input. So this we can return back as outputs. We can return back the outputs right here. So next step, after once this is done, let's go and initialize the model and hyperparameters. So I'm going to go outside here to initialize the model. So first let's start with device equal to torch dot device, and to this I will say, now depending on if you what type of system you're running, I'm going to say CUDA if torch dot CUDA dot is CUDA is available, or else we will use CPU. So in my case, probably just use CPU right now. I'm going to say input underscore dim equal to length of English vocab, and for whatever sample we are using here, it will work perfectly on our local computers. Output dim equal to length of, that is our French vocab. Take that, and next we need embed underscore dimension. This I will set it to 64. Next I need the hidden dimension, hidden underscore dim, I'm going to set it to 128, and then I need number of layers, that I'll set to 2. Now these parameters I've set up just so that I can create my encoder, decoder, and sec to sec. So let's call the encoder function or class. This needs all the different parameters that we said. First it needs the input dim, so I'm going to say input dim. Next it needs, as you can see, embed dim, so I'm going to give the embed dim that I've created. Next I need the hidden dim, so I'm going to provide that, and then finally number of layers, which I've also created, so I'll pass those. Next let's create a decoder. Now decoder needs, let's see what it needs. Decoder, it will need the output dim, so we already have that output dim. Next it needs the embed dim, so I'll pass the embed dim. Next it needs the hidden dim, I'll pass hidden dim, and finally number of layers. Oops. Number of layers. Perfect. So that will create my decoder. Now let's create our model, sec to sec. Now this needs, as you can see, encoder, which we just created above, pass that. It needs the decoder, pass that, and it needs device here, which I've mentioned above, depending on what we have, see either CPU or CUDA, depending on its availability, dot to device. So there you go. So that will have my model ready now. Now our next step is to training. So now the model is ready as usual. First let's create our optimizer, that is using optim dot Adam, and I'll say model dot parameters. That's the first thing that it needs, and the next thing that we need is the learning rate equal to 0.001. Perfect. So I'm an optimizer. Next criterion for this I will use nn dot cross entropy loss, and I will ignore the ignore index equal to French underscore vocab. The pad part I will ignore that. Padding is ignored here. So that's what I mentioned as my criterion. Now let's create our training function. So I'm going to create a train function. This will need model. We have to use data loader, which we have created already. Optimizer we have set optimizer, so that another we need criterion that is also created above. Next I need device, and I need number of epochs to run this, and this by default I'll set it to 20 because we have a small data set. that we've created. So we don't have to worry about that. First, let's put it in the training mode. So I'll say model.train, initialize that. Next, I'm going to say for epoch in the range of total number of, it's going to run 20 times if not specified. uh, I'll set epoch of loss equal to 0. If you have a bigger data set, you can probably pass that and make it generate better text. Target in data loader. So for the source and target, I'm going to say source comma target equal to src dot to device comma target dot to device. So this will create my source and target. Next, let's create my optimizer. Let's zero out the optimizer. So I'm going to say optimizer dot zero underscore grad. So this will zero out all the previous optimizers. Output equal to model of src comma target. That's what we pass. Next, we set the output equal to output equal to output of colon from 1 to 1 colon dot reshape and pass it -1 to output dot shape of 2. So that take care of our output. Next, target equal to target of colon comma 1 colon dot reshape of -1. So that will take care of my target. Now we need the loss, and then we'll call the backward class, backward function, then step function on the optimizer, and we'll increment the epoch loss. So for loss, I can get it from criterion and pass it output comma target that we just created above. Next, I need to get, as I mentioned, loss dot backward, the backward, and then optimizer dot step up. Perfect. So step. Next, I'll say epoch loss. I have to increment this plus equal to loss dot item. Perfect. This is same as before that we've done. Now let's to check it out. I can always print here f of epoch plus 1, since it starts with 0, divide by total number of epochs, and I'll say loss is epoch underscore loss divide by length of data loader. So this will give us, and then again, if you want to not see the entire numbers, I'll just say 0.4f. So it's only 4 decimal places. Now that it's complete, finally, let's go ahead and train it. Model data loader optimizer is what it needed. Next, optimizer, I have that. I have the criterion, so I'll pass that, and then finally device, of which device I'm running this, pass that. Perfect. So this is done. Our next step is to translate a particular sentence, the actual code. To translate whatever is provided to us, we need to go ahead and translate it. For that, I'm going to say define translate underscore sentence. Now what all does it need? For this, we'll need the model, we'll need the sentence that is passed, we need the English vocab that we've created to check, we need the French vocab if you want to convert to that, I need that, I need the max length in French so that I can see how much far it can go, and then finally device. So this will translate. Now here first I'll say it's pretty much translating is evaluating the model. So we start the model evaluation. I'll get the tokens equal to, now it comes from English vocab, and I'll say get for word that we have English vocab, and then inside that UNK is what I'm looking for. UNK is my parameter that I have. for, now where is the word coming from? Word is coming from in sentence. So our sentence that we have passed, if we just split that, we're taking each word at a time to kind of get the tokens from there. So that will give us the tokens. The next step here is to get the tokens again based on, so first we based on UNK, then but we need to get the start and end, start of statements and end of sentence. So for that I'm going to say English underscore vocab. My start of sentence is I've used SOS, and my tokens that I got from above plus my English vocab and the end of sentence that I've used, EOS, end of sentence. So that will create my entire token list. Now the token list is created. Let's create the source equal to torch dot tensor, and I'll pass the tokens to it, unsqueeze so it's proper length or proper dimension, dot to device. So that will take care of that. Now let's go ahead and open, let's go ahead and make sure that we ignore the gradients, so no grade, and this will give us here, let's get the hidden end cell that is coming from model dot encoder, that encoder class that we created, and we pass the source, and that will give us the hidden underscore cell. Oh, I think no underscore torch, sorry, I think when you type to first you sometimes mess up. No grad, okay, perfect. So I have this. Now next thing, I'll get the target vocab equal to v of k for k, where v in French vocab dot items. I usually try to use better parameters, but it's difficult to do it when you're doing so much coding. Target indices that we are looking for is inside my French vocab, and the ones that I'm looking for is start of sentence in the start to start with. Next, for underscore in range of max, because I don't care about this parameter, I just want to loop through the max length French. That's why I use underscore in here. Now I can say tgt underscore tensor equal to torch dot tensor of tgt underscore indices. There you go, I have that, of indices of -1. That's where my thing is, and then I convert that to device. Perfect. So that will give me my target tensor. Next, I want to get the output hidden and cell. Output hidden and cell. This will come from model dot decoder function that we have written, or decoder object that we've given, and this needs our target tensor, hidden and cell. So this will give me my output hidden and cell. So now I can do my predictions equal to output, and from there I'll get our argument max of 1 dot item. Next I get the prediction. Now I get the target underscore indices. For these I can now go ahead and append the predictions. So now, if also another thing that I have to check here is if predictions equal to French, French underscore vocab of, if it's end of sentence, then what do? I just break out of this. Oops, break again. Forgot to put a colon here. Perfect. So that's done. Now I'm out of it. I've got everything in. Now let's go ahead and get the translated sentence equal to target underscore vocab of I for I in I in target underscore indices of from 1 to -1. It's all over. And then that will return back. Let's get space and join, and to the end of it let's pass the translated sentence. So that will, is it, I said translate sentence. Okay, translated sentence. Now let's go ahead and test all these things out. So I am going to do a test translation here. Now to do that, first I need a sentence. I'll say sentence is good morning. I'll try good morning and good night. Translation equal to, I'll call the translate function, translate sentence function, pass the model, pass the sentence that we have. It needs English vocabulary that we have created, so I'm going to pass that. Next thing it needs is the French vocabulary that I'll pass. Next it needs the max length for French, so I'm going to pass that because I have that too, max length of French. And then it needs the device, which I also have. So that's why we created all those different things. Now finally let's go ahead and say translated sentence is, I'll pass the translation object here. Perfect. So this should work right now. I've written a lot of code, almost 169 lines of code to build this entire translation. It's not that too much if you think about it to build a translation engine. But again, my data source is just a list of items here, but you can give data list from somewhere else. If you have some data set available, you can give that as inputs here and it will work perfectly. So I'm going to go ahead and say Python day 6. Let's hope I don't have any typos, which is not possible. Again, this is not closed here, so I'll have to find where is that. I'll have to find SOS. That's what I've used. So let's make sure this is closed. Perfect. So that's good. Let's go ahead if that is the only problem. Nope, we have more issues here. So torch has no attribute ran, which is, where did I give it? So torch.ran. Oh, okay, I see it here. Instead of random, I used ran. So that's perfect. Save, close. Let's clear it out. Let's run it again. And number of epochs is not defined. So let's see, where did I use that number of epochs? That is number of, what was it? Epochs. Okay, there you go. What was the typing? Oh, I missed the H. Perfect. So let's clear it out. Right. If you're following along, you probably have the same errors or you probably already figured out. So there you go. Bon matin for good morning. That's right. And if I say good night, it says bon nuit. So let's go ahead and add that. Clear it out. Run it again. And there you go. We have this working perfectly based on, it tries to train based on the data and gets you as less loss as possible and gives you the translated output from this particular model. Now, just to recap, today we understood the architecture of sec-to-sec models and their use cases. We learned how to implement encoder-decoder frameworks with LSTMs. We gained insight into attention mechanism for enhancing sec-to-sec models and developed skills in building and experimenting with sec-to-sec models for NLP tasks. In our case, we kind of did a translation, built a translation engine. So I hope you were able to follow along and build it. If not, if you were able to get through the code and implement it, that's good. If you had issues or problems or have some questions, let me know in my messages and I'll get back to you. Welcome to day 7 of week 11, our last day of this week. And today we're going to work on an RNN project for sentiment analysis. Now the steps that we're going to take here is first applying RNN, LSTM and GRU models to a complete task, in this case sentiment analysis. For the project overview, we'll choose a task which is sentiment analysis. Another option was text generation, which we kept for later. And inside sentiment analysis, we'll classify text into categories like positive or negative sentiment. Next, we're going to use RNN, LSTM, and GRU models to solve the chosen task. So we're going to use all of them for this particular project. We'll focus on pre-processing, embedding integration, model architecture, and hyperparameter tuning. Next, we're going to look at analyzing the model performance. Some of the key metrics we're going to look for our sentiment analysis project is accuracy, precision, recall, and F1 score. Next, for tuning hyperparameters, we look at embedding size, number of hidden units, learning rate and optimizer choice, and sequence length and batch size. Next, for experimenting with architecture and techniques, for architecture variations, we look at single layer versus multi-layer RNNs, bidirectional RNNs for improved context capture. For pre-processing techniques, we'll use tokenization, stemming, and lemmatization, and padding for sequence uniformity. So let's get started on our hands-on project for this week, which is build, train, and optimize RNN, LSTM, and GRU models for sentiment analysis. So let's get started. So first, go ahead, create a new file, save it as day 7 project. Inside here, first step is to load and pre-process the dataset. We'll use our favorite IMDb movie review dataset, but if you have any other dataset, go ahead and feel free to use it. Now from TensorFlow.keras.datasets, I am going to import IMDb. That's the first step. Next, from TensorFlow.keras.preprocessing.sequence, I will import pad sequences, which we'll use to pad the sequences that we have. So we have both the functions that we need ready. So let's go ahead and load the dataset. Now you're probably used to this. First thing that we have to create is a vocab size, which I want to limit it to 10,000. So that's what I'll specify here. Next, I want to set the max length. We're going to reduce the length here. We can just set 100 for now. Now let's go ahead and load the database. So imdb dot load underscore data, and here I specify number of words equal to vocab underscore size. Now this will give me x underscore train comma y underscore train as one tuple, and then it will give me x underscore test and y underscore test as a tuple 2. So I have all the data that I need. Now let's go ahead and pad the sequences. To do that, I'm going to say x underscore train equal to pad underscore sequences and pass it x underscore train. We'll pass the max length equal to max length. Next, I need to pass a padding of post, which means pad to the end of the sentence. Next, I'm going to say x test equal to, I'm going to use the same thing. So why not copy paste it? Copy this, paste it here. Perfect. So I have that. Next step is to print the shapes just to check if everything is good. This is where you can actually catch issues. The reason I've done it again and again is a lot of times the shapes don't match, and that's why you get errors. That's probably, if you're one of them, you probably know what I'm talking about. So it's always good to check the shape sizes just to make sure that they are matching, because that's the first place of error that you can get. Dot shape. It's very difficult for me to talk and type, as you can see. Next, I'm going to say test data shape equal to x test and y test dot shape. So once I've cross-referenced this, next step is to build RNN, LSTM, and GRU models. So let's start with RNN. For RNN, as you remember, we probably need something from TensorFlow, dot keras dot models. The model that I'm interested is, which can be used probably all of them, is sequential. Okay, next thing that I need is from TensorFlow dot keras dot layers. For layering my sequential with different layers, I need embedding. I would need simple RNN for RNN and dense. I'm going to import the others when I'm writing the code for them, but this is for RNN, so I'm just strictly stick to RNN. So let's go ahead and define the RNN model. Now to do that, first I'm going to say create a variable RNN model equal to give my sequential, and then here give my layers. So my layer says first is embedding as usual, and inside embedding I will put input underscore dim equal to vocab size. So this is my input dimensions. Next, my output dimensions, output underscore dim equal to the standard 128. So that's all I need to create for embedding. Next, I'm going to say simple RNN, and this needs our input 128 and activation. In this particular case, I'll use 10H. That's simple as that. Next, my final output layer is using dense. I'll say 1 comma activation equal to sigmoid. So again, 1 because it's true or false, it's a binary operation. So that's why 1 layer. 1 is the output here as the first parameter. Next, let's go ahead and compile the model. Now to compile the model, I'll say RNN underscore model dot compile, and I need to pass first is the optimizer, and optimizer that I'll use is the same one that I've been using throughout the week, Adam. Loss equal to, since this is binary operation, I'm going to say binary underscore cross entropy, and the metrics that I'm interested is accuracy. So that will take care of that. Now let's go ahead and display the model summary, how it looks like. Always good to see how it looks up. Summary, perfect. Now I'm going to create all the different models, and then we can actually display just for the fun of it. So next thing is LSTM model. So for LSTM, I need to add one more thing here, which is LSTM. That's all I need. The rest of the stuff is there. So I'm going to say define the LSTM model. Say LSTM underscore model equal to sequential, and here I will pass embedding of input underscore dim equal to, it's almost the same as that, so I'm gonna just copy this and paste it. The only thing that changes in here is instead of simple RNN, say LSTM, and I'll pass 128, and activation is also pretty much same, so I could have just kept everything here and just add LSTM in front of it. Now to compile the model, again, copy this. To compile the model, I'll say LSTM model dot compile Adam binary cross entropy accuracy, and finally I'll say LSTM model summary. Now the next one is our GRU model. So for that I'll have to go here and add GRU. So GRU is added. Next I am going to copy this, paste it, call this one GRU model, and then I will compile the GRU model with the same parameters, summary, and only thing that changes is GRU here, and it takes 128 activation 10H. Rest of the stuff is exactly same. So this is my, let's say GRU model. Welcome to week 12, transformers and attention mechanisms. This week, our day 1 will start with introduction to attention mechanisms. Day 2 will be looking at introduction to transformers architecture. Day 3 will cover self-attention and multi-head attention in transformers. Day 4 will be positional encoding and feed-forward networks. Day 5 will be doing a hands-on with pre-trained transformers like BERT and GPT. Day 6 will be looking at advanced transformers, which are BERT variants and GPT-3. And finally, on day 7, we'll do a transformer project, which will be text summarization or translation. So let's get started with week 12.
Welcome to week 12, where we'll be looking mostly on transformers and attention mechanisms. Today, day 1, we'll be looking at introduction to attention mechanisms. So first, let's talk about understanding the limitation of RNNs and the need for attention. So what are the challenges of RNNs? Again, so the RNNs is a topic that we covered last week. So if you are jumping directly into week 12, you would rather want to go over week 11 first. So, to continue again, challenges of RNNs. First, sequential processing. RNNs process data sequentially, making parallelization difficult, which leads to long training times for large data sets. Next, long term dependency problems. The struggle with learning long term relationships in sequences due to vanishing gradient problem. Fixed context vector. The encoder-decoder structure of sec-to-sec models compresses all input information into a single vector, leading to information bottlenecks for long sequences. Now let's look at the role of attention mechanisms. Attention overcomes these limitations by allowing the model to focus on specific parts of the input sequence dynamically during each output generation step. Instead of relying on a single context vector, attention provides a weighted combination of all input tokens relevant to the current output token. Let's talk about the basics of attention mechanisms. First, the core concepts include queries, Q, which represents the current focus of the model. Example can be the current decoder state in sec-to-sec task. Keys, K, encoded representations of the input sequence, and values, V, additional information associated with the keys. Let's talk about attention mechanism itself. The attention score is computed using the dot product of the queries and keys followed by a softmax function to normalize into a probability distribution. The weighted sum of the values forms the context vector. Let's look at the formula. Attention of Q, K, and V equal to softmax of Q of K raised to T divided by square root of dk times V. Next, let's talk about the different types of attention. We have self-attention. The query, key, and value all come from the same input sequence, and it's widely used in transformer models for learning interdependencies within a sequence. Then we have a multi-head attention. Extends self-attention by applying multiple attention mechanisms in parallel. It captures different aspects of relationships in the sequence. The multi-head attention looks something like this, where multi-head of Q, K, and V equal to concatenation of head 1, head 2, all the way to head H, W of O, where each head computes attention with different learned projects of Q, K, and V. Now, with all this information, let's jump into our hands-on exercise, where the objective is to implement a basic attention mechanism using NumPy or PyTorch and visualize its impact on a simple sequence task. So I'm going to do both this time, NumPy and PyTorch. So let's go ahead, and first step is implement a basic attention mechanism using NumPy. So go open a new file, save it as day1 underscore numpy, and here let's start with importing numpy first. Next, I'm gonna write the q, k, and v, which are the define the queries, keys, and values. So for that, let me just write it down here. Define queries, keys, and values. To do that, I'm gonna say queries equal to np dot array, and this I'll give a 2 by 3 matrix 1 comma 0 comma 1, and next row the value says 0 comma 1 comma 1. So this is my 2 by 3 matrix for queries. Next is my keys. For my keys np array, this will be a 3 by 3 matrix 101 1 1 0 and 0 1 1. Okay, this is my 3 by 3 matrix for query. The next one is for values. It's 3 by 2. So I'm gonna copy, actually let's copy this. So this one, as I mentioned, it's values np array equal to, let's call it 10 comma 0 first element, second element I'm going to say 0 comma 10, and the third element I'll call it, since these are keys, I can say 5 by 5. Perfect. So this is my 3 by 2 matrix. Now let's go ahead and compute attention scores for this. Scores equal to np dot queries comma keys dot transformed. So there you go. So this will be giving us queries, which is a 2 by 3 matrix. Okay, I think I misspelled queries here, so oops. There you go. Perfect. Next, I'll go ahead and apply soft max to normalize scores. If you remember the formula that we looked at, if not, you can just always go back a few minutes and you'll see the formula. Softmax of x will be exp underscore x equal to np dot exp x minus np dot max of x comma axis equal to -1 and keep the dimensions equal to true. Again, so this is first get me exp exponential of x, then next I'm going to go ahead and return with exp underscore x divide by exp underscore x dot sum of axis equal to -1 comma keep dims equal to true. Again, if you want to look at this how it works, you can always go back to the formula and see what I'm doing here. Just applying those formula here. Now attention weights is another thing that I need. For that I'm going to say softmax of scores. So this will call the softmax along with the scores and give me my attention weights, which will be a 2 by 3 matrix. Now I'm going to go ahead and compute the weighted sum of values, which will give me all the things that I need. So context equal to np dot, so this is my final formula, which will take attention weights and the values which are passed, which will give me a 2 by 2 matrix. So now let's go ahead and print first the attention weights slash n attention weights, and then I will print the context vector slash n context. Now all the formula is based on the formula that is defined by it, but if like this is the basic formula for basic attention mechanism, but if there is some typo or something, then we can't help it. So let's go ahead and open terminal, and I'm going to say Python, the file is called day1 underscore numpy, run it. And as I mentioned, if there is some typo that we have done, I have to make sure that I don't do any typos. Clear, run it again, and there you go. We have our attention weights based on the inputs that we have given, and this is the context vector which we get. So again, typos, I can't help it, but again the values are here. So this is based on the formulas that we spoke about earlier, and this is using numpy. Now if I want to do the same thing using PyTorch, let's create another file, and I'm going to call it day1 underscore pytorch.py. In here, first let's go ahead and import torch. Next I will go ahead and import torch.nn.functional, where we have all the functions, and there I will get the f. Now first let's go ahead and define queries, values, keys and values. So I'm going to go ahead, copy this, and define keys and values. So for queries, I don't use this, I will have to use, since I want a tensor, torch.tensor, and 1.0, it needs in float 0.0 and 1.0, 0.0, 1.0 and 1.0. This is a 2 by 3 matrix. Next, for keys, I'm going to do the same thing. Torch tensor again, 1.0, 0.0, 1.0, 1.0, 1.0, 0.0, 0.0, 1.0, and 1.0. So this will be a 3 by 3 matrix. Then for values, again, I will say torch dot tensor 10 point 0, 0.0, then we have again 0.0, 10.0, 5.0, and 5.0. So this will get me my queries, values, and keys. Now first step was to compute attention scores. Now to do that, in PyTorch I can just say torch dot mat mul. The formula is to multiply queries and q of t, which is queries and keys dot transform. If you remember, that's what we used here. So same thing, we'll do it in PyTorch using this keys. Okay, perfect. Next thing is to, here in PyTorch we'll have to use softmax, apply softmax to normalize scores. So here we called the softmax function, and then we did this. In PyTorch, I'm going to say attention underscore weights equal to f dot softmax, because PyTorch already has softmax in here, and all I have to do is pass the scores and say dimension equal to -1. It will give me a 2 by 3 matrix of attention weights. Next, I want to say compute weighted sum of values. This I can get the here context equal to torch dot matmul. If you see, what we did here was np dot attention weights and values. So same thing, I'm going to say attention weights and values. So this will give me my 2 by 2 matrix. So now I'm going to go ahead and print again something similar that we did here, attention weights and context vector. And since my variable names are same, I don't have to change anything. Perfect. So this is how you do it in PyTorch. Now let's go ahead and check it out. I'm going to say day1 underscore PyTorch. And there you go. We have a tensor. If you look at the values, it's almost close. It should be the same, almost same to each other. And that's what you get. Now, next thing is, if you want to visualize these attention weights, I can always use import matplotlib.pyplot as plt, and then visualize attention weights. Now to visualize attention weights, I'll say mat show, and I'll give the attention weights here. Next, I am going to say plot dot color bar. Next, I'm going to say plot dot title attention weights and plot dot show. So this will show our plot for attention weights. So let's go ahead and run it. So I'll say python day1 underscore pytorch, and there you go. We have our attention weights displayed in a plot, nicer mat show type of plot, and that's what we see here. So I hope you were able to follow along with this, and if not, if you had any issues or have any questions on implementing any of these, let me know. We went and got our attention calculation. We computed attention weights and context vectors using a simple implementation in both NumPy and in PyTorch. And to summarize, today in day one, we understood the need for attention mechanisms to address RNN limitations, we learned the basics of attention, including queries, keys, and values. We gained practical experience implementing attention mechanisms using both NumPy and PyTorch. Finally, visualized and interpret the role of attention in sequence modeling. So if you had any issues or have any questions, let me know in the messages and I'll get back to you. Day 2. Introduction to Transformers Architecture. Today, let's start with overview of transformer architecture. Now, what is a transformer? A transformer is a neural network architecture introduced in the paper Attention is All You Need, and it relies entirely on the attention mechanism to process sequential data without using recurrence or convolution. It is transformative for NLP tasks like translation, summarization, and text generation. Let's look at the different components of the transformer. We have encoder, which processes the input sequence and generates a contextual representation. It consists of multiple identical layers, each with first self-attention mechanism, which captures dependencies between all input tokens, and feed-forward neural network, which is FFNN, which processes the attention outputs. Next, we have the decoder. It generates the output sequence one token at a time, and it consists of multiple identical layers, each with a masked self-attention mechanism which prevents the decoder from attending to future tokens, and encoder-decoder attention which attends to encoder outputs, and we have the feed-forward neural network. Now the workflow for this is input sequence comes in and gets through encoder, next to the context vectors, next to a decoder, and finally you get the output sequence. Now let's go over the detailed breakdown of the transformer model layers. First, we have the self-attention layer, which captures relationships between all tokens in the input sequence. It then computes the importance of each token to all other tokens. Next, we have the position encoding. Since transformers lack recurrence, positional encoding injects information about the token order into the model. Next, we have the feed-forward neural network. It applies a position-wise FFNN to the outputs of the attention layer, and nonlinear transformation enhances the representation. Layer normalization stabilizes training by normalizing inputs within each layer. Finally, the multi-head attention. This combines multiple self-attention mechanisms to learn various aspects of the relationships within the sequence. Now let's look at some of the key differences between transformers and RNNs. As per the aspect of parallelization goes, transformers are fully parallelizable, faster training. RNN is sequential processing limits parallelization. Next, as per long-term dependencies, transformers handles long dependencies via attention, whereas RNN struggles with long dependencies. For position information, transformers uses positional encodings and RNNs implicitly encode its position. For architecture, transformers are built on attention mechanisms, so no recurrence, whereas RNNs have sequential processing through hidden states. Next, with all this information, let's jump into our hands-on exercise. The objective here is to visualize the architecture of a transformer model and set up an environment for working with transformers using PyTorch and TensorFlow. So let's get started, and first we'll visualize the transformer architecture. So this is a fun project. You might need some libraries installed. I already have things installed. I will keep this open to my day 2 folder, and here first let's go ahead and add the visualization code. So I'm going to call this visualization day 2. It's okay, the spelling mistake, I can't run away from that. So first I'm going to say TensorFlow dot keras dot utils. I will import something called as plot model. Now this needs a bunch of additional libraries, so if you get any warnings or errors, it will probably tell you what you need to install. Next, I'm going to say TensorFlow dot keras dot models. I will import from here model. Next, from TensorFlow dot keras dot layers, I will import input dense and layer normalization and add and multi head attention. Perfect. So I have everything that I need here. Now with this, first let's define a simplified transformer block. So for that, let me call out what I'm doing. Define a simplified transformer encoder block. Okay, so let's start with the function. I'll call it transformer underscore encoder. I'll pass it input dimensions, which is input dim, and then I'll pass it number of heads that I want, and then I'll pass it the ff dim dimension, so feed forward dimension. So that's what I've passed. Now here, first I'll say input will be input of shape equal to none and input underscore dim. So this will be displayed as the input dimensional. Next, let's say for a multi head self attention, I'm going to first start with a variable called as, I'll call it attention output, which will be equal to multi head attention number of heads equal to number of heads that we got from the parameters. Next, I'm going to say key underscore, and the parameter needs is key dimensions, which I will pass it as input dimension. So that's the start of it, and then I'll say inputs comma inputs. So this, I think I named this as input instead of inputs. So those are my inputs. So that is what I passed there. So that's my first attention output. Next, attention output, I will go and add another layer. In this case, I'm going to add inputs. This is my residual connection, so that's why I'm using add inputs and attention underscore output in the previous one. So this will create my residual connection, and then finally again I'll say attention output equal to layer normalization, and inside this I will pass the attention output. So we have our multi-head self-attention. Once we have that, the next thing that I need is the feed forward neural network. So feed forward neural network. Now for that, I will first create ff output parameter, and first layer is the dense. We'll pass the ff underscore dimension that we have passed. Next, I'll use activation equal to relu, and I'll pass bandwidth of attention output. Next, I need another layer, ff output equal to, I'll say dense, and then to this I'll pass input dim of ff output. Perfect. So this will create my ff output. Next, I need outputs, final outputs equal to, I'll say add, what layers am I adding? First the attention output from above, and then I need ff output from here, from the line number 15 above. So this will be my residual connection again. And now finally outputs equal to layer normalization, and I have to normalize everything for outputs. There you go. So this can return back now finally model with inputs and outputs. Perfect. So this will have my entire transformer encoder block inside it. Now if I want to plot it or visualize it, so I'm going to say create and visualize that simplified transformer, and so a sample transformer encoder block. So what I'm going to do in this particular case here is, first let me fix this, create the encoder block. Now to create the encoder block, I'll have to call that function. So I'm going to say transformer encoder. I'll pass some values. I'll say input dim equal to, let's say, 64 dimensions. I need number of heads equal to 8. And then I'll say feed forward dimensions of equal to 128. And then I can plot this model using plot model function that we have imported. And I'll say, I'll pass it, it needs the encoder block. I'll say show the shape. There's a parameter called as show shapes, and that I'll say true. And then to where do I want to save it? I'll say to a file called as transformer underscore encoder.png. So kind of when I save this and run it, it will create an image and save it on my folder. So that's why I have also the folder open here. This is my app. This is my code here, code file that I have here, and now I have nothing over there. So I'm going to say Python visualization underscore day2, run it. It's going to run through that code. If there's no typos, hopefully everything will be good, and create an image right here with the encoder transformation, with the transformer encoder block definition. And there you go. It took a minute or so, and then finally we have the visualize transformer encoder image here. I can open it, and as you can see, it shows the input layer with the output size of none 64. Then we have multi-head attention, and we have added layer normalization, dense we've add, finally added these together, and layer normalization. Based on the code that we have written here, it has created a visualization for me from that. So I hope you are able to follow along, because our next step is to set up an environment for transformers in PyTorch. For this, I'll have to go to my terminal, and first let's clear this out, and first install torch vision and transformers. If you have not installed already, these are the things that you need to set up the environment. So I'm going to run this, and it will run very quickly because I've already installed most of it. And then let's write a code to see if it works. I'm going to create a new file, save as day2 underscore exercise 1.py, and here first from transformers I am going to import bird tokenizer and bird model. Now these are some of the pre-trained models, so I'm going to say load a pre-trained bird tokenizer and model. To do that, first let's get the tokenizer equal to bird tokenizer that we have imported from underscore pre-trained, and the one that I'm interested in is bird dash base dash uncased. Okay, so that's my tokenizer. Next I'm going to say model equal to bird model. From that I'll say from underscore pre-trained, I want to get the pre-trained model, which is bird dash base dash uncased. So this will give me my tokenizer and model. Now let's go ahead and tokenize a sample input. So I'm going to say tokenize a sample input, and this will be text equal to transformers are powerful models for NLP tasks. That's what I'll say. Now I have that. Now I'm going to create an input equal to tokenizer, tokenize this input, where I'll pass this text that I've created, and I'll say return tensors equal to PyTorch tensors. So I can specify which one I want. So I'm saying return me PyTorch tensors, and then I will pass the input through the model. And for that I'll create an outputs which will say model. I'll call the model function, and to that I'll give the inputs. There you go. And now I can say print hidden states shape. You can also go and visualize these things, but I don't want to go that far. You already saw how to visualize. I'll just say last hidden state dot shape. So just give me a shape of the last hidden state from the outputs. So that's what I'm doing here. I can go to my terminal and say Python, and this file is called day2 underscore exercise 1. Run it. I've not used most of the functionalities here because I'm just doing tokenizer model. So even if it gives me warning, that's normal. And there you go. We have hidden state shape torch dot size 110,768. So this is the shape of the last hidden state, and this is how we implement in PyTorch. Now, to do it in TensorFlow, first make sure that you have the TensorFlow installed. So we have already done a lot of projects in the previous week, so you should have it. So I'm going to say pip install and TensorFlow. I assume you have the TensorFlow installed. If not, okay, I think I spelled it wrong. TensorFlow, and there you go. It will have my TensorFlow installed. If you don't, then just go ahead. It will take some time to install. I'm going to call this day2 underscore exercise 2.py. In this case, since we need from TensorFlow, so I'm going to say from transformers, I want to import tf BERT model and BERT tokenizer. So I'm going to go ahead and take much of the same code from here, and I need the BERT tokenizer. I don't need the BERT model. I need TensorFlow BERT model. Now first is pre-trained BERT model and tokenizer. So I'm going to say tokenizer BERT model from pre-trained. This is what I need, and this is for TensorFlow BERT model from pre-trained BERT base uncaged. Next I'm going to say tokenize the input, transform, same stuff I'm going to give tokenizer. Now this is not PyTorch. I'm going to get TensorFlow, so I'm going to say change this to TF. Pass the inputs, outputs equal to model of inputs, hidden sample states, output last hidden state dot shape. So save this and go ahead and run it. Python. It was called day2 underscore exercise 2.py. Now again, as I mentioned, if it gives me some warnings because I'm not using a lot of things inside these, so that's understandable. And as I said, some weights of PyTorch model were not used because I'm not using PyTorch here. This is expected if you are initializing tf-BERT, and it tells you why it does that. And anyway, at the end, this is what I'm interested in. Hidden state shapes 110,760, almost same as the PyTorch one, and that's what we get from here. And that's now your environment is ready for both coding in TensorFlow and PyTorch. So I hope you were able to follow along. If you had any issues implementing this, let me know right now, because we'll be using this quite a lot throughout this week, and it's better to get clarity, or if you can search and see what the issue is, that can also help you into moving into the next steps. But if you had any issues and you want some guidance, let me know in messages and I'll get back to you. So just to summarize, today we understood the structure and components of transformer models. We went over and learned the differences between transformers and RNNs. We gained experience visualizing and setting up transformers in popular frameworks, and we built foundational knowledge for advanced transformer models like BERT, GPT, and more. So again, if you have any questions or had any issues, let me know and I'll get back to you. Day 3. Self-attention and multi-head attention in transformers. So let's start today with self-attention mechanism. Now, what is self-attention? Self-attention allows a model to dynamically focus on different parts of an input sequence when encoding a token. It captures dependencies across all tokens in a sequence, enabling context-aware representations. The steps involved in self-attention includes first, compute attention scores, where you calculate the dot products between the query Q and key K vectors for all tokens. Then you scale by the square root of the key dimension dk to stabilize these gradients. Then you apply the softmax function to convert scores into probabilities. And weight values. Use the attention scores to compute a weighted sum of value v vectors. And that's what we did in the last one, but we're going to go more focused today in the hands-on exercise. So remember these, and also the formula. Attention of qkv equal to softmax of qk raised to t divided by square root of dk times v. Next, we have multi-head attention. What is multi-head attention? Instead of a single attention mechanism, multi-head attention applies several attention mechanisms in parallel, and each attention head focuses on different aspects of the sequence. The steps involved here is linear projections first, where you project Q, K, and V into multiple subspaces using learned weight matrices. Then you apply self-attention. Perform self-attention for each head independently. Then you concatenate outputs. Combine outputs from all the heads. And then final linear projection. Project concatenated outputs back into the original dimension. So multi-head QKV is equal to concatenation of each and every head W of O. Now, let's talk about the applications of multi-head attention in NLP. First, machine translation. It captures dependencies across languages for better translations. Text summarization. Identify some key phrases to generate concise summaries. And named entity recognition. Focuses on contextual clues to detect entities in the text. With all this in mind, let's jump into our hands-on exercise, and the objective here is to implement a simplified self-attention and multi-head attention mechanisms and visualize their effects on text sequences. Now, if you want to implement this, you have to remember these formulas that we did in the last few slides. So if you want to cross-reference, always cross-reference or take a screenshot of it, and then you can look at how to implement the code. So first step is to implementing the self-attention mechanism. For this, I'm going to go ahead and start with a new file, save it as day3 underscore exercise, and save it here. So first I'm going to get import numpy as np. Let's go ahead and define query, key, and value matrices. For this case, what I'm going to do is I'm going to create a function, say generate data, and this will take our sequence length and embedding dimension. These are the inputs for this generating data, and here I'm going to say np.random.seed of 42. The reason I'm setting this again is to make sure that I get the same random data every time I run this. And then I'll say return np.random.rand sequence length and embed dim, so dimensions of how you want the data to be. So now let's go ahead and create a sequence length of 4 for this. Then I'm going to say embedding dimension equal to 3. So this is what I'll pass to the generate data. Now let's go ahead and get the query where, sorry, the Q parameter or Q variable, where I'll say generate data and pass it the sequence length and embedding dimension that I've created above. For key, I'm going to do something similar. Generate data, the sequence length and embedding dim. And for value, I'm going to do the same thing. Generate data and pass the 2 parameters, sequence length and embedding dim. So we'll get the Q, K, and V parameters now. Now next step is to go ahead and compute the attention scores. Okay, I'll move this up. To compute the attention scores, we can say scores. If you look at the formula, that is pretty much multiplication of 2 matrices. One is query and key transform, so that is key dot t. So that divide by np dot square root of embedding dim. Now, where do I get this from? Again, if you go back to our slide on single attention mechanism, here soft q k transform divide by square root of d of k. So that's what we are doing here. Our next step is to apply softmax to normalize the scores. So that's what is softmax of this. So for that, I am going to say create a function. First of all, softmax. Now this is not available with NumPy, but with Torch it was. So I'm gonna create that softmax function. Exp of x equal to np dot exp of x minus np dot max of x comma axis x comma axis equal to -1. I have to set up. Next, I need the dimensions to keep dims equal to true. So that's my first. Next, this will return the softmax of whatever parameter that we passed by expx divide by expx dot sum of, I will pass axis equal to -1 and keep dims equal to true. Perfect. So this will give me my softmax. So I need to get the attention underscore weights equal to softmax of scores that we have. So this line number 22 pretty much does this softmax of the scores that we have. The next step, as you can see here, I need the multiplication of this softmax times v, which is the value. So for that, I am going to say compute the context vector. So that is context equal to np dot multiplication of the two matrices, which is attention weights, whatever I got above, and value. So this will give the context, which is attention q kv softmax of this times v. So I have that here. So let's go ahead and print attention weights on the data that is generated. I'm going to say attention weights. Right, so I have that. Next, I can also print the context text vector that is comma context. Right, so I have my attention weight and context printed out. I can go and open my terminal, and here I can say Python day 3, and there you go. We have our attention weights and we have context vector based on the random array that is created, and we'll get our context vector here. Now, if you want to implement a multi-head attention mechanism, and I want to use PyTorch this time, so I can just keep on writing here. I can say import torch, and I will import torch dot nn, and nn also I need the mf, so that is coming from import torch dot nn dot functional. I will import import as f. You can directly use functional. Now that I have that, let's create a multi-head attention class. So I'm going to call it multi-head attention. Now if you remember, our multi-head attention looks like this, multi-head of all the concatenation of all the heads. So for that, create this pass the module as usual. I will go ahead and initialize, call the initializer, create the initializer method. I will pass in here self and embed underscore dim, and I will pass number of heads that I want, and then I'll call the super with my multi-head attention and self dot underscore init, and call that. So I'm calling the super function here. Next, I will go ahead and say self dot embed underscore dim equal to whatever was passed to me. So embed dim self dot number of heads is equal to number of heads that was passed. Next, self dot head underscore dim equal to, from this embed dim slash number of heads. So that will give me the head dimension. Now let's go ahead and assert embed underscore dim mod number of heads equal to 0, then I will give a message saying, oops, embedding dimension must be divisible by number of heads or else it's invalid. So that's what I'm going to specify here. So once that is done, our next step is to say self dot query. So let's get the query first, the q parameter, nn dot linear embed dim comma embed dim. So that's the first step. Next, for the key, is equal to nn dot linear, and that is embed dim comma embed dim. Perfect. Next, our value self dot value equal to nn dot linear, oops, not this, linear, pass it, same thing, embed dim comma embed dim. And then finally self dot output layer equal to nn dot linear embed dim comma embed dim. So that's good. So now let's go ahead and create the forward function, which will take self and x as input parameters as usual. And here let's first set the batch size. So I say batch underscore size, that will be always whatever the x size is, x dot size of 0. Next, let's go ahead and do the linear projections. So to do that, I'm going to say q equal to self dot query, pass it the value of x dot view. I'll have to pass the batch size and -1 for the second parameter. So next, I'm going to say self dot number of, I'll pass the number of heads it has, and then I'll pass self dot head dim, and then I'll say transpose this 1 comma 2. That's the parameters. Okay, so that's our first, that will give us the q. Same thing I'll have to do for k and v. So I'm going to go ahead, copy this, and I'll say k and v. So self dot, this time not query but key of x dot view batch size -1 self num, so all stay same, self dot value for v dot view. So this kind of gets us q, k and v. Now next step is to compute the attention scores. To do that, I'm going to say scores equal to torch dot mat multiplication or matrix multiplication, where I'll pass the value of q, k dot transpose, if you remember the methods, k transpose -2 comma -1, and then divide by np dot square root of self dot head of head dimension. So if you don't remember, you can go back to the formula and look at it. But again, I'm going to go ahead and calculate the attention weights equal to f dot soft max, pass the scores, and it was a scores comma dimension of -1. Perfect. So this will give me my attention weights. Now let's go ahead and compute the context. To get the context, I'm going to say context equal to torch dot mat mul and get the attention weights comma v dot transpose 1 comma 2 comma dot contiguous dot view batch size comma -1 comma self dot embed dim. So this will give me, let's go all the way, context for the entire thing. And then now let's go ahead and return our self dot out and pass the context and attention weights. So that's my forward function. Now let's take some sample input and run through this. So I am going to say sample input. I will say sequence length equal to 4, or I also give embed dim, both of them together in the same line. My sequence length is 4, my embed dimension is 8, and I'm going to say x equal to torch dot random 1 comma sequence length and embed dim. Perfect. And now let's go ahead and instantiate and test this. To do that, first I want, let's say, MHA equal to multi head attention. MHA stands for multi head attention. The embed dim, and I'll need number of heads. I'll specify number of heads as 2 for this. Context comma attention weights, WEIG attention weights, or I'm not going to use the same parameter. Therefore, attention weights equal to MHA of X. So I'm going to pass this MHA of X, which multi-head attention, which will call this class, pass it and give me here context and attention weights outside. So that's good. So I have everything that I need. Now let's go ahead and print attention weights /n and pass it the attention weights. I don't know why I called it this. I'll remove the E, and then next I'll say print context vector equal to /n of context. Perfect. So I have my entire code. I'm going to go ahead and mute these two guys. I don't need them, but I'll show this thing. So I'm going to go ahead and run, first clear it out, run my day 3 exercise 2. I think I have some mat mul instead of I'll use as usual. I've done some typos. Mat mul, clear this out, run it again. One more transpose is spelled wrong. Let's go ahead and try this. And there you go, we have our attention weights and context vector. Now if you want to visualize this attention weights, I can always go ahead and import matplotlib dot pyplot as plt, and then inside this, let's say I want to visualize attention weights for a single head instead of multiple heads. I just want to see for single head. Okay, so for that I'll say plot dot mat show, and this I'll pass the attention weights of the single head. So I'm going to say 0, 0, and I'll say dot detach dot numpy, so I can get my numpy data here. CMap equal to, I will use a colorful one, so I'm going to say viridis is what I'm going to use for this display. I'm going to say plot dot color bar is my display, and then I'll say plot dot title. I will give it as attention weights for head 1. I picked the first head, that's why. You can kind of change that and see whichever head you want to see, because we have 2 heads right now only. That's what we have specified, but I'm looking at the first head. So I'm going to go ahead, clear this out, run it again, and there you go. We have our attention weights head 1 figure here, plot for that, so you can visualize that and see the differences. So to summarize, today we understood the mechanisms of self-attention and its role in sequence modeling. We learned how multi-head attention extends self-attention's power, and we gained practical experience implementing and visualizing these attention mechanisms. We understood applications of attention in modern NLP tasks. So if you have any questions or had any issues while implementing this, let me know in the messages and I'll get back to you. Day 4. Positional encoding and feed-forward networks. So let's jump into understanding the role of positional encoding in transformers. Now, why positional encoding? Unlike RNNs, transformers do not
process sequences sequentially. They process all tokens in parallel. Now, transformers lack inherent knowledge of token positions, which is crucial for tasks like translation or sequence modeling. What is positional encoding? Positional encoding introduces information about the order of tokens in a sequence. It allows the model to differentiate between identical tokens in different positions. Let's look at mathematical foundation and implementation of positional encoding. So first, let's look at sinusoidal positional encoding. It encodes positional information using sine and cosine functions. The formula for positional encoding is PE of pos or position of 2i equal to sine of position divided by 10,000 raised to 2i divided by d, and PE of position of 2i plus 1 equal to cosine of position divided by 10,000 of 2i divided by d, where POS is position of the token in the sequence, I is the index of the embedding dimension, and d is the total embedding dimension. Now, why use sinusoidal functions? It provides unique encoding for each position and allows generalization to longer sequences not seen during training. Let's talk about the feed forward network next. What is a feed forward network? FFNs are fully connected layers applied to each token independently and identically within a transformer layer. It adds non-linear transformation to the output of the attention mechanism. What is its role in transformers? It captures token specific transformations and enhances representational capacity. Let's talk about the structure. We have first the linear transformation, then we have non-linear activation, which is we use ReLU, and another linear transformation. So FFN x equal to ReLU x of W1 plus B1 times W2 plus B2. With this in mind, let's jump into our hands-on exercise where the objective is to implement positional encoding and integrate it with basic transformer model. We will also experiment with different positional encoding methods and observe the effects. So let's go ahead and start with a new project. I'm going to save it as day 4 underscore exercise. And first, we're going to go and implement positional encoding. So for that, I'm going to say import numpy as np. Next, I'm going to import, since we want to display the data, I'm going to use matplotlib.pyplot as plt. Next, I'm going to go ahead and define positional encoding function. So to do that, I'll create a function called as positional encoding, and it takes input as sequence length and embed dimension. Now inside this function, I will first get the position, which is POS equal to np dot range, and pass the sequence length to it along with the dimensions from np dot new axis. So that will give me my position. Next, I'm going to say I equal to np dot range and pass it embed dimension. For this, I'll use from np dot new axis to end. So next, I'll get the angle rates. So angle underscore rates, which is from the definition, if you remember the formula, 1 divided by np dot power. So I mentioned 10,000. Make sure we have all the zeros, comma 2 times. Let's make sure they're visible. I slash slash 2. So I have that, and divide by np dot float 32 of embed dimension. So as per the formula, this will give me the angle rates. Now I'm going to say angle
rads equal to position times angle rates. So that will give me my angle rads. And next I'm going to go ahead and apply sine to even indices and cosine to odd indices. So to start with, let's say POS underscore encoding equal to NP of zeros. So I'll start with the zeros, and the things that I want in the diagonals are angle rads dot shape. So that will create my zeros matrix. Next I'm going to say pos of encoding for colon 0 colon 2. For this I will say NP. So these are the even indices. I'm going to say NP dot sine of angle rads from colon 2 2. So this will just take the even indices. Now for odd indices, I'm going to use cosine. So I'm going to say position encoding, in this case 1 to 2 NP dot cos angle rads 1 2. So this will use the odd indices, and then I will return my position underscore encoding back. So this will give me my positional encoding. Next step is to generate the positional encoding, calling the function above. So from that I can see that I need sequence length that we defined as parameter. So I need sequence length, and then sequence length I need embed dimension. I'm going to use embed dimension of 16 this time, and I'll say position encoding is equal to, call the function positional encoding, and it needs sequence length and it needs embed dim. So I'll pass those two parameters. Perfect. So now that I have that, next thing that I need to do is let's visualize this positional encoding. So I'm going to go ahead, say visualize positional encoding using matplotlib. So I'm going to say plot dot figure. Let's create a figure size of 10,6. I have to put it inside parenthesis. Perfect. Next I'm going to say the plot that I want to see is a p color mesh. So p color mesh, use a new one every time we do something, so we can play around with different ones. Pos encoding is what our positional encoding is what I'm going to pass. I'm going to use cmap, so same colors as what we used yesterday. Viridis is what I'm going to use. Next I am going to create the color bar, so call color bar function. Next I'm going to give a title to this. For the title I'll say positional encoding, and then I will, oops, not title, title. Then I'll say plot dot x label. For x label it's using our embedding dimension, so that's what I'll say. And for y label we are using position. So that's good. Now let's go ahead and say plot dot show. See how it looks like. It should be a little bit weird as compared to what you've seen before, because of the way positional encoding works over the entire matrix. So I'm going to say Python day 4, and there you go. We have our positional encoding. Oops, probably. And it goes from here 0 to 50 and 0 to 16 here. And as I said, it kind of goes more solid as in when it goes towards right, start from this, and that's how the embedding dimension works. Perfect. So we have this working, this kind of we got implemented positional encoding. Next thing what we want to do is integrate the positional encoding with a transformer model. So I'm going to close this and go ahead for step 2, where we want to integrate positional encoding with a transformer model. I will use PyTorch. So I'll say import torch. Next I will import torch.nn as an n, and then I'm going to create a class again for transformer with positional encoding, just to make it clear what we are doing here. And then, as you know, the parameters are nn.module can do that. Next, I need to create the initializer function. So as usual, call initializer function. This will need, as you know, the basic ones, which is our embed underscore dim. We need the sequence underscore length. We need the number of heads that we want, and we want the ff dim, something that we did in yesterday's video. So same thing I'll do here. Again, I will first go ahead and call the super with the name of this class and self, and then make sure that I call its initializer method. Okay, so that's called. Now first step is embedding, equal to nn dot embedding, and I'll pass it sequence underscore length, and I'll pass embed underscore dim. So these are two parameters that it needs. Next, I want to call this positional encoding. So I'm going to say self dot positional underscore encoding equal to, this is nn dot parameter. That's what I use, parameter, and to this I'll pass torch dot tensor, and the parameter that I pass inside is the positional encoding function that I've created above, and I'll pass the sequential. It needs two parameters, seq length and embed dim. So I'll pass those, and it needs the d type at the end. D type. For d type, I will pass torch dot float 32. That's the one that we need. Perfect. So that kind of takes care of our positional encoding. Next, we need the multi-head attention. So I'm going to say self dot multi-head underscore attention. For that, I'll use the nn dot multi-head attention, and that needs embedding dim. As you can see, the parameters embedding dim and number of heads. Those are the two things that it needs. I'll pass that. Rest of the stuff we can leave as it is. Next, self dot fn ffn equal to I'll say nn dot sequential, and in here I'll create a layer of nn dot linear. First one, I'll pass embed dim and ff dim. Next, I will create the ReLU. As I mentioned, I'll say ReLU. That's the activation that I want to use. And next, I'll end with another linear layer, nn dot linear. And this time, it needs ff dim and embed dim. Perfect. So as per our definition, this takes care of all of them. Now finally, let's normalize. So I'm going to say norm1 equal to nn dot layer norm, and pass it embed dim, and then I'll create another one, norm2, again nn dot layer norm embed dim. So this will normalize our layers. And then finally, let's go ahead and create the forward function, which needs self and x. Now this one, first we'll have to do is add the positional encoding to embeddings. So I'll probably say that add positional encoding to embeddings. For that, I'll specify, let's move it up. I'll say x equal to self dot embedding, pass it x plus self dot positional encoding. So that will take care of that. Next, we have self attention. So for that, I'll say attention underscore output, comma. I don't care about the second parameter, so I'll just put an under it underscore, and I'll say self dot multi-head attention, and I'll pass x, x, and x. Then I'll say x equal to self dot norm1 and pass x plus attention output from above. So that will take care of our self attention. Next, finally, we need the feed forward network. For that, I will have to say ffn underscore output, create a variable, and pass for self dot ffn from above, and pass it the parameter x. Next, I'll say x equal to self dot, I'll normalize with norm 2 this time, and I'll say x plus fn output. Perfect. Now I can return the value of x back. Perfect. So this will take care of everything. Next, let's go ahead and define the model parameters. So say define the model parameters. So first I'll say embed underscore dim equal to, I'll give 16 for the dimensions. Next, sequence length I will set as 50. Next, I will say number of heads equal to 4. Next, I'll say ff dimension, I will set that to 64. And now I can create the model, and inside my model I'll call the model name, class name. I'll pass the embed dim, I'll pass the sequence length, and I'll pass number of heads, and then finally I'll pass ffdim. So these are the parameters that we need passed, and then I can go ahead and print the model. Perfect. So let's go and check it out. It will probably also print the previous things. Also, I've defined these here, but it will change based on what we have overwritten here. Go ahead, clear it out, run it. And there you go. We see our same thing from the first exercise. And then we have our transformer with positional encoding, where you see the embedding, you see the multi-head attention. You can always print it out from as per day 1 that we did this week. You can also print it in an image, and it says, and you can see all the different layers over here. Multi-head attention, then we have FFN, then normal 1, normalization 2. So you see everything over here. Our next after this is to work on experiment with different positional encoding method that I mentioned. So another alternate positional encoding we can use is learnable positional encoding, which where we use the trainable parameters instead of sinusoidal functions, and this is suitable for data sets with specific sequence patterns. So I'm just going to write it down here, but we don't have to actually print it. So first I'll say learnable positional encoding. For that, I'll create a class learnable positional encoding, and then nn dot module is what we module what we pass in there. And then let's create our initializer method. It needs, as usual, self will give sequence underscore length, and we need the dimensions, which is embedding dimensions, embed underscore dimension. Now in here, first I'll call the super with our learnable encoding, and self dot underscore init, call the function. So once that is called, next step is I'm going to say self dot positional underscore encoding. In this particular case, I'm going to say nn dot parameter of torch dot zeros. I'm going to do everything inside here so it's not separately outside. Sequence underscore length and embed dimension. So that's what I pass here. This is all that we do for this, and then I can create the forward function, pass self and x, and this forward function I'll say return, since it was only one, I'll say x plus self dot positional encoding is what I'll pass back. And if you want to create it, I can say learnable positional encoding equal to, you call it by saying learnable positional encoding, and then we can pass the sequence length and embedding dimension. And if you want to print it, you can go ahead and print the learnable e out. So again, I don't have to run this because this has just only one layer which will be displaying the learnable positional encoding, but you can go ahead and play with it and check it out. So I hope you are able to follow along and go through this. If you have any questions on this, have any doubts, or had issues implementing this, let me know in the messages and I'll get back to you. So just to summarize, today we understood the necessity of positional encoding in transformers, learned the mathematical foundation of sinusoidal position encoding, gained practical experience implementing and visualizing positional encoding, and finally understood the role of feed-forward networks in transformer layers. If you have any questions or any issues, let me know and I'll get back to you. Day 5. Hands-on with pre-trained transformers like BERT and GPT. Today, let's start with introduction to BERT and GPT, some of the very popular ones that you've probably heard. Now, what is BERT? BERT also stands for Bidirectional Encoder Representations from Transformers. It's developed by Google AI. It processes input sequences bidirectionally, enabling it to capture context from both directions. It's pre-trained on tasks like masked language modeling, MLM, and next sentence prediction or NSP. Some of the key features of BERT include it's bidirectional, which understands context from both left and right sides of a word. It's transformer encoded based, which means it's optimized for understanding input text. And applications are sentiment analysis, named entity recognition, and question answering. Now, what is GPT? GPT, which stands for Generative Pre-trained Transformer, is developed by OpenAI. It processes input sequences unidirectionally, left to right, focusing on generative tasks. It's pre-trained using causal language modeling. Some of the key features of GPT include its unidirectional, processes text from left to right, focusing on text generation. Transformer decoder based, it's optimized for generating coherent text, and applications include text generation, chatbots, and summarization. Now let's talk about some of the key differences between BERT and GPT. As per the aspect of architecture, BERT is transformer encoded, whereas GPT is transformer decoded. Training objective is MLM and NSP, whereas for GPT, it's causal language modeling. Directionality for BERT is bidirectional and GPT is unidirectional. Use cases for BERT is understanding task example classification, whereas for GPT is generative task, which is text generation. And if you've used ChatGPT, you know what I'm talking about. Now let's go ahead with fine tuning pre-trained models for downstream tasks. Now, why fine tune? Pre-trained models are trained on large generic data sets. Fine tuning adapts them to specific tasks like sentiment analysis or classification. Now, what are the different steps to fine tune? First, you load a pre trained model using libraries like Hugging Face to load a pre trained BERT or GPT model. Then you prepare the dataset, format the dataset for a specific task, example tokenization for text classification, and then train and evaluate. You fine tune the model using task specific data. So let's try all of this in a hands-on exercise where the objective is to use Hugging Face Transformers library to fine-tune a pre-trained BERT and GPT model for a text classification task. Now, if you don't have not heard about Hugging Face, just Google it, or you can just go to huggingface.co and you'll probably see what it is with all the data sets and models that it has available for you. So first, let's go ahead and create a new file. I'm going to create a Python file, save it as day 5 underscore exercise. And here I am going to first start with installing stuff. So I'm going to open my terminal. And first thing is to install Hugging Face Transformers, you have to say pip install transformers. And I also need the data sets from there. So once you install these, I mean, it will be pretty fast next time. So that's why it's fast for me because I already have it available. Once you have that, now let's import these libraries. Now from transformers, I can import first is auto tokenizer. As the name says, it's used for tokenizing. Next, I'm going to use auto model sequence classification. There you go. Next, I want the trainer, which will train my models. And I need training arguments where I can pass the arguments for my trainer. And next thing I want to do is I want data sets. So I'm going to say from data sets import load dataset, load underscore dataset. That's what I need. So I have everything that I need. So this will install and import the necessary libraries. Now next step is to load and pre-process the dataset. Now we'll use the same IMDb movie reviews dataset that we used before for sentiment classification. So first, I'm going to say load the data set. Now to load the data set, I'm going to say data set equal to load data set, and I specify which data set I want, db. So this will get me my data set. Next, I'm going to create my tokenizer. To create my tokenizer, I will call the auto tokenizer that I have imported, and there I'll say from pre-trained I want to use bird tokenizer, bird base uncased. That's what I want to get. Next, let's go ahead and tokenize the data set. To do that, I will create a function called as tokenize underscore function, and I'll pass it some examples as argument, and this will return to me tokenizer examples text that it will take, and it will, if you want to pad it, I'll say padding equal to max underscore length and truncation equal to true. If it's more than max length, just truncate the text that is passed to here. Next, I want to get my tokenized data set, so I'm going to say tokenized underscore data sets equal to data set. From my data set, I'll say map tokenize. I'll pass the tokenized function to this, and I'll say batched equal to true. So this will call my tokenized function right here, and then pass the data set from there to it, and then in batched mode it will send that and give me my tokenized data set back. Now next step is to prepare data for training. To do that, I'm going to say tokenized data sets equal to tokenized data set from above. I will remove particular columns, for example text. Next, I will say from tokenized data sets dot rename column. This is some example of what all you can do. You can remove columns, you can rename columns. Now we have labels in here. I want to, or label in here, I want to rename it. So for example, I want to rename it to labels, just because I can. Next, I'm going to say tokenized data set dot set format. The format for this, I want to format as my torch. So torch format. Next, I can say train data set equal to tokenized data sets with training parameters, and for test I want to use data set which is inside test. So when you do the above parts, it will automatically give you some tokenized data set for training and for testing automatically. You don't have to do much. So as you can see, next step is to load the pre-trained model. So to do that, I'm going to say model equal to auto model for sequential from pre-trained. I'm going to pick the model which is bird base uncased. So bird dash base dash uncased. Now inside Hugging Face, you can go and look at all these different things about this model. It will have all the parameters, all the different things that you can do with it. Number of labels that I want to pass is 2, so that's my model is available. Now next is, let's define the training arguments. For training arguments, I'll create a training args variable, and I can call the training arguments. This is where I can pass things like, what is my output directory where I want the training data to be, the evaluation strategy. I can give the learning rate, all those things here. So as you can see here, all the parameters are listed right here. So first is output directory. I'll say output directory. For that, I will save in my local folder which I am running this file, in a results folder. That's where I'll save. Next thing I can do is give my eval strategy. So I'll say eval strategy or evaluation strategy equal to epoch, my favorite ones. And then I'll say learning rate. I can give a learning rate of 2 epsilon raised to minus 5. That's what I can set as my learning rate. And then I can say per device train batch size, I can set that to 8. Next, I can say per device eval batch size equal to my evaluation batch size and training batch size, set both to 8. Next, I'm going to say number of train epochs, that I can set it to 3. It's going a lot of time for this to happen because of the data set that we have. Weight decay, I'm going to say 0.01. Next, I can say where do I want the logging. I say logging directory equal to dot slash logs. Next, I'm going to say logging steps, how many, so it will print out these to you. So I'm going to say every 10 I want to log it out and also save. And then save steps equal to 500. So that's what I want to save in the logs. So that is my training arguments. Once that is done, next step is to train the model. So train the model, I'm going to say trainer equal to, call the trainer function that we have initialized or imported, and to this it needs model, which we have model, so I'll pass that. Next parameter it needs is, what are the different arguments, the training arguments. I'll pass the training argument that I've created above, which is this one. As you can see, training argument, that's what I've passed. Next parameter is training data set, that I already have created above that, which is training data set. Train data set is what I called it. Evaluation data set, I can set that as test data set. Now if you want to see a better clearly this, I can just move them to the next line so it's clear and visible. Okay, what else do I need to pass here? So I've passed my evaluation data set. Next, my tokenizer, or also called as processing underscore class. It was used to call tokenizer before, so if you're familiar with that, that's what. So if you see that, it still shows up over there, tokenizer. So that's called processing class in the latest version. If you give I think tokenizer, so if you give tokenizer equal tokenizer, it might give you a warning saying that it is deprecated and you would want to change it. You can try that out. And then I'll say train dot train. Now this will take forever to train because of the data set that we are passing. So I am going to go and do the next steps too. So next is evaluate the model. To evaluate the model, I'm going to say results equal to trainer dot evaluate. I can just call that function. That's it. That will evaluate it, and that I can print evaluation results from my results above. Perfect. So that will give me my evaluation results. Next, if you want to experiment the same thing with the GPT, I can probably write the code here. So I'll probably say experiment with GPT, because one is large enough, you don't need another one. I'm going to comment this code out, but for this I'll say transformers import auto model for causal LM. So that's the one. As I mentioned, GPT uses causal language model, and then load the pre-trained GPT. I can just say GPT underscore model equal to auto model for causal LM, and from pre-trained I can pick GPT-2 in this particular case. Then I can say input underscore text equal to once upon a time. That's my input text. My input underscore IDs equal to tokenizer that I've created above dot encode input text that I've created above once upon a time, and my return tensors in this place is PyTorch PT. Next I can say output should be GPT model dot generate I call generate function, and I say input underscore IDs, comma, max underscore length equal to 50, and number of return sequences that I want for this sequences equal to 1 is good enough for us. Number of return sequences, trying to make sure there's no typo, and then I can print this out saying print generated text equal to, I'll pass the tokenizer dot decode, and to that I'll pass output, whatever I get back, output at 0. And I'll also say there's one thing special, there's sometimes there's some special tokens in front and back, so I will say skip special token equal to true. Okay, perfect. So this kind of takes care of everything. I'll probably also run this along with it just to see what happens. Doesn't matter, but it's going to take a lot of time. So I'm going to go ahead and first start this process, Python day 5. It's going to run through it. It's going to take some time. Let's see. First, it will try to get the libraries, data sets, and stuff. And there you go. It started the process of downloading. It will first get the samples data, and all my examples have been downloading. It will do this, I think, 3 times first, where it gets all the data. Next, I mean, it says some weights of bird classifier were not initialized, so I don't, that those are just warnings. You should probably train this model on a downstream task to be able to use for prediction. So that's what it mentions, but here is where I am doing all the things. Now, as you can see, since I mentioned that I want to do every log the steps every 10 steps, so every time it finishes 10, so 17, 18, 19, 20, it will print. And as you can see, it has 9,375 and is doing 1 per second pretty much, or a little bit slower than that. So it's going to take around 3 hours, I think. So I'm going to leave it here right now, and I'll come back, and when it's done, I'll show you the output. So it took around almost 5 hours, I would say, to run through those 3 epochs and give us some output back for this. Now, as per the BERT model goes, we, as you see here, it ran through all the different epochs, 3 epochs, and took around 3 hours and 51 minutes, and then it went through each and every one of those epoch items, and then kind of got us the evaluation results. Our evaluation loss, as you can see, is 31%, and evaluation runtime, this is the runtime that it took. Samples per second, these many samples were evaluated per second, and epochs are 3. We also wrote some code for this GPT, which is not completely complete because I did not give attention mask and bunch of different things, which we'll probably be doing tomorrow. But it says that the attention mask and the pad token ID were not set. As a consequence, you may observe unexpected behavior. Please pass your inputs attention mask to obtain reliable results. And also says setting pad token ID to EOS token ID none for open-end generation. So it will try to do that, but as a result, as you can see here, the generated text that we get is once upon a time, unused. So it's trying to fill it up, but it can't get the actual data out properly. But we were able to fine tune a pre-trained BERT model for the text classification. We also evaluated the fine-tuned model performance using the accuracy of the metrics. And finally, when we try to explore the GPT's text generation capabilities, since we didn't even put the code or completely write the code, we'll probably do this more on the next session. So I hope you were able to get these results similar to this. If not, let me know in the messages and I'll get back to you. To summarize, today we understood the differences between BERT and GPT, including their architectures and use cases. We learned how to load and fine-tune pre-trained transformer models for specific NLP tasks, and we gained practical experience using Hugging Faces Transformers library. And finally, we built foundational skills for advanced application like custom fine-tuning and transfer learning. If you have any problems or had any questions or issues, let me know in the messages and I'll get back to you. Day 6. advanced transformers, BERT variants, and GPT-3. So let's look at exploration of BERT variants first. Why BERT variants? While BERT is powerful, it has limitations like large computational requirements and inefficiencies in capturing certain nuances. BERT variances optimize the model for specific tasks, improve performance, or reduce computational overhead. Some of the key BERT variants include Roberta or robustly optimized BERT. It removes next sentence prediction NSP task for better efficiency. It trains on more data with larger batch sizes, and use case can be superior performance in tasks requiring deeper context. Then we have digital BERT, a distilled or smaller version of BERT that retains 97% of BERT's performance while being 60% faster. Use case is ideal for real-time applications and resource-constrained environments. Then we have Albert or a little BERT, reduces memory consumption by factorizing embeddings and sharing parameters across layers. Use case is suitable for large scale pre trained and downstream tasks with memory limitations. Next, we have BERT Wheat. It's fine tuned on Twitter data, and the use case is social media, sentiment analysis, and hashtag prediction. Next, let's go into introduction of GPT-3. What is GPT-3? GPT-3 or Generative Pre-trained Transformer 3 is developed by OpenAI. It's a massive model, 175 billion parameters trained on diverse data sets, and it excels at generating coherent and contextually relevant text. Some of the key features of GPT-3 include zero shot and few shot learning, which can perform tasks with minimal or no fine tuning. Versatility. It's used for text generation, summarization, question answering, and conversational AI. Some of the applications include first conversational AI, where chatbots and virtual assistants. Next is content generation, like articles, scripts, code snippets, and creative writing, like poems, stories, and creative ideas. Transfer learning in NLP with transformer models. Now, what is transfer learning? Transfer learning involves retraining a model on a large dataset and fine tuning it for specific downstream tasks. Advantages include it reduces the need for task specific label data and speeds up training and improves performance on specialized tasks. Now, with all the knowledge that we gained, let's get into our hands on exercise where the objective is to experiment with the BERT variant. Example is Roberta and fine tune it on an NLP task. We'll use the GPT-3 API for text generation and analyze the quality of the generated text. So let's get started. So to start with, let's go ahead and create a new file, Python file. I'll save it as day 6 underscore exercise 1 or exercise. And then here, first let's get from transformers. I am going to import our auto tokenizer, and I will also import the auto model for sequence classification. So I'll say auto model for, let's write it down, for sequence classification. That's the next thing that I want, and I want trainer and the trainer arguments, training arguments. There you go. So these are the basic ones that we used earlier too. So next, for data sets, I'm going to say from data sets import load dataset function, and with that available, I'm going to go ahead and load my data set. So for that, I'm going to say data set. In this particular case, I am going to load my data set, which is called AG news, AG underscore news, and I will load the Roberta tokenizer and model. So say load Roberta tokenizer and model, and I'm going to say for that I'll create a variable called as tokenizer, and to that I will say auto tokenizer dot from pre-trained. I am going to get, as I mentioned, that is available at Roberta dash base. So if I show you here, so Roberta dash base, that's where you can find the Roberta tokenizer. Next, for the model, I'll do the same thing. I'll say model equal to auto model for sequence classification dot from pre-trained. I want to get the same one called as Roberta dash base, and I'll give another for labels. I'm going to say number of labels that I want is equal to 4. So specify that. So I have my model and my tokenizer. Next thing is, let's go ahead and tokenize data set. For that, I'll write a function as before, tokenize data set, and here I'm going to create a function called as tokenize underscore function, and it takes inside argument, let's call it examples, and here I am going to say return. So this will return using the tokenizer. So as a tokenizer, I'll pass the examples, which is inside has labeled text, comma, then I'll say truncation. So if I want to truncate something based on the max length, I'm going to set that to true, truncation. Next, I need the padding of how much padding if the max length is not reached. I'm going to say max length. So based on max length, it will do that. And what is my max length? I'll have to also provide that. I'll say 128. So that will give me my tokenized items. Now let's go ahead and say tokenize underscore data sets, and for that I'll say data set dot map, and from there I'll pass that function that you created, tokenize function, and it wants to know if it bashed or not. So I'm going to say bashed equal to true, set it in batches. So that's done. Next step is to prepare the data set. So I'm going to say prepare data set. Inside here I'll say tokenize data sets or tokenized data sets, just so be more precise, because these are my tokenized data sets. I'm going to say tokenized data set dot remove columns. I am going to remove the column called as text inside here because they're tokenized already, and then I'm going to rename the label as labels. So I'm going to say tokenized data sets equal to tokenized data sets dot rename column. One column I want to rename, so that's why. And then I'll say labels, label to labels. So that's good. Next thing I'm going to say tokenized data sets dot set format. Now what format do I need to set here? In which torch? PyTorch. So that's why I'll say torch. Next thing is I need once I select torch, next thing is I want to get the train data set. So I will say train data set for the model. This is for the model that I can get from tokenized data sets, and once with the label train. Same thing for test data sets. This will be available inside my tokenized data sets named as test. So perfect. So I got that. So next, let's go ahead and get the training arguments. Training, too many in arguments, and those are, I'll call it training underscore args equal to training arguments, and inside that I'll pass the parameter that it needs is first is output directory, is where you want to output. I'm going to say dot slash results. Next, I'm going to say what is the evaluation strategy that it needs, or eval strategy is equal to epoch. Next we need is learning rate. What is the learning rate? So this I'll say 2e minus 5. Next I want to say per device train batch size equal to 16, and then I'll need per device eval batch size equal to 16 again. Next I need is the number of training epochs. So I'm going to say number of train epochs equal to 3. It's quite a lot. It's going to take 4 to 5 hours. Weight decay equal to 0.01. I always say once you run this, what you have to do is you just go ahead and do rest of the stuff of your day and then come back. And then I'll say save steps every 500, save a step, weight decay 0.01, number of train epochs 3. So everything is ready for my training arguments. Now it can be taken by trainer. So let's create our trainer here. Trainer, I'll say trainer equal to trainer, and to this, first thing it needs is the model. So I'm going to say model equal to model. That's what we named it, so easier. Next, it needs the arguments, which is the training arguments. So I'm going to give it whatever I created above. So I called it training args. Next, it needs is the training data set. So I'm going to say train data set equal to, I called it train data set. And then next is eval data set. So eval data set equal to, I called it test data set. And then next it needs the tokenizer, or which is also called as processing class, if I'm not wrong, equal to tokenizer. It still thinks is tokenizer. This is what do you call it? Deprecated. Before it was called tokenizer equal to tokenizer. Now it's called as a processing class equal to tokenizer. So that's how you set it. Now once this is done, let's go ahead and train our model. So train this model. Let's train our model. To do that, I'm going to just say trainer dot train. That's about it. Now since it's going to run 3 to 4 hours, let's also go ahead and get the evaluation results. So evaluate the model, and I'm going to say results equal to trainer dot evaluate, and then I'll say print evaluation results is equal to results, whatever I got above. Save it. So this should be good to run. Now again, as I mentioned, once I run this, it's going to take 4 to 5 hours. So be prepared for that. So I'm going to go ahead and say Python day 6. Okay, let's run it. Now, as I mentioned, it's going to take some time. So I'm going to let it run and then come back when it's completed training and then evaluating the data, and then we can continue from there. So it took around 4 to 5 hours, I think, approximately, to get this thing running, and we have our results here based on the data that we have provided, the AG news set, and using our model, we kind of got the evaluation results here. The final evaluation results say evaluation loss is 20%, whereas evaluation runtime is 72.13, samples per second is 105, and steps per second is 6.5 with epochs of 3. So this is our final results here of the evaluation. I hope you are able to follow along and get some similar results. Our next step is to use the GPT-3 API for text generation and analyze the quality of the generated text. So let's go get started with that. So let's go to Visual Studio Code again, and this time I'll create a new file. I'll save it as, let's call it day6ex underscore OpenAI. And to run this, first what I'll have to do is I'll have to install OpenAI. So I'm going to say pip install OpenAI. So they have a library available. So it's very fast for me because I've already installed it, but make sure that you install it again. And once you have that installed, let's go back here and write our code. First I'll say import OpenAI. Next I'm going to set OpenAI API key. So for the OpenAI API key, go to Chrome and go to platform.openai.com and create an account, and inside there you can get your API keys from API keys here. I've already created an API key, and that's what I'm going to use. Do not use mine because again, it's built and it will be billed to you depending on how much you use. So do not use mine, and I'm not going to show you mine, but this is where you get the key from. So when you say create new secret key, it will show you your API key and you can use that API key. So I'm going to close this here. I'm going to go here. Our next step, as I mentioned, is to set this up so that I say OpenAI dot API underscore key. That's how you set it. And here you set your key. Now I'm going to just copy my key into here. Next, I'm gonna say try, and first thing I'll try to do is I'll try to generate text using, I'm gonna use GPT 3.5 Turbo that's available to me. So I'm gonna say I'm gonna use that library. For that, I'm gonna say response that I get from the API equal to OpenAI dot chat completion dot create, and inside here I will set first the model that I want to use is, as I mentioned, is GPT, actually that's in double quotes. I'll say GPT dash 3.5 dash turbo. Next, I'm going to say what is the message that I want to send. So I'm going to create an array of messages equal to give it some context. I am going to say the first one where the role, so I have specified as a key value pair, where the role is system, and the content of this is, it says you are a helpful assistant. That's what I'm going to say, and that's the role for the system. Next, we have, I'm going to create a role called as the user who's going to ask questions. User, and his content is, I'm going to say that write a short story about, you can like specify as if you're going to chat GPT and saying stuff. So you can say about a robot learning to cook, something like that. So that's what I'm asking it to write. It's saying, think of like as if you're going to chat GPT and writing this text, what will happen. So it will do the same thing because again it uses the same OpenAI engine. So next step, so that's the messages that is passed. Now I'm going to say max underscore tokens used for this is 150, and then I'm going to say temperature. So temperature is used to check like how much how, like, more higher the temperature, better the answer is, but it's cost more too. So that's what I've specified here. Next, I'm going to go ahead and print my generated text. Generated text is, I'm going to move it to next line and say from the response. So you can look at the documentation. So the response comes in an array list called as choices, and inside that I'm going to pick the first choice, and from that first choice I'm going to read the message in there, and that message object has another object inside. It's not p but content. So that's where the data is. So from that data I am going to go ahead and say strip, because it might have some spaces and other things. So I'm going to strip it out. So strip will clean the text that I have and display it for me as generated text. Next, now I have given try, so I'm going to also say except. So that means if there's an error or something, if there's an exception, I want to catch it instead of crashing. I'm going to say print here f of an error occurred, and that error, if I want to display it to the user or here on the screen, I'll display that error. So perfect. So my entire code is here. So this is how it works. It just replace your OpenAI API, get that, and then you can run this too. So I'm going to go ahead and run this. It will be faster. Doesn't take 3-4 hours. It'll be immediate because the API is already, the AI is already trained. The model is trained. All I'm doing is passing a question, and it's going to give me a response. So I'm going to say Python day 6 underscore OpenAI, run it. And there you go, we have the generated text. Once upon a time, in a bustling city filled with technology and innovation, there was a robot named RoboChef. RoboChef was a state of the art robot designed to assist in the kitchen, but there was one problem: RoboChef couldn't cook. Determined to learn, RoboChef embarked on a journey of discovery. It started by observing the talented chefs at a nearby restaurant, studying their every move as they chopped vegetables, stirred sauces, and grilled meats. RoboChef also read countless cookbooks and watched cooking shows to understand the art of culinary creation. After weeks of learning and practicing, RoboChef decided it was time to put its newfound skills to the test. It gathered ingredients and set up a cooking station. And it stopped. Why? Because I said tokens equal to 150. If you specify more, it will give you more data, but again, it will cost you more too. Same thing with temperature. So there you go. We have completed both our exercises. I hope you were able to follow along. If you have any questions, let me know. So just to summarize, today we explored the strengths of BERT variants like Roberta and their advantages over BERT. We understood the capabilities of GPT-3 for generative tasks and its limitations. We learned to fine-tune pre-trained models for specific NLP tasks using Hugging Face, and we built some practical skills in working with state-of-the-art transformer models. If you have any problems or issues or questions, let me know in the messages and I'll get back to you. Day 7, Transformer Project, where I'm going to guide you through text summarization and or translation. You can pick one or both. Let's start talking about applying transformer based models to advanced NLP tasks. Our first task is text summarization. That is the process of condensing a piece of text while retaining the key information. There's two types: extractive summarization, which selects key phrases or sentences from the original text. And then we have abstractive summarization, which generates new sentences that capture the meaning of the original text. Next, text translation, that converts text from one language to another while maintaining the meaning and grammar. Examples can be English to French translation, multilingual translation with models like T5 or MT5. Let's talk about fine tuning and optimizing models. We have pre-trained models for summarization and translation. First is T5, which is text to text transfer transformer. That's why it's called T5. It treats every NLP problem as a text to text task. It's fine tuned for summarization and translation tasks. We have BART, which is bidirectional and auto regressive transformer. It combines BERT like encoder and GPT like decoder. Is pre-trained for denoising and fine-tuned for summarization and translation. Next, what are the optimization techniques? Learning rate scheduling and hyperparameter tuning, where you tune the batch size, optimizer type, and maximum sequence length. Let's talk about analyzing model performance next. So what are the different evaluation metrics for text summarization? We have ROGUE, which is recall oriented understudy for gestling evaluation, and we have BLUE, which is bilingual evaluation understudy for generated summaries. Next, for text translation, we have BLUE score for translation quality, and we have perplexity to measure model performance. With this in mind, let's jump into our hands-on project where the objective is to fine-tune a pre-trained transformer model, example T5 or BERT, for text summarization and or translation and evaluate its performance. So let's get started. So first step, let's go ahead and create a new file. I'm going to say Python file, save it in our day 7 underscore exercise. And then first thing that I need is I need to make sure that you have all the install required libraries. So I'm going to go ahead and say pip install transformers and datasets. So make sure you have this. It will be pretty fast if you do that early. Next step is to prepare the dataset. Now we will use the CNN Daily Mail dataset for summarization, and for if you want to do translation, you can use the WMT 14 English French dataset for translation. And I'm going to show you the steps as I mentioned. So I'm going to say from dataset import load dataset. So this will load my datasets. Now to load the dataset for summarization, I'm going to say dataset equal to load underscore dataset and pass it. As I mentioned, I'm going to use the CNN underscore daily mail, and the version is 3.0.0 is what I'm going to use. And then I can print of how this dataset looks like. Dataset in the training module, show me item number 0. just to see how it is. Now for translation, you can use, I'm going to create this variable, but I'm going to comment it out. You can run this yourself. Data set, and as I mentioned, the best one to use is WMT14 at the time of the recording. There might be better ones coming out, but this is what I'm going to use, English to French. So that's what you can use. I'm going to comment this out because I'm just going to do summarization right now. So now next is we have to tokenize the data set, which we have done before. So for that, again, from transformers, I need to import auto tokenizer. If you spell wrong, then it will not help you. Auto tokenizer. Next, I'm going to go ahead and first load the tokenizer. Now the tokenizer in this case is, I'm going to use the T5 small tokenizer. So I'm going to say tokenizer equal to auto tokenizer, and from underscore pre-trained, I'm going to, as I mentioned, T5 dash small. That's what I'm going to use. Next, I'm going to say tokenize for summarization. I'll do that. I'm going to move this up a little bit so it's available. Function is, as I mentioned, tokenize underscore function. This will be added as a parameter in the actual tokenizer that I'm going to call in some seconds. So function examples. Now first, I'm going to say inputs equal to summarize, and then I'll pass it doc for doc in examples. So I'm going to take the example that was passed to me. Inside that I have articles, which is articles from the CNN, this one data set that we have, CNN Daily Mail. It takes these articles and it will take each and every one as a doc and then summarize them. So that's what it does here. Next step is, I'll say model underscore inputs equal to tokenizer and pass it inputs that I've created above, and I'll say max underscore length equal to 512. That's the max that I want to do, and then truncation equal to true. So that's my model inputs. Now let's go ahead and tokenize the targets. To do that, I'm going to say with tokenizer dot as underscore target tokenizer. I want to get the labels, which is equal to tokenizer, and it needs examples of highlights. So these are my targets. Max length equal to 150, and I'll say truncation equal to true as before. Perfect. So that takes care of my tokenizing targets. Now let's go ahead and I'm going to say model underscore inputs dot labels equal to labels of input IDs, input underscore IDs, that's where it is, and then I will finally return my model inputs. Perfect. So that's what I'll get back. Next step is to fine tune the model. So for that, I'm going to go ahead and first from transformers, or I can just use it here, I can say auto model. For this time, I'm going to say use sec to sec LM. That's what I'm going to use. Go at the bottom here, and I'm going to say model that I want to use is auto model sec to sec LM dot from pre-trained, and I will select, as I mentioned, T5 dash small. Next, let's go ahead and define the training arguments. So I'm going to say for that, I will go above, and in here from transformers, I need training arguments, as you remember. So I'll go back, and here I'm going to say training underscore arguments equal to training arguments, and here pass the different arguments. Now it will help me here to tell me what it needs, which is output directory equal to dot slash results. So it will create a results folder over there, and that's where it will keep the results. I want to say the evaluation strategy or eval underscore strategy that I want to use is epoch. Next, I'm going to say that the learning rate that I want to use here is 2e dash minus 5, and then I'll say per device eval batch size and train batch size equal to 8. So I always like to give per device train batch size equal to 8, and then eval batch size equal to 8, and then I'll say number of training epochs that I want to do is equal to 3, and then I'll say that weight decay that I want equal to 0.01, and then I'm going to say save the total limit equal to 2, and I'll say predict with generate, which is predict with generate equal to true. Maybe because I messed up something above. Let's go ahead and fix this. Weight decay equal to 0. And then predict with generate equal to true. Perfect. So these are my training arguments. Next thing that I want to create is to train the model. Now to train the model, I need to get the trainer. So I'm going to go above here, say trainer. Now here I'm going to come down and say that trainer equal to trainer, and then pass it model equal to model arguments equal to training argument that I've created above. Next, I will say training data set that I want to use is my tokenized underscore data set. Did I create that above? I guess I forgot to create the tokenized data set after this step here. So I'm going to say tokenized underscore data sets equal to data set dot map, and to this I pass that function above that we created, tokenized function, and then I say batched equal to true. Okay, perfect. So now that I have tokenized data sets, I can go here and say tokenized data sets of train. So that will get my train data set. Next thing I want to do is get the evaluation data set. So that is eval data set equal to tokenized data sets again, and this time the value is inside not test, but it's called validation. Next thing that I need is my processing class, or also called as tokenizer. From before is tokenizer. I say that's fine. So before it was called tokenizer, that's why it says tokenizer equal tokenizer, but we need process. The new one is called, it will still work, but it's better to give the new name because that will be deprecated eventually. Then I'll say trainer dot train. This will train the model. It's going to take some time, so you can relax after that. So next, before even stopping, we want to see it in action. So what I'm going to do is I'm going to give a sample text. This is the evaluating the model. So I am going to say sample underscore text equal to, I have some sample text. Let me get that. Now paste it here. So the transformer model has revolutionized NLP by enabling parallel processing of sequences. That's my input text. Now I'll say my inputs equal to tokenizer, and then to that I'll pass summarize, and I'll say what do I want to summarize here, plus sample text from above. That's my input. Next, I'm going to say return tensors, return underscore, come on, show me tensors equal to in PyTorch format. So that's why I'll say PT here. Next, I want to specify the max length. So max underscore length equal to, I'll say 512, and then I'll say truncation equal to true. That means if it's more than what I need, I'll truncate it. So perfect. So that's done. That's my inputs. Now let's go ahead and get the outputs. Outputs equal to, I'll call the model and say generate, and to this I'll pass the inputs of input IDs. input underscore IDs, and then I set max underscore length equal to, set it to 150, same as our GPT that we did yesterday. Next, I'm going to say number of beams. In this particular case, I want to use 4, and I want to say early underscore stopping is true. So this can stop early equal to true. Perfect. So that will take care of my outputs. Now that I have inputs and outputs, let's go ahead and print generated summary. So based on whatever text, sample text I have provided, let's see what does it give me. So inside my tokenizer, I have that decode function which I can run here, and to this I'll pass outputs at 0. I will say the next parameter is skip underscore special token. So if there is some special variables that are created or that helps the model, so that I'll say skip them, don't show me, I don't care about them. That's what I'm pretty much saying here. I just want to see the text here. So if you also want to evaluate using Rogue or Blue, what you can do is you can say metric equal to load underscore metric, and then pass here Rogue, ROUGE, or you can use it's also called, for Blue you can say SACREBLEU. So that's what you can use for that. That's what you can specify, and then you can say predictions equal to outputs of, here in this case, generated underscore text, and then you can say references equal to data set of validation, and then highlights, HIGHLIGHTS, highlights. Okay, so and then you can replace this with the target translation for translation task, and then if you want to get the results, you can say results equal to metric dot compute, and then to that you can say predictions equal to, pass the predictions that we got above or created above predictions, and then it needs references which we have created above references, and then finally you can print the final evaluation metrics by just saying, let's say, like you can just say results, and this will give you the what you call the evaluation metrics over here. I'm going to go ahead and comment this out because I just want to see the generated summary and I don't want to see this. So let's go ahead and run this and open my terminal and say Python, and the name of the file is day 7. Okay, there you go. And it started getting the data, and then it's going to run for a little while. So I'm going to leave it as it is and come back once it's completed training and evaluating and show you the final output. So it took a couple of hours, but after that we got the generated summary where it says transformer model has revolutionized NLP by enabling parallel processing of sequences. So we were successful in training or fine-tuning a pre-trained transformer model. In this case, we used T5 for text summarization and were able to look at the outputs. If you had any issues or problems with implementing this, let me know and I'll get back to you. Now to summarize, this week and today, we understood the end-to-end workflow for fine-tuning transformer models on advanced NLP tasks. We gained hands-on experience in data pre-processing, fine-tuning, and evaluation for summarization and translation. And we learned to experiment with hyperparameters to optimize model performance. We also developed insights into practical challenges and solutions for working with large-scale NLP tasks. Let me know if you had any problems, issues, or have any questions in the messages, and I'll get back to you.
Welcome to week 13, transfer learning and fine tuning. This week, first, we'll look at introduction to transfer learning. Our day 2 will cover transfer learning in computer vision. Day 3, we'll look at fine tuning techniques in computer vision. Day 4 will cover transfer learning in NLP. Day 5, we'll be looking at fine tuning techniques in NLP. Day 6, we'll be looking at domain adaptation and transfer learning challenges. And finally, for day 7, we'll be doing our transfer learning project where we will be fine tuning for a custom task. So let's get started with week 13. So let's start with the day 1 of our week 13 with introduction to transfer learning. So first, we're going to look at what is transfer learning. Transfer learning is a machine learning technique where a model trained on one task is reused as a starting point for another related tasks, and hence the name transfer learning. Instead of training a model from scratch, pre-trained models are fine-tuned on a smaller dataset for a new task. Now, how it differs from traditional training? For that, I have a table here. So as per starting point, in traditional training, you train from scratch using random weights, whereas in transfer learning, you start with a pre-trained model. For training time, traditional training is longer due to need for learning basic features, whereas in transfer learning, shorter as the model has already learned features. Next, for dataset size, traditional training requires large datasets to perform well, whereas transfer learning can work well on small datasets. Now let's talk about the benefits of transfer learning. As we mentioned, the first one is reduced training time, where pre-trained models already capture foundational features, so fewer epochs are needed. Improved performance on small datasets. Transfer learning allows effective training even when data is limited, and it leverages generalization. Pre-trained models generalize better across tasks due to exposure to large-scale datasets. Now let's talk about applications of transfer learning. In computer vision, pre-trained models like ResNet, VGG, Inception, EfficientNet are used for object detection, image classification, and image segmentation. In NLP, models like BERT, GPT, T5 are fine-tuned for text classification, sentiment analysis, named entity recognition, and question answering. With all this background, let's jump into our hands-on exercise where the objective is to set up a transfer learning environment, load a pre-trained model, and explore its architecture and layers. So let's get started. Let's create new files using our Visual Studio Code. So I'm going to say Python file. Now what I'm going to do is I'm going to do two different files. One is I'll call it day1 underscore TensorFlow TF, and another one I'll call it day1 underscore PyTorch. So I'm going to do for both of them separately. Now, first step is to always install the required libraries. So I'm going to go ahead and say, make sure that you have these installed. I am sure you have already if you are at this particular point, but just in case, make sure TensorFlow, PyTorch, and Torch Vision are installed. So it's going to take a few seconds if it's already had installed, so you're not losing much time, but try that, make sure that's there, or else that's what will kind of help you with a lot of errors that you might face in future. So next step, let's go ahead and load a pre-trained model first in TensorFlow. So in TensorFlow file, I'm going to say import TensorFlow as TF. Next, I'm going to say from TensorFlow dot keras dot applications import, and I need ResNet 50 in this particular case. So I'm going to say ResNet 50. Perfect. So I have that. Now let's go ahead and load. I'm going to type it down. Load a pre-trained ResNet 50 model. Now to do that, I can say model equal to, I can call that ResNet 50, and I'm going to say weights equal to image net. Perfect. So that will load a pre-trained ImageNet model here. Next, I am going to say display the model's architecture. So that was our first step. So I'm going to display the model architecture by saying model dot summary. That's how we load it. So that will display. And at the same time, if I want to do the same thing for PyTorch, let's go ahead and write that code. So I'm going to say import torch. Next I need, oops, I think I saved it as, let me rename it quickly.
So now that it's renamed, I'm going to say import torch vision dot models as models. So I will have both of them. Now that we have that, let's go ahead load a pre-trained ResNet 50 model here. To do that, again, I'm going to say model equal to models dot ResNet 50, and I will pass that I want a pre-trained model, and equal to true. Let's make sure I spelled it right. Perfect. Pre-trained equal to true. Next, I'm going to go ahead and print the model architecture. To do that, I'm going to say print model, and that's it. Next, let's go ahead and in this particular case, freeze the model parameter, something that we just covered. So to do that, I'm going to say freeze the model parameters first, and once I've added the comment, I can say for parameter in model dot parameters, inside this I can say param dot requires grad equal to false. So this will freeze the model parameters. Now next step is to modify the final layer for a new task. Now that's frozen, so what I'm going to say is number of features that I need equal to model dot, inside model I can call the fc dot in features. So this will give me the final layer, and I'm going to add a new task to that. To do that, I'm going to say model dot fc, which is our final layer. I'm going to say torch dot nn dot linear, and I'm adding this task here. I'm going to say number of features comma 10. So I'm giving example here is like 10 classes. Now let's go ahead and print the modified model slash n, and I'm going to say model. Perfect. So this will display me the new model, and some of the first few or all of the model parameters are frozen here. So we have frozen the model parameters, and then we just added a new task to the final layer of the model. Now to check it out, let's go ahead and run one at a time. I don't know. I know that I've not done anything for TensorFlow, so I'm going to say Python day1 underscore TensorFlow. Can run it. We can see the summary or architecture of the model. That's what we have written here. Just display the models architecture, and here is our models architecture. So it shows you this ResNet 50 with all the different layers that it has from top to bottom. You can explore that. As you can see, total parameters is these many, trainable parameters are these, non-trainable parameters are these many. So you have all the information over there. Now the same thing I'll do for PyTorch, and it will show me. I think there are some warnings at the top, but you can ignore that. They're mostly about how some of the things that are here, like pre-trained, is changed to weights, just like this here. So they're going to deprecate them. So be careful what you're doing. Or by the time when you see this video, maybe it's already deprecated. So those are things that your terminal will actually tell you what to do. And here is our entire, as you can see, the entire architecture of this ResNet 50 ImageNet model that it displays. And also it will display it again because I said modified model. If I search for it here, if you see here, this is the previous model and this is the modified model where I've added an additional task at the end of it. So that's what you see here. So I'm going to go ahead and clear this out. So our next step is inside TensorFlow. If I want to explore model layers, so I'm going to go ahead and first let's comment this out because it adds a lot of different displays a lot of different things here. So first thing I want to do is access specific layers in TensorFlow. To do that, I can say for I comma layers in enumerate model dot layer. So I'm going to each and every layers here, and then I'm just going to print. But you can actually access any of these layers by the index, and you can say do whatever you want to do with it. So I can say like this is layer I right now. The name of the layer is layer dot name, and I can also check if it's trainable, because as I mentioned earlier, you saw that there are some trainable layers, some not. So I'm going to say ask is the layer dot trainable, so it'll tell you if it's trainable or not. So if I run this now, I'm going to say run my TensorFlow, and it has some error here. Layer I think I did not close. Oops. Let's try it now. Clear, and there you go. Hopefully it will show up now with all the layers that. Okay, what happened? Layers. Clear. One more time. And there you go, we see all the different layers. As you can see, it has 176 layers, and it's going to tell me if they're true trainable or not. Also give me the name of each and every layer right here, so you can actually pick and choose whatever you want, and you can play with any layer that you want in there and train them if you want to. Now similarly, if I want to do this for PyTorch, I can say for name comma parameter in model dot named underscore parameters. Here you go. Inside this, I want to do the same thing. I want to print f of layer, and this layer is name, and then I say requires grad. I can say param dot requires grad. So this also tells you if you can play around with that model or not. So I am going to go ahead and run this again now, but this time for PyTorch. There you go. I think I forgot to do this print. I don't want to see the model or anything, but again it will show me all the different layers that are available here with their names, and if it requires grad, it will tell you true or false. Based on that, you can play around with them. As you can see, it just shows the last two because I've frozen pretty much everything else, right? So that's why it's saying grad false for everything else. Makes sense. But if I go ahead and not freeze them and not add this additional thing, you can run that again, and you see all of them are requires grad is true, so you can modify them. So that's the power of freezing and unfreezing. So let's go ahead, now that we've done that, let's go ahead and check how to freeze all the layers except the top layer in TensorFlow. So if I want to do that in TensorFlow, we have not done any code yet for freezing, unfreezing. So here I'm going to say for layer, I'm going to comment this out because I don't need this anymore. For layer in model dot layers, and we have a lot of layers here, so I'm just going to say -10, so top 10 layers. What I'm going to do to that is I'm going to say layer dot trainable equal to false. So this is the code for freezing all the layers except the top 10. Now if I want to unfreeze specific layers, I have frozen here. Let's go here and let's say unfreeze particular layers in oops, go ahead, comment it out. And in this case, what we have done was so I froze all the layers here, so I'm gonna unfreeze them. I'm gonna also put this code back, but now I want to in this particular case unfreeze specific layers. So I can go ahead and I can say for name comma param in model dot named parameters, and I want to say if layer 4 in name. So what I'm doing is I'm saying if the name of the layer is layer 4, then I want to go ahead and say param dot requires underscore grad equal to true. So you can tell just by this code, how you can actually access a particular layer and unfreeze them or freeze them. Similarly for TensorFlow, this is how you unfreeze or freeze layers. You got an idea of the model architecture. You understood the structure of the pre-trained models like ResNet 50. We learned to control trainable parameters for transfer learning, and we were successfully able to set up an environment for transfer learning using both TensorFlow and PyTorch. So if you had any issues implementing this or got any errors, let me know in the comments and I'll get back to you. Now to summarize, today we understood the concept and benefits of transfer learning compared to traditional training. We have also explored the architecture of pre-trained models and learned to adapt them for new tasks.
and we gained hands-on experience in setting up and modifying pre-trained models in TensorFlow and PyTorch. And we developed foundational knowledge for applying transfer learning to real-world problems. If you have any issues or questions or have any problems with the implementation, let me know and I'll get back to you. Day 2. Today, we're going to look at transfer learning in computer vision. So let's start with some of the popular pre-trained models for vision tasks. First, we have the VGG, which is VGG16 or VGG19. These are the deep networks with 16 or 19 layers. It's known for simplicity in architecture, where stack of convolutional layers followed by fully connected layers. And the applications for this are general purpose image classification and feature extraction. Then we have ResNet or residual networks, introduced residual connections which skip connections to tackle vanishing gradients. The popular variants include the ResNet 18, ResNet 50, and ResNet 101. Applications include large scale image classification task and object detection. Next, we have Inception. Inception v3, known for inception modules, which allow for multi scale feature extraction in one layer. Applications are scene recognition, fine grained image classification. EfficientNet, family of models that scales network depth, width, and resolution efficiently, is the EfficientNet. It provides better performance with fewer parameters, and applications include resource constrained environments requiring high accuracy. Next, let's talk about freezing and unfreezing layers for fine tuning. Now, first, why freeze layers? Early layers in pre trained models capture general features, example, the edges or textures, and freezing these layers reduces training time and prevents overfitting on small data sets. Next, why unfreeze layers? Later layers learn task specific features. Unfreezing layers allows the model to adapt to the new task. Let's look at the approach. Initial training, freeze most layers and train the last few layers. And for fine tuning, gradually unfreeze layers and reduce the learning rate for fine tuning. Let's talk about using transfer learning for image classification task. The steps involve first, load a pre-trained model, example ResNet or VGG, and replace the last layer with a task-specific classifier, example softmax for multi-class classification, and then fine-tune the model on the new dataset. Now with this knowledge, let's go ahead to our hands-on exercise where the objective is to load a pre-trained ResNet or VGG model and fine-tune it for a new image classification task, example classifying animals or plants, and experiment with freezing and unfreezing layers and observe the impact on the performance. So let's get started. So first step, let's go ahead and start with a Python file. I'm going to call it again day2 underscore TensorFlow for a TensorFlow one. And I'm going to do the same thing for day2 underscore PyTorch.py. So now that I have both my TensorFlow and PyTorch files ready, let's start first with loading a pre-trained model. For that, I am going to say import TensorFlow STF. Next, I'm going to say from TensorFlow dot keras dot applications import ResNet 50. Next, I'm going to say from TensorFlow dot keras dot layers import dense and flatten. Next, I'm going to say from TensorFlow dot keras dot models, I want to import model. Perfect. So I have that ready. Now let's go ahead and load the pre-trained ResNet 50. To do that, I'm going to say base underscore model. That's the name that I'm going to give it as base model. And then I'm going to say ResNet 50, say weights equal to image net. I'm going to download these. And then I'm going to say include
underscore top equal to false, and then I'm going to say input shape for this should be equal to, in this particular case I'm going to say 224 comma 224 comma 3. Perfect. So that will load my pre-trained ResNet model. Next I'm going to go ahead and freeze all layers in the base model. Now to do that, I can say for layer in base underscore model dot layers, layers, I will say layer dot trainable equal to false. And we saw yesterday's video that when you set this trainable equal to false, it freezes those models and you can't do anything with it. Now next I'm going to say add custom classification head to that. To do that, I'm going to say x equal to flatten. So I'm taking the existing and then adding some flatten layers here. That's what I'm doing. Say base underscore model dot output. So that's my first, and I'm going to say x equal to dense 256 comma activation equal to ReLU on top of my previous x. So that's what I'm doing here. Next, I'm going to make the output layer. This will be dense with 5 different output options. Activation equal to softmax of the previous x. So there you go. So we have created custom classification head here, which classifies into 5 different classes. So now I'm going to say model equal to model of inputs equal to base underscore model dot input comma outputs equal to whatever the output is, output variable that we defined above. Perfect. So that will have my model. Now next I'm going to go ahead and compile the model dot compile, and I can say optimizer equal to Adam. I'm going to say loss equal to categorical underscore cross entropy. I know you see a issue here where I am putting this outside. Cross entropy comma metrics equal to accuracy. So I have my optimizer, loss and metrics defined here. Next I'm going to go ahead and print this model. Perfect. So that's it. So I'll go to my command prompt, and here I'm going to say python day2 underscore tensorflow.py. Run it. It's going to download. If you're not downloaded before, it says no module named tensorflow.keras.application. Yep, because it's called applications. So let's go ahead, clear it out again, run it again. And there you go. We see our model with our flatten, dense and dense here displayed after on top of the existing layers which are not trainable because we froze them. So similarly, if I want to do this in PyTorch, I'm going to go here and say import torch. Oops. Next, I'm going to say import torch vision dot models as models. Next, I need to import torch.nn as nn. Now here I'm going to first again load the pre-trained ResNet 50. To do that, I'm going to say model equal to models.resnet 50, and I'm going to specify pre-trained equal to true. Once I'm done with this, I'm going to again do the same thing what I did in TensorFlow, is freeze all the layers. To do that, I'm going to say for param in model.parameters, I am going to say inside here param dot requires grad equal to false, and this will freeze it, freeze all the models. Now I'm going to go ahead and replace the last layer uh, for a new task. So that for that I'm going to say number of features. Let's see how many features are there. First of all, say model dot fc dot in underscore features. That's how you get that. And then I'm going to say model dot fc equal to nn dot, what I want to add, I want to add a sequential. Inside this I want to add a layer of nn dot linear number of features that are there, comma 256. So I added one, another layer, I'll say nn dot ReLU. That's my activation function. Next I'm going to say nn dot dropout, and I'm going to give 40%, and then I'll say nn dot linear 256 comma 5. This is again the 5 classes that I mentioned earlier in TensorFlow, same thing here. And then finally softmax dimension equal to 1. Perfect. Now I'm going to go ahead and print the model. Go ahead, open this. I'm going to clear this out, and I'm going to say Python PyTorch. And there you go. So we'll have all our models displayed plus the one that we added on top, where we have linear ReLU, dropout, linear softmax, right, displayed here. So there you go. That's how you load a pre-trained model and add your own own layers on top of it. So I'm going to go ahead and clear it. Next, let's go ahead and prepare the data set. So to prepare the data set, first we'll do that in TensorFlow. So I'm going to go here in TensorFlow. I am going to say from TensorFlow dot keras dot pre-processing dot image. I'll say import image data generator. So that's what I need. And then I am going to go at the bottom here after my model is created, and I'm going to say data preparation. Inside I'm going to say data gen, so generated data, equal to image data generator. Now I say rescale equal to 1 point divided by 255, and I'll say validation split here is 20-80%. So I'm going to say 0.2. Perfect. So that will be my data generated. Now for the training data, now if you have some data available, what you can do is you can just call the flow from directory function, and then give the path. So I'm going to just say path to your data set. So whatever data set you have, you can set it here, and then you can say target size equal to 224 comma 224. Next I'm going to say batch size equal to 32. Then I'm going to say class node equal to categorical, and then you can say subset equal to training. Now I want to get the validation data equal to same thing. I'm going to just copy this from here, data gen dot flow from directory, give the path to the data set, target size is this, batch size is this, class node is categorical, subset is, instead of validation, or sorry, training, this is validation. So that's how you specify. So this is how you can train your or prepare your data set, so this is how you prepare your data set in TensorFlow. Now I want to do the same thing in PyTorch. So in PyTorch, I'm going to go and say from torch vision, I want to import data sets and transforms. That's what you used earlier in previous weeks. So first, for data preparation, I am going to say transform equal to transforms that I just imported dot compose, call the compose function, and to this I'll pass transforms dot resize to the value that is 224 by 224. Next I'm going to say transforms dot to tensor to convert that into tensor. Next, I'm going to say transforms dot normalize with mean of some values here 0.485 comma 0.456 0.406, let's say something like that, and then standard deviation of, let's say, 0.229 0.224 0.225, something like that. So I've set that to normalize with this mean and the standard deviation value. Our next step is I need the training data equal to, in this case I'm going to say data sets dot, I need to pass the folder again, same as what we did for TensorFlow, and here we pass path to the folder wherever it is, and it is the training folder again, just like previously, training and validation folder. So this is the training one, and I'm going to say transform equal to, I have the transform above created, so I'm going to pass that here. Next, same thing for validation data. I am going to say val data equal to data image set path, and this one, instead of train, I have to give the validation data set transform equal to transform. Perfect. Now I'll give train loader and then validation loader. So first for train loader, I'm going to say torch dot utils dot data loader. I'm using the entire thing because I've not imported this. Usually I like to import this file so I don't have to specify everything. And this needs our training data, our batch size of 32, and I'm going to say shuffle, since it's training data, I will shuffle it. I'm going to say shuffle equal to true. Now for validation loader, I am going to say torch.util data loader, and here I'm going to say validation data batch size, and instead of shuffling it, I'm going to say don't shuffle it for this. Perfect. So that's done. So that's how you could prepare your data sets. Now next, to train the model, I'm going to go back to TensorFlow again, move it all the way to the top. Our data set is available. Let's go ahead and train the model. Now to train the model, I'm going to say history equal to model dot fit, and inside this I'll pass the training data first. Next parameter it needs is the validation data. I said validation underscore data equal to our val underscore data that we've created above. Next, I'm going to say number of epochs that I want to run equal to, let's say, 10. Next, I need steps underscore per underscore epoch. I'll say length of train data, depending on how big that is. I'll use that, and then I'll say validation underscore steps equal to, for this I'll use the length of the validation data. That's what I'll do. So that's my training the model. Now same thing if I want to do it in PyTorch. Let me save this. In PyTorch, first I will need the optimizer. So from I'll say import torch.optim as optim. So I have that. Once I have that, I can go ahead and give the criterion and criterion and optimizer, which is the defining the loss and optimizer. So I'm going to say define loss and optimizer. To do that, I am going to say criterion equal to, I will say nn dot cross, the one that we've used before, cross entropy loss. And for optimizer, I'm going to say optim dot Adam, and I'll say model dot parameters as one variable, and the second one is the learning rate equal to, this I'll specify to 0.001. Perfect. Now let's go ahead into the training loop. Now for epoch in range of, let's say I want to run it for 10 epochs, just same as TensorFlow. I'm going to say model dot put it in training mode. Once it's in the training mode, I'm going to say for inputs and labels in train loader. I am going to say optimizer in this particular case dot 0 underscore grad. So I'll zero out all the gradients, and next I will say outputs is the same thing that we've been doing in the previous weeks. Pass the model of inputs. Now, if you're not seen the previous weeks, I'll probably recommend you to do that before you get into this, because you'll not understand what I'm doing here. Criterion, so this is the loss. I'm going to say outputs, and I need to pass the labels. So that I'll pass here. Now that loss is done, now I'm going to go loss backward, and I'll optimize the step. Call the optimizer step function, done. And then now that is done, I can, if I had created a loss variable, I would have probably displayed that, but I can just say f of epoch, depending on which epoch it is, epoch plus 1, since it starts with 0. I'm going to say loss is, just display the loss of this particular loop. I'm going to say loss of item. If you had a variable, the thing that we do is we keep on adding up the loss. Next step is to experiment with freezing and unfreezing layer. So let's go to TensorFlow and freeze the, let's unfreeze the last 5 layers for fine tuning. So what I'm going to do is for layer in base model, that's what we called it, base model dot layers of, since I want the last 5 layers, I'm going to say -5 colon, and then here I'm going to say layer dot trainable equal to true. So now I'm unfreezing them here, and then I'm going to say model dot compile optimizer equal to I need to pass optimizer, which I want to say tf dot keras dot optimizers dot Adam, and I'll say learning underscore rate. For this I want to set up as 1 e minus 5. Next I'm going to say loss equal to just what we've done before, categorical cross entropy. So I'm going to say categorical underscore cross entropy, and then metrics I want to pass as accuracy, same as before. So that will compile my model. Now if I want to do the same thing for PyTorch, let's save it here, go to PyTorch. Here I'm going to say for name comma param in model dot, it's called named underscore parameters. You can also call children, that's another way of doing it. If layer, so let's say layer 4 in name, then I'm going to say param dot requires underscore grad equal to true. That's how you do that and unfreeze specific layers in PyTorch. Now if you want to evaluate the model, this is the final step. In TensorFlow, I can just say val underscore loss comma val underscore accuracy. I can calculate by saying model dot evaluation or evaluate comma, sorry, and then I'll pass it the validation data. This will give me the validation accuracy. So similarly in PyTorch, if you remember, the way to evaluate is first you put the model in evaluate mode, then I create two variables, correct equal to 0 and total equal to 0, create two variables, because once I open torch with no grad, the reason I'm doing it so it's optimized faster, it ignores the gradients. For inputs comma labels in val underscore loader, go through each and every one. I'm going to say outputs equal to model comma model of inputs. Now I don't care about the inputs. I'm going to say underscore comma predicted, which I get from torch dot max outputs comma 1. So once I get predicted, I can say total plus equal to labels dot size of 0, and then I can say correct plus equal to, I can check if predicted is equal to labels. If it's same, then I can say, okay, sum it up dot that particular item. So that will give me that. Then I can print this validation accuracy based on the, so I can say if I want to say 100% times correct divide by its total, uh, let's say 0.2 f is how I want to display it. So I can just say something like this, print f of validation accuracy is equal to this, close it, perfect. So that will give me my accuracy, 100 times correct, total f, and then of course if this is in percentage, so I can also display the percentage. So that's how you do it. So here we covered both loading a pre-trained ResNet or VGG, on our case with ResNet, and fine-tuned it for new image classification task, and then experimented with freezing and unfreezing layers and observe the impact on the performance. So if you have any questions on implementing this, or if you have a data set to play with and had any issues, let me know in the comments and I'll get back to you. To summarize, today we developed some hands-on skills in using pre-trained models for computer vision tasks. We understood the benefits of freezing and unfreezing layers in transfer learning, and we learned how to evaluate and interpret the performance of fine-tuned models. Finally, we gained some experience in implementing transfer learning workflows using TensorFlow and PyTorch. So if you have any questions or problems or had issues implementing any of this, let me know in the messages and I'll get back to you. Day 3, fine-tuning techniques in computer vision. Let's start with choosing layers to fine-tune and understanding the feature extraction process. Now, what is the feature extraction in pre-trained models? Early layers capture the low-level features, example the edges and the textures. Middle layers capture mid-level features, example the shapes, parts of objects, and the late layers capture high-level features which include specific objects or task-specific patterns. Next, let's talk about choosing layers to fine-tune. First, freeze the early layers, where you retain general features learned during pre-training, and then unfreeze the late layers, allow the model to adapt high-level features to the new task. Now, the best practices here is for small datasets, fine-tune only the last few layers, and for large datasets, unfreeze more layers and fine-tune with a smaller learning rate. Let's talk about data augmentation for improving generalization. Now, what is data augmentation? It's a technique to artificially increase the diversity of training data by applying transformations like rotation, horizontal or vertical flipping, scaling or zooming, cropping, or color jittering. Now, why use data augmentation? It reduces overfitting by introducing variability. It improves the model's ability to generalize to unseen data. Examples of augmentation include rotation, where you rotate an image by random degrees, example plus or minus 15 degrees. Then you flip, where you apply horizontal or vertical flips. There's also zoom, where you randomly zoom in or out of images. Let's talk about hyperparameter tuning for transfer learning. Now, some of the key hyperparameters include, we have learning rate, where a smaller learning rate is recommended for fine-tuning pre-trained models. If too large, then it overshoots the optimal solution. If it's too small, it's slower convergence. Batch size. Larger batches stabilize training but require more memory, and smaller batches may lead to noisier updates but help with resource constraints. Then we have optimizer. We either use SGD, which works well with transfer learning when paired with momentum, and Atom, which you're familiar with, is faster convergence but may require fine tuning for stability. As per the tuning process, you start with default setting, example the learning rate of 1e minus 4 with the batch size of 32, and experiment with one hyperparameter at a time to isolate its effect. Now, with all this knowledge, let's jump into our hands-on exercise where the objective is to apply data augmentation to a data set and train a fine-tuned model, and we'll experiment with hyperparameters to observe their impact on performance. So let's get started. First, we're going to do just TensorFlow right now. So I'm going to say day 3 underscore TensorFlow. And let's start with loading a pre-trained model. So I'm going to say import TensorFlow STF. Next library that I need is from TensorFlow dot keras dot applications import. I want to import mobile net v2. Next, from TensorFlow dot keras dot layers, I am going to import dense. I'm going to import another one, global average pooling 2D. And from TensorFlow dot keras dot models, I will import model. Next, let's go ahead and load the pre-trained mobile net v2. To do that, I am going to say base underscore model equal to mobile net v2. The weights that I want to use equal to image net. Next, I'm going to say include underscore top equal to false. Don't include the for top. And I'm going to say input underscore shape is the same what we have used before in yesterday's video. We'll use the 224 comma 224 comma 3. Perfect. So that my base model is available. Now let's go ahead and freeze all the layers. To do that, I'm going to say for layer in base underscore model dot layers. Oops. I'm going to say layer dot trainable equal to false. Next, I'm going to say add classification head here. So I'm going to say x equal to global average pooling 2D. Use that, and to that I'm going to add base underscore model dot output. So from there, next I'm going to say output equal to add a dense layer with 5 classes, and activation I'm going to set it to soft max of the previous X layer. Next, finally, I'm going to say model equal to model, and I'll pass that inputs equal to base underscore model dot input, and pass out output equal to output. Perfect. So that's my model is ready. Now next step, now that we have loaded a pre-trained model, next go ahead and apply the data augmentation here. To do that, I am going to first go up here and say from TensorFlow dot keras dot preprocessing dot image, I want to import from here something called as image data generator. So once I have that, I'm going to go down here and I'm going to define the data augmentation. So let's say that, call that out, define data augmentation. So I'm going to say data gen equal to image data generator. To this, I'm going to say rescale equal to 1 point divided by 255, comma. Next, I'll give the rotation underscore range. So how much with plus 20 minus, so 20. Next, I'll say width shift range. Use that shape underscore range. In this particular case, I'll say 0.2. Next, I want to give the height shift range. Height underscore shift underscore range. I'll give the same value 0.2. Next, I want to give the shear range. Shear range that I'll set to same 0.2. Next, I'm going to say zoom range, how much you can zoom and zoom in, zoom out. That again, I'll say 0.2. Next, I'm going to say do you want to flip it? Horizontal underscore flip equal to, I'll set that to true. and then I want to give the validation split underscore split equal to 0.2. So that will create my data gen. Now let's go ahead and create the train data object. So train data equal to data gen dot flow from underscore directory. Now this is wherever your data set is available. Again, same as last time. I'll say path to underscore data set. So just pick from there. Next, I want to say target size, target underscore size. If you remember what size you provided above, 224 comma 224. That's what we'll specify. Next, once we have the target size, next thing that we want to do is batch size. Batch size equal to 32. Next, I'm going to say class underscore mode equal to, I'll say categorical. Categorical. Next, I want to select the subset. Which subset is this? This is the training subset. Now again, if I want to do this for the validation data, again, same thing, copy paste, just go ahead and change train to validation data. Next, it's path to the data set, target size, batch size, class name is categorical. The only thing changes here is validation. Perfect. So I have that. Now next step is to train the model. Now to train the model, first thing that I need to do is, let's go ahead and compile the model. I'll say model dot compile, and here I'm going to select the optimizer. Now optimizer is available in tf.keras.optimizers.atom. So that's what I'll get, and then it needs a learning underscore rate equal to 1 e minus 5, and then I'll say next is my loss. Again, loss equal to categorical underscore cross entropy, and then I need to pass the matrix which is and this accuracy. Perfect. So that creates my compiled model. Now let's go ahead and train the model. Now to train the model, if you remember, you create a variable history, and it's a model dot fit, and then to this I'm going to pass the train underscore data. I can pass the validation underscore data, which is my val underscore data. Next, I can give the epochs equal to, let's give 10. It will train for 10 epochs, and I'm going to say steps per underscore epoch equal to length of our training data, and then I'll say that validation steps equal to length of our val underscore data. Perfect. So I have that. So that will train my model. So once the model is trained, uh, next step is you can tune the hyperparameters. You can adjust the learning rate depending on how you want. You can experiment with batch sizes that we have provided here. So you can change that to 16, 64. You can test different types of optimizers. So instead of Adam, you can use SJD and see how it performs. So this is for our TensorFlow. Now, if I want to do the same thing, day 3 for pytorch.py, let's start with our first step. Again, the first step was to load a pre-trained model. Now to do that in PyTorch, first I'm going to say import get the libraries, of course, torch, and then import torch vision dot models as models. Next I'm going to say import torch dot nn as nn. Next, let's go ahead and load the pre-trained mobile net v2. To do that, I can say model equal to models dot mobile net underscore v2 is what I want, and I'm going to say pre-trained equal to, I want a pre-trained model. So that give me the model. Next, I'm going to go and freeze all the models. So if you remember that for param in model dot parameters, so for each and every parameter, I'm going to say param dot requires grad equal to false. So this will freeze all the layers. Now we want to replace the classification head. So to do that, I can say model dot classifier of 1 equal to nn dot linear, and then to that I'll pass model dot last underscore channel, so that way I can get access to that, and I'm going to say 5 is what I want. So this is the 5 different classes that I want to classify it with. So that's the first thing. Now let's go ahead and add the data augmentation. So just like in TensorFlow, first I need my from torch vision. I need my library functions, which is datasets and transforms. What I need now, I'm going to go here and let's go ahead and define the data augmentation first. For that, I'm going to say train underscore transform equal to transforms dot compose, and this will have all my layers in here. So I'm going to say transform dot, or not layers but the image transformations. I'm going to say random rotation. So random rotation of how much did we set in TensorFlow? 20 degrees. So I'm going to use the same thing. Next I'm going to say transforms dot random horizontal flip. I'm not going in the same order, but you can look at what we did over there and use the same as TensorFlow. Then I want to create, like, say, random resized cropping. So I'm going to say transforms dot random resize crop. That's what I want to do, and that I want to do of 2 to 4 because that's our image size. Transforms dot to tensor, that is important. And then finally I'll say transforms dot normalize. After all that thing, I want to make sure that they are of a particular, so with the mean of 0.485, 0.465, 0.406, and I want to give a standard deviation in the range of, let's say, 0.229, 0.224, and 0.225. Seen that these are the best numbers that you can provide. And now I'm going to get the validation transform equal to transforms dot compose, and here I'll give first one transforms dot resize 224 comma 224. Next I want to make sure that it's in tensor format, so I'm going to say transforms dot to tensor. Next I'm going to say transforms dot normalize, and I'll give the same mean and these mean and standard deviation. So that's good. So that's my validation transform. Now let's go ahead and create the training data. I'm going to say train data equal to data sets. I'm going to say pass the image folder that I have, which is, let's say, training image folder. If you want to play with some, there's some folders available, data available in Kaggle that you can download and play around with that. Transform equal to train underscore transform. I'll pass that. And then for my validation data, I'm going to say validation data equal to dataset dot image folder. I'll give the path of my image folder, and this time is not the, make sure you change it to the validation image folder that you have. Transform equal to validation underscore transform. Perfect. So pass that. Now finally let's get our train loader and validation loader. For train loader, I'm going to say torch dot utils. I've not imported the data loader, so I have to go through the entire thing again. Data loader, and this needs our train data. It needs our batch size equal to 32. That's what I'll pass. And then I will say shuffle this data equal to true. Now same thing for our validation loader, torch.utils.this, and instead of train data, I'll give validation data, batch size is same, and in my validation, I do not shuffle them. So that kind of takes care of that. Now next, I'm going to go ahead and train the model. So train the model, again, I need from or import torch dot optim as optim for my optimizers. And here I'm going to go ahead and create my criterion equal to nn dot cross entropy loss. There you go, that. And my optimizer that I want to pick is optim dot atom pass model dot parameters and my learning rate equal to 1 e minus 4, something like that. And then I am going to go ahead in my training loop. I'm going to say for epoch in range of 10, run it 10 times, say model dot train, oops, too many these, and send for inputs and labels in train loader. I'm going to set first optimizer a dot 0 underscore grad, so my gradients are removed from the previous loop. Next I'm going to say output equal to model of inputs. Perfect, so that's good. Then my loss calculation, I'll pass my criterion that I've created, and to that it needs outputs and it needs labels. So perfect, so that's there. Now I'm going to go ahead and go loss dot backward, and I'm going to go optimizer dot step. Perfect. And then after end of this, I can just say for this particular epoch, which is epoch plus 1, I can display the loss that we got, and that I can just say loss dot item, print it out, and you can display it over there. So that's, and then again, same thing, you can go ahead and next step is to tune the parameters, where you can either change the learning rate, you can change the batch sizes, or you can test different optimizers and not just Adam that we have used for our optimize. You can go with SGD, so try those different things, and you will have a complete exercise where you have applied data augmentation to a data set and trained a fine-tuned model and experiment with hyperparameters to kind of check what is the impact of the on the performance of these models. So again, I hope you were able to follow along. If you have any questions, or if you're playing with some data set of your own or from Kaggle, let me know if you had any issues and I'll get back to you. Now to summarize, today we learned to apply data augmentation techniques for better model generalization. We developed practical skills in freezing, unfreezing layers and fine-tuning pre-trained models. And then we understood the effects of hyperparameters like learning rate and batch size on training outcomes. And finally, we built proficiency in evaluating and optimizing models for real-world image classification tasks. If you had any problems while implementing this or have any questions, let me know and I'll get back to you. Day 4, Transfer Learning in NLP. Let's talk about some of the popular pre-trained NLP models. We have BERT, which is bidirectional encoder representations from transformers. The architecture for this is transformer-based encoder model. The training tasks here include the masked language modeling or MLM. Next, we have the next sentence prediction, which is NSP. Applications here can be text classification, sentiment analysis, and question answering. Next, we have GPT, which is generative pre-trained transformer. The architecture here is transformer-based decoder model, and the training task is causal language modeling, which is predicting the next word. Applications here include text generation, summarization, and dialogue systems. Next, we have T5, which is text to text transfer transformer. This treats all NLP tasks as text to text transformations. Applications involve summarization, translation, and text classification. Then we have Roberta, or robustly optimized BERT. It removes next sentence prediction. It's pre-trained on a larger dataset with optimized training strategies, and applications include similar to BERT but with better performance on downstream tasks. Let's talk about tokenization and text preprocessing for fine-tuning NLP models. First, tokenization converts raw text into numerical representations. Types are the word piece tokenization used in BERT and byte pair encoding, which is BPE, which is used in GPT and Roberta. Next, text preprocessing. First, cleaning, where we remove unnecessary characters, example URLs, special symbols. Then we do normalization, where we convert text to lowercase and remove stop words if necessary. Next, we have tokenization, where you break text into tokens compatible with the pre-trained model. Let's talk about adapting pre-trained models for NLP tasks. Some of the common tasks here involve text classification, where you categorize text into predefined labels, example positive or negative sentiment. Then you do sentiment analysis that determine the sentiment polarity of text, example positive, neutral, or negative. And then you have summarization, where you generate concise summaries from lengthy text. Steps here are first you load the pre-trained model, add a task specific head, example classification layer, and then you fine tune the model on task specific data. Let's look at an hands-on exercise for today, where the objective is to fine-tune a pre-trained BERT or T5 model for sentiment analysis using Hugging Faces Transformer library. Then we pre-process the text data, tokenize it, and evaluate the model. So let's get started. So step one, start with a new file. Save it as, and call it day 4 underscore exercise. In here, I'm going to make sure that you have installed transformers and datasets. You can do that again by on your terminal by saying transformers and datasets. If you are directly jumping into this particular video, then you probably would want to do that by just going here to your folder and then add that. Once that's done, that's all that you need to start with. So let's go ahead and from transformers import auto tokenizer, and then I'm going to say auto model for sequence classification. That's what I'm going to use right here. And then I need the trainer and I need training arguments. Perfect. So once I have those, next step is also another thing I need is data sets, which we just added. So I'm going to say import load underscore dataset. That's the function that I need from there. So once I have that, let's load the IMDb dataset. So I'm going to say dataset equal to load dataset and pass it IMDb. So I have IMDb. Now let's go ahead and load the BERT tokenizer. I'm going to show you T5 too a little bit, but I'm not going to run that because this itself is going to take quite a lot of time, but you can run both of them if you have time in your hand. So I'm going to say from pre-trained, the one that I'm interested is BERT dash base dash uncased. So that's what I'm interested in. Next, I'm going to tokenize the data set. For that, I need a function. First one is called tokenize. The function is called tokenize underscore function. You can name it whatever you want because you're going to use it. Next, so I'll have examples as passed to it. I'm going to say return tokenizer dot of examples, and inside that we have text. So this is the IMDb database, so it has text parameters, and then inside that I'm going to say truncation equal to true. So I am saying that if you have something that is more than, for these parameters, if you have more than what you need, just truncate them. And I'm going to set the max length to 130/28, and anything more than that I will remove it. And also I'm going to say padding should also match to max length. So if your text is shorter, then add some padding, 128. So this will make sure that my data set is ready to be tokenized. So I'm going to say tokenized underscore data set equal to I'm going to say data sets equal to data set dot map the tokenized function. That's what it needs. And the second one it needs is it batched or not. So I'm going to say batched equal to true. Okay, perfect. So I have my tokenized data set. Now with this, I can prepare data for training. For that, I'm going to say tokenized data sets equal to tokenized data sets. I'm going to remove columns, which is the text one, since it's tokenized. Say text, I don't need that anymore. And same thing I'm going to say again, but this time I'm going to say from my tokenized, I want to rename my column, only one column, that's I'm going to say column label to labels, just to give an idea of how this works. Next I'm going to say tokenized data sets, and I'm going to say set the format. I need it for PyTorch, so I'm going to say set the format as torch. Next, now that is done, I'm going to get the trained data set that I can say get by tokenized data sets. Inside that there is trained data, and then I know you know what I'm doing. I want the test data set, so test data set equal to test. So I have my data sets available. Our next step is to load the pre-trained BERT model. To do that, I'm going to say model equal to auto model for sequence classification. From that, I'm going to say from pre-trained, the one that I am interested in is BERT dash base dash uncased. Next, I'm going to say another one is how many labels does it have. I'm going to say number of labels equal to 2. Set that. Perfect. That's good. Make sure they don't have any typos. Now, with that, let's go ahead and define the training arguments. So I'm going to say training underscore args equal to training arguments. I'm going to use this and put one at a time. First one I need is output directory, where in the same folder I want to save in a folder called as results. Next, I'm going to say evaluation strategy, eval underscore strategy equal to, I'll say epoch. Next, I'm going to say learning rate underscore rate equal to 2e minus 5. That's what I'm going to set. Next, I want the per underscore device train batch size equal to 16. And then same thing, per device eval batch size equal to same 16. Set that. So that's ready. Next, we need 3 more things. One more. First is number of train epochs, which is 3. I can reduce it just to reduce the time. Let's see what I think about that. Weight of decay equal to 0.01. And then I can set save underscore total underscore limit equal to 2. So I'm going to change this epoch to 1. 3 is ideal, but I just want to show you the final output quickly. So I'm going to set that to 1 right now. Next, what we have to do is fine tune the model. For that, I'm going to go here and I'm going to say from transformers, I want to import, or I already have import trainer. Anyways, ignore that. Go back here and say trainer equal to trainer, and say model equal to model. What else does it need? It needs our arguments, which is our training arguments that we have created, training args. Next thing that it needs is the data set. I'll say train data set equal to train data set. That's what we've created. Next, evaluation data set equal to, I called it, I think, test data set. Yes, test data set. Next, I need to get the processing class or tokenizer, that is tokenizer. Okay, there you go. So I have that ready. Now let's hit trainer dot train. It will be quick because I have only run for 1 epoch. You can increase this to as many as you want. Now next step is get the results or evaluation of this. So I'm going to say trainer dot evaluate, and I'll say print evaluation results is results. Of course, my 1 epoch might not be the best option here for evaluation, but you can try with multiple epochs and try how and see how it looks like. So I'm going to go ahead and run it just to see if I have any typos or something. Let's see, say Python day 4 Looks like it's running and we don't have any errors here. So let's give it some time and see how much time it takes, and we'll come back and record the rest. So as you can see, it took us probably around 20-25 minutes here to run the entire process of training and evaluation, and our evaluation results are here. Eval loss is 27%. We have eval runtime of 246.8751. Evaluation samples per second was 101, and evaluation steps per second was 6.331 with epoch of 1. Now if you do this for 3 different epochs, it'll probably take you 3 times the time, so that's why I ran it for once. But you can try it with 3 or multiple times and see how your evaluation results change. Now that kind of covers our fine-tuning a pre-trained BERT model. Now if I want to do something similar with a T5 model, what I can do is I can just show you quickly. So from transformers, I can import T5 tokenizer, and then I need T5 for conditional generation. So these are the libraries that I need. Now I'm going to load the T5 tokenizer and model. To do that, I'm going to say tokenizer equal to, that's our T5 tokenizer dot from pre-train. I'm going to pick up T5 dash small. Next, I am going to go ahead and get my model equal to T5 for conditional generation. From pre-trained, I'm going to get T5 dash small again for the model. So next, I'm going to tokenize the inputs with sentiment prompts. I can do that by saying creating a function called as preprocessed dash T5, pass it the examples, and those examples can then go ahead and go into input. I'm going to say classify sentiment, where I will pass my data by saying doc for doc in examples of text. This is again data from the IMDb. I have not imported the IMDb, but you've done it in the previous project, so you can use the same thing. But I'm going to go ahead and just give you the skeleton of that. So now my model inputs equal to tokenizer, and then to that I'll pass the inputs, and I'm going to say max length that I am interested for this equal to 128. Next I need to give, okay, this is, again I'm going to call this inputs instead of changing the other one, and then I'm going to say truncation equal to true. You know what this is for truncating if it's longer. And if I want to give a padding, so I can say padding is depending on the max length that we have. So I'm going to say max underscore length, so that will take care of my model inputs. Our next one is model inputs for labels. We got our features done. Now this is for the labels. I'm going to say equal to tokenizer, and inside this I'll pass my examples of labels that I have there. Next I am going to go ahead and say max underscore length of 16, and then I'm going to say same thing, truncation equal to true. Next I will give the padding equal to max length, max underscore length, and then to the end of it I will pass the input IDs of input underscore IDs. So that's how I can get my model inputs with labels. So once I have this, I am going to return this back to whoever called it. In this particular case, it's not the call, but it's actually the tokenized underscore T5 equal to, which needs my data set dot map, and this needs my process or pre process T5 and batched. So it will, I'll pass this function here that will run through this and get me the model inputs, and here I'm going to say batched equal to true. So this will give me my tokenized T5, and then you can follow the same process that we did for BERT and use the same and run and check how the evaluation turns out for the model. Let me know how that works.
If you have any questions, let me know. To summarize, today we gained hands-on experience in fine-tuning pre-trained transformers models for NLP tasks. We understood the role of tokenization and text pre-processing in preparing data for NLP models. And we learned to adapt models like BERT and T5 for text classification, sentiment analysis, and summarization. And we built some practical skills for evaluating and interpreting model performance on NLP datasets. If you have any problems with the implementation or have any questions, let me know and I'll get back to you. Day 5, Fine Tuning Techniques in NLP. So let's start with fine tuning methods for NLP task. So first we have the discriminative fine tuning, where different layers of a pre-trained model capture different types of information. The approach here is first use different learning rates for different layers of the model. Then lower learning rates for early layers, which is general features, and then higher the learning rates for later layers, which are task specific features. Next we have the slanted triangular learning rates, or STLR. Dynamically adjust learning rates during training to balance the exploration and convergence. The phases here are: first is a warm up, where you gradually increase the learning rate to promote exploration. Then you decay, which is slowly decrease the learning rate to ensure convergence. Use case here effective for fine tuning pre trained models like BERT and GPT. Next, let's talk about regularization and dropout for preventing overfitting in NLP models. For regularization, we have L1 regularization, which encourages sparsity by penalizing absolute weights. And then we have L2 regularization, which is also called as ridge, which penalizes large weights to improve generalization. Let's talk about dropout. Randomly drops units along with their connections during training, and it prevents over reliance on specific neurons, commonly used in transformer based models. Next, let's look at evaluating model performance with NLP specific metrics. So, some of the key metrics here are F1 score, harmonic mean of precision and recall. Is suitable for classification tasks with imbalanced datasets. Then we have the blue score, which evaluates the quality of generated text against reference text, and it's commonly used for translation and summarization tasks. We also have the rogue score, which measures overlap between generated and reference text and is used for summarization tasks. So let's jump into our hands-on exercise, where the objective today is to experiment with advanced fine-tuning techniques like STLR on an NLP model and evaluate its performance using the F1 score or the blue score. So let's get started. So to start, let's go ahead and create a new file, Python file, save it in day 5 dot or underscore ex.py. First, let's go ahead and import the necessary libraries. So I'm going to say import torch is the first one. Next, I'm going to say from torch dot utils dot data import data loader. That's what I need. Next, let's get from transformers. I'm going to import transformers. I'm going to import auto tokenizer. That's the first one that I need. Next, I want to get the auto model for sequence classification. For sequence classification. Next, I want to get the scheduler. So I'm going to say get underscore scheduler. Perfect. So I have the required libraries from transformers. Next, from data sets, I am going to import load dataset function. That's all I need right now. And from sklearn dot model underscore selection, I want to import train, test, and split. Perfect. Once I have that, next thing is from sklearn dot metrics, I'm going to import F1 score because we are going to use that. So F1 score. Perfect. So I have everything that I need. So first step is here to load dataset. So I'm going to say load dataset. Say dataset
equal to load underscore dataset, and we'll be using the IMDb sentiment analysis dataset. So it's MDB, that's what I'm going to use. Next, I'm going to say train underscore the text that I get, training text. Let's change the variables a little bit. Test text, x train, x test, y train, y test. That's what these are. Train underscore labels. I'm giving proper labels to these so we understand what they are. Again, test labels equal to, I'm going to call that train test split function, and inside here I'm going to, let me put it on the next line, I'm going to say data set. From my data set I can get the train text, that's what I'll get here, and then from my data set I also have train label. So I have my data set X and Y, which is my features and my labels. So next I'm going to go here and say test size that I want is 0.2 and random state equal to 42. Next step is tokenization. So I'm going to go ahead and say tokenization. For tokenization, I'm going to use the tokenizer that I have, initialized, which is my auto tokenizer. And to this I will pass, I'll say from pre-trained and pass the bird base dash uncased. Next step is to create our tokenized data function. So I'm going to say def tokenize underscore data, and it needs our text, it needs the labels, and it needs tokenizer comma max underscore length equal to 128. Once I have that, next step, let me move it all the way to the top so it's much more clear. So next step, I'm going to go ahead and get my encodings. I'm going to say encodings equal to tokenizer, and to that I'll pass my text, I'll pass my, I'll say the truncation to this is true. That means if it's longer than the max length, I want to truncate it. Next, say padding equal to true. If it's small, if it's shorter than the max length, then pad it. And then I'll specify max length equal to whatever was passed to me on the top, max length. So that's about the encoding. So we'll have the encodings. Once I have the encodings, what I'm going to do is I'm going to return my object with input IDs to be encodings of input IDs, input underscore IDs. Next, I will say I also need to pass the attention mask. So I'm going to say attention underscore mask. For this comes from, again, encodings has it. So I say encodings of attention underscore mask. Next, I need labels. Labels are available in labels. We don't do much for that, so that will return back. So to call this function, now first I need to create my train data equal to tokenize underscore data and pass it what all it needs. First is the train text. Next I will pass the train labels, and then I'll pass the tokenizer. Next, for my similar thing for my test data, say test data, tokenize data, and then it needs test text, it needs test labels, and it needs the tokenizer. So everything is here, perfect. Now next step is to create the IMDb dataset class. So for that I'm going to first move all the way to the top and say class IMDb dataset, and to that I am going to say torch dot utils, since I have not imported our data set directly. So I'm going to say data dot dataset. If you import this, you just can put dataset here. Next I'm going to say define the initializer function underscore, which needs self and data, and this function will have self dot input underscore IDs. will be coming from data input IDs. Next, I'm going to say self dot attention mask. Now this will be coming from again data attention underscore mask. Next, I need labels. So I'm going to say self dot labels equal to data of labels. So I have all my parameters for my initializer function. Next, I'm going to define another function called as len, which will give me the length of the object. So I'm going to say self, and here I am going to say return length of self dot label. So this is the length for the labels that I'm returning back. Next thing is I want to get the item, so I'll create a get item function. Get item function. Now this takes self and index, so idx I'll call it in short, and here I am going to return input IDs are the same thing. Input IDs, attention mask, and labels is what I want have to return back. So I'm going to say input IDs is torch dot tensor self dot input underscore IDs at index idx. So that will get my input IDs. Next, I want to give the attention mask. So I'm going to say attention underscore mask is again torch dot tensor, and to tensor I'll say self dot attention mask, and then attention mask of the index. Perfect. So that's done. And finally, as you know, labels. So for labels, I'll say torch dot tensor, and then to this I'll say self dot labels at a particular index. Perfect. So I have I've returned everything that I need for a particular item with the index. Our next step, let's go outside and create the train data set. This will be IMDb. I'm going to call that class data set and pass it my train data. Now similarly for test data set, I am going to say IMDb dataset and pass it the test data. So this will give me my train dataset and test dataset. Next thing, the loaders, data loaders. So I'm going to say train underscore loader equal to data loader, and to this I need to pass my train dataset that I have. I'll say batch size. It does processing in batches, so I'm going to set something around the line of 16. Shuffle, I'm going to set that to true. By default it's false, so you don't specify it, it will be false. So I can show it here because I don't do shuffling for test. So I say data loader test data set, and I just have to say batch size equal to 16. I don't have to specify shuffle because, as I mentioned, by default it's false. Now that takes care of our step number 2, which was tokenization. Now the next step is to load the pre-trained model. So load pre-trained model. In this particular case, I'm going to say model equal to auto model. If you remember, we have imported this, and from pre-trained I am going to get the same one that we got earlier, bird base uncased. Perfect. So I have my model. Also I can pass the number of labels that I have, so I can say number of labels equal to 2 here. Perfect. So that gets my model. Our next step is to define the optimizer and the STLR scheduler. So I'll say define optimizer and STLR schedulers. For that we have the get scheduler that we've imported. So first, for optimizer, I am going to say torch dot optim, since I have not imported optim, torch dot optim dot Adam is what I'm going to use, and inside this the parameters that Adam needs are, first one is model dot parameters. Okay, the next thing it needs is the learning rate, which is 2e minus 5. Perfect. So that's pretty small. Perfect. Next, let's go ahead and define slanted triangular learning rate, which is also called as STLR scheduler. Okay. Now for this, first I'm going to get the number of training steps. Now that, as you are already familiar with, we can get from train underscore loader and assume that it's 3 epochs. So I'm going to say times 3. Next, I'm going to get the warm-up steps. This one I'll assume this one I'm going to say 10% of the warm-up. So I'm going to say int 0.1 times number of training steps. Next, I'm going to create the scheduler. Now, to create the scheduler, I am going to say scheduler equal to get scheduler, the function that we wrote above. And the first thing it needs is the name of the scheduler. And as I mentioned, I want to use slanted triangular scheduler. Perfect. Next, I'm going to say optimizer equal to optimizer. Next, I'm going to say number of warm-up steps equal to warm-up steps. And next parameter it needs is number of training steps. Number of training steps equal to, we have that to number of training steps. So we got that from number of training steps and warm-up steps from here, and that's what we passed to our scheduler. Now next step is to write the training loop. So I'm going to go ahead and say training loop. Now for training loop, first I need to specify what device I am. If do I have a CUDA device with GPUs or do I have a CPU? So torch dot device, in this particular case I'll say use CUDA if torch dot CUDA dot is underscore available. Now this is very helpful when you're running this stuff on cloud. So I'm going to say this. So again, close this here and not here, else I'm going to use CPU. Perfect. So next I'm going to say model dot to device. So the device that I'm using. Perfect. Next step is to actually write the training model. So I'm going to say train underscore model function. Now in here, first step, as you know, let me move it all the way to the top. First step is to put the model in the training mode. So that's by calling the train function. Now for each and every epoch, so I'm going to say epoch in range of, I'm going to run it 3 times. So 3 epochs. And then for batch in train loader, so for each and every batch inside the train loader, I'm going to say batch equal to, I'm going to create some variables here, k v dot to device for k comma v in batch dot items. Perfect. So that will give me my batch object. Next I'm going to do outputs equal to model of star star batch. That will give my outputs. Next I want to get my loss function, which is outputs dot loss. And next step is our backward propagation. So I'm going to say loss dot backward. Next step is we want to get our optimizer step dot step this up. Next optimizer. Next I'm going to do the scheduler. So this is a special stuff. Just because of the SLTR that we have, we need to also make sure scheduler is 1-up. Next I'm going to say optimizer dot 0 grad. Usually I do it at the start, but it doesn't matter at the end of it or before the start. You have to make sure that you zero out the gradients. Next I'm going to go ahead and say train underscore model, call that function. Perfect. So that will put my model in training. Next step is after everything is done here, I'm going to go ahead and evaluate model using F1 score. Now to do that, first thing that I'll do is I'll put the model in the evaluation mode by calling model.eval. Then I'm going to say all underscore preds, all predictions, comma, all of labels equal to empty, comma, empty. So I'm initializing an empty list for both of these. Move this up. And now I'm going to go ahead with my loop. First I'm going to say with torch dot no grad for optimization. Remove the gradients. I am going to say run my for batch in test loader. Again, same thing what we did with training. I'm going to first get my batch, or I can go ahead and copy most of stuff from here. I need batch, I need outputs, and then I need pred. So I don't. So the batch equal to k dot v dot to device for kv in batch dot items. Next one, I'm going to say outputs equal to model of batch. Next, I need the preds equal to torch dot argmax of outputs dot logits. So that will give me my, and also I need one more parameter is dim equal to -1. So this will give me my predictions. Now that I have predictions, I'm going to say all underscore preds that I've created above. I'll say extend preds dot cpu dot numpy. So this will add my pred objects into my list that I've created above. Next, I'm going to say all labels. Now to do the same thing for labels dot extend, and from batch this time I can get my labels dot cpu dot numpy. So this will give me my labels, add to my list. So once I have that, next I'm ready for my f1 score. F1 equal to f1 score. I'll pass my all labels. Next I'll pass my preds, all underscore preds, and then I'll say average that I want is weighted. Average weighted, so that's good. Next, let's go ahead and print our f1 score. F1 score, that is f1.4 f. So that should give me my f1 score for this model. Now the next thing is, I also mentioned that we're going to get f1 score or blue score. We already got f1 score. We don't have to get the blue score. No, just kidding. What we'll do is next we'll get the blue score. For that, I am going to, so from my Sacre Blue library, I am going to import BLEU. So that's where score calculation can be done using this function. So first thing I need to do is, let's show me an example. Let me show you an example of example, reference, and hypothesis of how it looks like. So first I have my references. These are different texts that are available. I'm just going to put them in list. So this is, so first I'm going to say this, just some random text. This is a, let's say test sentence, and then, okay, I spelled it wrong, and then I'll put another item in this list. It's always good to have multiple. You can add as many as you want. This is a sample sentence, again same thing, and these are the nested list of references. Next thing that I want is the list of hypotheses that I have. So I'm going to say hypothesis equal to, this is a test. So this is the list of hypotheses. Now next I'm going to go ahead and initialize the blue scorer. So I say blue equal to blue, and this will initialize my blue. Now let's calculate blue. So I say blue underscore score equal to blue dot, the function that I call for this is corpus. I think we used it earlier in the class, corpus score, and I'll pass this hypothesis and references. So earlier in one of the weeks we used blue, I remember, and that's why this is where it's coming from. And then print. I don't use it that much, but it's good to know how to use it if you have to. Score is blue score, and then I'll say 0.2 f to display it. So there you go. So our entire project is done, where we experiment with advanced fine-tuning techniques using HTLR on an NLP model and evaluate its performance using F1 score or blue score. So let's go ahead and run this. It's going to take some time, so I'm going to run it and then wait for it to complete. So let's go ahead and run this. I'm going to say Python day 5 And looks like I have an issue here. Number of training steps. Looks like I've used it too many times. This is warm up steps, and I'll say warm up. Number of warm up steps equal to warm up steps. Perfect. Let's try it again. Go ahead and clear it out. So it's running. I guess no more errors. So that's good sign. So I'll wait for a little while. It has some warnings here and there. You can read through them and try to fix them. There's always some or other updates which makes your code a little bit old-fashioned or kind of deprecated. So try to look at these and then fix to the latest version. So this is at the time of recording. These are the different warnings that I'm seeing. So I'm gonna wait for it to complete and then I'll start recording again. So there you go. So it gave me my warnings and everything. And at the end, after around a long time, we got our F1 score of 0.3477 and a blue score of 46.31. I hope you were able to follow along and get some similar results. If not, you can always try to increase the epochs or reduce the epochs to run the code faster and get experience from how these steps work. So if you have any questions, let me know in the messages. To summarize, today we learned to implement and optimize fine tuning methods for NLP tasks. We understood the role of learning rate scheduling, which is STLR, in transfer learning. And we gained practical experience in evaluating NLP models using advanced metrics. And finally, we built some skills in preventing overfitting through regularization and dropout. So if you had any issues or problems implementing this or have any questions regarding this topic, let me know in the messages and I'll get back to you. Day 6, Domain Adaptation and Transfer Learning Challenges. So let's start with understanding domain adaptation and handling domain specific data. Now, what is domain adaptation? Domain adaptation involves transferring a model trained on one domain, which is the source domain, to perform tasks in a different domain, which is the target domain. Example can be source domain is a general news articles and target domain is medical text. Now, why domain adaptation? Many real world tasks involve domain specific data, example legal, medical, and financial. We have pre trained models on general data sets, example BERT, might not perform optimally without adaptation. Now, steps in domain adaptation involve first, you fine tune the pre trained model on a domain specific dataset. Then, you incorporate domain specific embeddings or vocabulary. Apply additional pre training on the domain data if necessary. Now, what are the challenges in transfer learning? First is the data mismatch. The source domain may not represent the target domain adequately. Example can be general text like Wikipedia versus technical medical jargon. Then we have catastrophic forgetting. During fine tuning, the model may forget the knowledge learned from the source domain. Then we have computational constraints. Fine tuning large pre trained models, example BERT, GPT, requires significant computational resources. Let's talk about strategies to address these challenges. Transfer learning from related domains. Fine tune on an intermediate domain dataset before adapting to the target domain. Data augmentation. Generate synthetic domain specific data to augment the target dataset. Example can be use paraphrasing techniques to increase dataset diversity. Next, domain specific embeddings. Use pre trained embeddings tailored to the target domain. Example, BioBERT for biomedical data or LegalBERT for legal text. Let's talk about today's hands on exercise. Today, the objective is to fine tune a pre trained model on a domain specific dataset, example BERT for medical text classification, and experiment with domain specific embeddings. Let's get started. So first step is to go ahead, create a new file, Python file. I'm going to save it as day6 underscore ex.py. And here, first thing that you need is make sure that you have your transformers and datasets installed. So for that, the command on terminal is again install transformers, because a lot of people complained from yesterday that it was not working for them, and this is kind of solved the problem. So most of the times it's something that is missing, and if your terminal should tell you, but if not, this is how you do it. Next, let's write the code. From datasets, I want to import load underscore dataset. And then I am going to load the PubMed 20K RCT dataset. Now this is a dataset that is really big, and if you want to train this, it can't be done on a simple computer. You need a very powerful machine or somewhere on the cloud that you can run it. So I'm not going to run this project, but I'm going to just show you the steps on how to do this. So first, let's get the dataset equal to load underscore dataset. Dataset is PubMed underscore RCT, and it's the variation is 20K underscore RCT. Okay, so this will have all our medical data in here. Next, I'm going to say print dataset train of 0. If you want to check how the dataset looks like, you can just display that. Next thing is to pre-process the data. Now to pre-process data, I'm going to go ahead and say from transformers import auto tokenizer. Now this I can say load BERT tokenizer. For that I'm going to say tokenizer equal to auto tokenizer dot from pre-trained, and I am going to say BERT dash base dash uncased. So that's good. So I have my tokenizer. Next, let's create the function for pre-process underscore data. Examples is what I get as input here, and this will return back our tokenizer of, in my examples dataset that I have, it has text inside there, and then I'll say truncation equal to true if it's too long. Then the max length that I'm going to say, padding in this case equal to max underscore length. So that brings us to our final parameter, which is what is the max length that I want to give for a data set like this. I'll say 512. Okay, so that's my, that will give me, that's my pre-process data function. Now to call it, first I need my tokenized underscore datasets equal to dataset dot map, and here we will call that function pre-process data. I give it as a input, and I'll say batched equal to true. Next, again for tokenized datasets equal to tokenized datasets dot I'm going to rename a column, which is my label column, to labels, so it matches the standard. Okay, next I'm going to go ahead and say tokenized datasets dot set underscore format. I want to set it for PyTorch, so I'm going to say torch. Perfect, so that's done. Next step is to load the pre-trained BERT or domain specific model, in your case whatever domain you're working with, but here since we are working with the BERT specific domain, I'm going to say from transformers import our favorite one, auto model for sequence classification. Perfect. So to get the model, I'll say model equal to auto model for sequence classification dot from pre-trained. Inside this, again same thing, BERT dash base dash uncased, and then number of labels, I'm going to say number of labels equal to 5 because it has 5 different classes. So that's why I specified that. Next step is let's say if you want to do, instead of this, as I mentioned, if you want to do domain specific model, which is for BioBird, if you want to do that, here I'm gonna comment it out. Model equal to auto sequence for classifier. Here the one that we use is, let's say remote this, or DMIS dash lab slash, they've created this from BioBird itself and they've pre-trained it, base dash cased dash v 1.1. so this is the most latest one that I have during the time of the recording. There might be better ones. Number of labels equal to 5. Perfect. Our next step is to fine-tune the model. To fine-tune the model, again from transformers, I am going to import the training arguments, because I need to create the variable called as training underscore args equal to training arguments, and in here I'll pass my different training arguments. The first one, as you familiar with, output directory. Where do you want it? I'm going to say dot slash results. Next is the evaluation strategy or eval strategy is equal to epoch. We've been using that forever now. Next is the learning rate, learning underscore rate equal to 2e minus 5. Then next thing is per underscore device. I'll first use the training one equal to 16. Next, per underscore device, the eval batch size equal to 16. Next, I'm going to say number of epochs that I want to run. Again, depending on how better you want the solution, more epochs you run, but depends again of what processors you have have available. Next is my weight decay. I want it to be 0.01. So perfect. So that takes care of my training arguments. Now I need to create my trainer. So I'm going to say from transformers again, import trainer. Now this trainer, I'm going to say trainer equal to trainer of, so in the argument that we need is first it needs the model. So which is the model? We have already created the model. I'm going to pass that model to it. Next, my arguments, which is my training arguments, I'll pass that. Next, I want to give the training data set. So we have the data set. So I'm going to say tokenized data sets from above that we've created. I'm going to pass the training data set here. Next, I need the, why did I copy paste it? Because it's eval or test, not test, eval data set, tokenized data sets, and inside here I get validation object. Next, I'm going to say processing cell, or let's use tokenizer because that's the old-fashioned one, or you can use the latest one. Say tokenizer, and then I'm going to say trainer dot train. So this will train my model, and we are ready to evaluate the model. Now to evaluate the model, we can just say results equal to trainer dot evaluate. Just make it simple on you. You can just say trainer dot evaluate, or just follow the same steps that we have before, and I can say evaluation results and pass the results out. So easy breezy. Next thing, so now that we're done with this, like next thing that I want to talk about is addressing the data mismatch with augmentation. So you can use paraphrasing or synonym substitution to augment the data set. So for that, I can just first I need random, just an idea of how to use it. So if I want to augment, especially medical data, augment text, which comes with text. In here, I'm going to say synonyms. Now I have some synonyms based on some of the things, some of the diseases that are there. So I'm going to get that. So for example, cancer is tumor, malignancy, that's what it means. You have cancer, study is research, experiment. So these are the basic ones that I've just used here, just to give you an idea of how it works. Next, I'm going to say words equal to text dot split. So whatever I get, I am splitting those words because I want to create a list of new words, and that is random dot choice of synonyms of word if, that is, if word in synonyms, in synonym, did I spell it right? In synonyms, else word for, so if there's not there, then I'm going to say for word in words, else for word in words. So I'm going to take it from the word. So that's how you create the new words. And now I'm going to finally return everything. I'll put a space in between and join all the new words and send them. So there you go. So we have our data augmentation. Now if you want to apply this augmentation, you can create an augmented underscore data, and then to that I'll say augment text, call that, and then pass that data set that we have, which is sample of text, again for sample in data set in the training object. Let's say train. So, and then you can go ahead and print and check this, how it looks like. You can just say augmented data. You can just see the first 5 of them. If you want to check, you can print and check this out. So this is the entire code where we are fine tuning a pre-trained model or domain specific data. And here we are using the BERT for medical text classification, and that's why we are using this BioBERT base case model, and then experiment with domain specific embedding. So we looked at different segments, whereas we also look for data augmentation using synonyms into the existing data set that we have. So I hope you were able to follow along, and if you have any questions on this code, let me know. If you run this somewhere, let me know how was the results or how well it did. So to summarize, today we understood the concept of domain adaptation and its importance in real world tasks. We learned how to adapt pre-trained models like BERT for domain-specific datasets, and we gained some practical experience in addressing challenges like catastrophic forgetting and data mismatch. And we built skills in evaluating models trained on specialized domains using domain-specific metrics. If you have any issues or questions, let me know. And if you have any questions, leave them in the messages and I'll get back to you. So, welcome to the end of the week 13. Today, day 7, we are going to learn about transfer learning project where we'll be fine tuning for a custom task. Now, first, let's talk about applying transfer learning techniques to a custom project. The project objective is leverage transfer learning to solve a specific task in either computer vision or NLP. Fine tune a pre trained model for domain specific data to achieve this optimal performance. Now, steps that we'll be following today is first dataset selection. For computer vision, we can pick either custom image dataset, example animal species classification, and for NLP, we can pick text classification task, example sentiment analysis or product categorization. For pre-trained model, we will use computer vision models like ResNet, EfficientNet, or MobileNet, and for NLP, we'll use BERT, Roberta, or T5. Next, fine-tuning techniques. We'll be doing regularization, hyperparameter tuning, data augmentation, discriminative learning rates. Let's jump into analyzing the fine-tuning techniques. Now, the fine-tuning process involves freeze the pre-trained layers and train the custom classifier head first. Then we unfreeze some pre-trained layers for domain adaptation, and then gradually reduce the learning rate to avoid the catastrophic forgetting. Some of the key techniques we'll be using can be regularization. We use dropout, L2 regularization to prevent overfitting. For data augmentation, you can enhance diversity in training data, rotation cropping, or text paraphrasing. And hyperparameter tuning, you can experiment with learning rate, batch size, and optimizer. So let's jump into documenting results and baseline comparisons. Now, the steps that involved here is first evaluate the baseline performance of the pre-trained model without fine-tuning. Then you can track performance improvements after the fine-tuning and hyperparameter optimization. And then use metrics like accuracy, F1 score, blue, or rock AUC to compare the results. So let's jump into the hands-on project where the objective again is to fine-tune a pre-trained model, ResNet for computer vision or BERT for NLP, to solve a custom task and evaluate and document results against a baseline. So let's get started. So let's go ahead and start with computer vision example where the dataset that will be focused on either Kaggle cats versus dogs dataset. You can download from Kaggle or use an equivalent dataset. And for NLP example, you can use the Amazon review sentiment dataset, which is pretty good to start for NLP project. Now, first, I'm going to go ahead and start with the Python file. Let's call it day 7 underscore CV, which is for computer vision. And at the same time, I'm going to do day 7 underscore NLP. So both of them side by side. I'll do it one step at a time because it's the same step. So first step is, as you know, loading and pre-processing the data. So for computer vision, I'm going to say from TensorFlow dot keras dot pre-processing dot image. I am going to import image data generator. So that's the first thing. Now to get the first what we are going to do is we want to do some data augmentation and pre-processing, because you might not have enough data. There's never enough data in this world. So for that, I'm going to say data gen equal to image data generator, and to this I'm going to say I want to rescale 1 divide by 1 dot divide by 255. So that will kind of put everything from 0 to 1. Next I'm going to say rotation underscore range equal to 20 degrees. Next I want to say width shift range equal to around 0.2. Same thing I can do for height. I can say height underscore shift underscore range equal to 0.2. Next I can say shear underscore range equal to 0.2. Next I'm going to say zoom in zoom out range equal to 0.2. Next I can say flip, so horizontal underscore flip equal to true. Next finally I can also say validation underscore split from this data set equal to 2080, so 20%. So that kind of takes care of our data gen. Our next thing, let's go ahead and take the data that we have. So wherever data you have saved, whatever data you decided to use, what you can do is first call the data gen dot flow underscore from underscore directory. Now depending on where you've saved, I usually like to save it in my same folder with dot slash data, something like that. So here give the path to the data set that you have. So that's what you do. Next I'm going to say target underscore size equal to 224 comma 224. Next I'm going to say batch underscore size. I want to do 32 images at a time, so 32. And then I'm going to say class underscore mode equal to binary in this case. Next I'm going to say subset, so either cat or dog, so that's for binary. Subset equal to training. So there you go. So that kind of takes care of my training data. Now if you want to do the validation data, I can do the same thing here and say that this is my validation data, and then data gen flow from directory, again part to the dataset, training dataset that you have, training size, batch size, class mode, subset. Instead of training, it's validation this time. So perfect. So this kind of gets our, we have loaded the data and pre-processed it. Now this is for computer vision. How about for NLP? Now if you're taking data from Amazon, let's say you took from there, what I can do is I can say load underscore data set, because this is available on Hugging Face. So from transformers import auto tokenizer, and the data set I can get by saying load underscore data set. As I mentioned, Amazon, it's called Amazon underscore, unless they changed it recently, Amazon underscore polarity. Next I'm going to pre-process the text, so I'm going to say tokenizer equal to auto tokenizer dot from pre-trained. I'm going to use BERT base dash uncased. Perfect. So you have that. Next I'm going to define my pre-process data function, pre-process underscore data, and pass it examples, and at the end of it I'm going to say return tokenizer and pass it examples of the, in this particular case the name is content, so I'll make sure it's content, and then truncation equal to true. You know what that is. So if it's more, then truncate. If less, then use the max. Let me just max underscore length. And for this, the max length that I would recommend is same as what we used earlier. Max underscore length equal to 512. Longer the better. So this will pre-process my data. Now to actually run that, I'm going to say tokenized underscore data sets equal to data set dot map and pass it that function preprocessed data, and the next one is batched equal to true. Perfect. So this is our pre-processing, loading and pre-processing data for NLP. Now you want to load a pre-trained model for computer vision. So I'm going to go jump into that, and here I can say from TensorFlow dot TensorFlow dot keras dot applications. I can import. Sorry, I did this mistake before too. Applications import ResNet50, and you know how much time that takes to run. From TensorFlow dot keras dot models, I am going to import model, and then from TensorFlow dot keras dot layers, I am going to import dense and global. Show up, please. Global average pooling 2D. Okay, so these are my libraries or functions that I need. Now that I have this, I'm going to go below here, and first I'm going to load the pre-trained ResNet50. So for that, I'm going to say base underscore model equal to ResNet50 weights equal to image net. Next, I'm going to say include the top equal to false. I don't need those. Next, I'm going to say input underscore shape for this, which, as you remember, it's 2 to 4, 2 to 4, comma 3 classes. Perfect. So I have my base model. Next, I'm going to go ahead and freeze the base models from what you remember for layer in base underscore model dot layers. Oops, layers here. I'm going to say layer dot trainable equal to false. This will freeze the different layers. Now I'm going to do is add a custom head. For that, I can say x equal to, use my global average pooling 2D that I've imported. In here, I'm going to pass the base underscore model dot output to it. So this will be added on top. This is my custom head that I've added. So output in this case will be, again I will use dense and say one class activation model equal activation function that I want to use is sigmoid, and then pass x to it, top of x. So this is my binary classification NLP project. Next, I'm going to say model equal to model of inputs equal to base model dot input, and my outputs equal to the output. Perfect. So I have that. Next, let's go do the same thing in for NLP. For here, I am going to, it's much more easier. I'm going to just say from transformers, I am going to import auto model for sequence classification. There you go. That's what I'm going to use. And then now I can just say model equal to auto model for sequence classification dot from pre-trained. I'm going to use our favorite one, which is BERT dash base dash uncased, and then I will specify the number of labels here equal to 2 for 2 classes. Perfect. So that's done. Now next step is to train the model. So for training the model, I'm going to go back to my computer vision class. Here, I'm just going to start here from, for first, I'm going to go ahead and compile the model. So I'm going to say compile, and then pass optimizer equal to Adam. Let's say loss equal to binary underscore cross entropy, and then metrics that I want to use is accuracy. So that will compile my model. Now to train the model, I'm going to say history equal to model dot fit, and inside here I'll pass the train data. I have the validation underscore data equal to val underscore data, and then the number of epochs that I want to run it for is 10. Since I don't have the data, I can specify what I want, right? Now, similarly for my NLP project, here I am going to first from transformers, I am going to import trainer and training arguments. Okay, so once that is done, I'm going to go ahead and say training underscore arguments equal to training arguments, and to this I'll pass all the things that we need. First is output directory, which is dot slash results. Next is my eval strategy, which is epoch. Next is my learning rate, which is 2e minus 5, enough decimal places. And next I want to give per underscore device train batch size equal to 16 and per device eval batch size equal to 16. Next I'm going to say number of training epochs equal to 3, and then I'll say weight of decay equal to 0.01. Perfect. Next, let's create the trainer. So I'm going to say trainer equal to trainer model equal to model. Then we need to give the arguments equal to training arguments. Next, we need to give train data set equal to tokenized data sets of train. Next, I'm going to say after that evaluation, not test data set, eval data set equal to, I do that mistake quite a lot where I will provide test data set, whereas it's eval data set and it will give me an error. Test, and then finally tokenizer or processing class is tokenizer. So depending on which version you're running, you can specify either tokenizer as the input or processing class. Next thing, I'm going to go ahead and say trainer dot train. So this will train my model. Next step for both of them is to evaluate and document the results. So I'm going to go ahead in my first, for my computer vision, I say validation loss, comma validation accuracy equal to model dot evaluate is the function, that's the function, evaluate, and then I'll pass validation data to it. Next I'm going to print validation accuracy is val underscore, oops, I think I forgot F, and that's why val underscore accuracy. So this will give me my validation accuracy. Now I want to do the same for NLP. I'll just say results equal to trainer dot evaluate, call that function. Next I can just say print evaluation results is results. So this will give me my evaluation results. So I've done both with computer vision and with the NLP task. So both are done. Now, next thing of this is you have to document with baseline performance without fine tuning how it works. You then do some post fine tuning performance where you can look for accuracy, F1 score, and blue, etc. And then you can document the impact of data augmentation, hyperparameters, tuning, and regularization on top of these projects that you've done. So the expected outcomes for these projects, you have to build a fine-tuned model for custom tasks in both computer vision and NLP. And then you analyze the impact of fine-tuning techniques on model performance, and then finally you document the result and compare performance against a baseline, and you can use that as a project to show what you have done during this particular project. I hope you were able to follow along in both of them, and if you get an opportunity to run it, let me know how it goes and in the messages. And if you had any issues and you want help with that, let me know too. I can get on the messages and get back to you on your questions. So to summarize, today we gained hands-on experience in applying transfer learning for real-world tasks. We developed practical skills in fine-tuning pre-trained models for domain-specific problems, and we learned how to evaluate and optimize models using advanced techniques. And we built expertise in documenting the entire workflow for professional use. I hope it was helpful, and if you have any questions or issues implementing this, let me know in the messaging and I'll get back to you.
Before we dive into tools, models, and architectures, it's important to reset how we think about AI engineering. Many people still prepare for AI roles using mental models from 2020, when training a model in a notebook was often enough. But the role has evolved significantly. AI has moved from experiments to mission critical products, and expectations have changed along with it. This lecture explains why that shift happened and what it means for you. Understanding this evolution will help you avoid outdated learning paths and focus on the skills that actually matter for landing an AI engineer job in 2026. In this lecture, we're going to look at how AI engineering has changed from 2020 to 2026. This shift is not subtle. It fundamentally changes what companies expect from AI engineers. We'll compare how AI work was typically done in the past versus how it's done today, and we'll examine why those changes happened. By the end of this lecture, you should have a clear understanding of what modern AI engineering really means, and why many traditional AI learning paths no longer lead to jobs. This context will guide everything else you learn in this course. In 2020, AI engineering was heavily focused on models. Most work happened in notebooks, using static datasets and offline training workflows. Success was often measured by accuracy, loss curves, or benchmark scores. Once a model was trained, it was frequently handed off to another team for deployment. AI engineers had limited ownership of production systems, monitoring, or long-term performance. Many models worked well in controlled environments, but struggled in the real world. This approach made sense when AI was experimental, but as AI moved into real products, these limitations became impossible to ignore. The typical AI stack in 2020 was relatively simple. It usually consisted of Jupyter notebooks, libraries like scikit-learn, TensorFlow, or PyTorch, and a fixed dataset stored locally or in cloud storage. Training was done offline, and deployment, if it happened at all, was often manual. Monitoring after deployment was minimal or non-existent. If performance degraded, teams often didn't notice until users complained. This stack was optimized for experimentation and research, not for reliability, scale, or long-term maintenance. As AI adoption grew, these limitations became a major bottleneck. The shift away from the 2020 model didn't happen by accident. As AI systems were deployed into real products, teams started encountering serious issues. Models broke when data distributions changed. User behavior evolved faster than retraining cycles. Costs increased as systems scaled. At the same time, businesses began relying on AI for critical decisions, which raised expectations around reliability and accountability. AI could no longer be treated as a one-time experiment. These pressures forced a change. AI engineering had to evolve from isolated model development into full system ownership. By 2026, AI engineering looks very different. AI engineers are now responsible for entire systems, not just models. That includes how data is collected, how models and prompts are used, how outputs are evaluated, and how systems behave over time. AI is deeply embedded into products, often operating in real time and at scale. Engineers are expected to think about reliability, failure modes, and user impact from day one. This shift means AI engineers must combine strong engineering fundamentals with an understanding of modern AI systems and business constraints. The modern AI stack reflects these new responsibilities. Instead of just training models, engineers now work with LLM APIs and open source models, retrieval-augmented generation pipelines, and vector databases. Systems often include tools, memory, and agentic workflows. APIs and microservices are standard, and monitoring and evaluation are continuous rather than optional. Feedback loops are built directly into systems to support iteration and improvement. This stack is more complex, but it enables AI systems to be reliable, adaptable, and production ready, qualities companies now expect by default. The most important shift to understand is this: AI is no longer a single model. Modern AI solutions are systems composed of many parts: data pipelines, models, prompts, tools, memory, evaluation, and monitoring. Each component affects overall performance. As a result, engineering decisions matter just as much as algorithm choice. A slightly weaker model in a well-designed system often outperforms a stronger model in a fragile one. This is why reliability, observability, and system design are now core AI engineering skills. AI engineer interviews have evolved alongside the role itself. Companies now focus less on memorizing algorithms and more on how you think. Interviewers want to see how you design systems, reason about trade-offs, and handle failure scenarios. System design interviews for AI are increasingly common. You may be asked to design an end-to-end AI system and explain your decisions clearly. Communication matters more than ever. Being able to explain why you chose a certain approach is often more important than the approach itself. Modern AI engineers need a broader skill set than ever before. Strong software engineering fundamentals are essential. You must understand Gen AI systems, deployment patterns, and evaluation techniques. You also need awareness of cost, latency, and scalability trade-offs. Importantly, these skills are interconnected. You can't treat modeling, infrastructure, and evaluation as separate concerns anymore. This course is designed to help you develop this integrated skill set, one that reflects how AI engineering actually works in 2026. For learners and job seekers, this shift has big implications. Following outdated tutorials or focusing only on models is no longer enough. To be competitive, you must think like an engineer who owns systems, not experiments. Your projects need to reflect real-world complexity. Your interview answers need to demonstrate reasoning and clarity, and your learning path must align with modern expectations. This course is structured around these realities. So you're preparing for the job as it exists today, not as it existed years ago. Now that you understand how AI engineering has evolved, we're ready to explore the tools and systems that define modern AI work. In the next lectures, we'll look at LLM APIs versus open source models, prompt engineering versus prompt programming, and the core architectures behind modern Gen AI systems. You'll start moving from theory into hands-on system building, learning not just what these tools are, but how and when to use them effectively. This is where modern AI engineering truly begins. Before choosing tools or architectures, every AI engineer needs to understand one of the most important decisions in modern AI systems: whether to use hosted LLM APIs or open source models. This decision shows up in interviews, system design discussions, and real production work. There is no universally correct answer. What matters is your ability to reason about trade-offs: cost, performance, control, privacy, and speed. In this lecture, we'll compare LLM APIs and open source models from an engineering perspective. The goal is not to promote one over the other, but to help you think clearly and make decisions you can justify in real-world systems. In this lecture, we'll explore the two dominant ways teams use large language models today: hosted LLM APIs and self-hosted open source models. You'll learn what each approach offers, where it excels, and where it falls short. More importantly, you'll learn how engineers decide between them based on real constraints, not hype or personal preference. By the end of this lecture, you should be able to explain these trade-offs clearly, both in interviews and in system design discussions. This kind of reasoning is a key skill for AI engineers in 2026. LLM APIs provide access to powerful language models through hosted services. Instead of training or hosting models yourself, You send requests to an external provider and receive responses. The provider manages infrastructure, scaling, updates, and reliability. This approach allows teams to move quickly, especially early in a product's life cycle. You don't need GPUs, model optimization expertise, or complex deployment pipelines. For many teams, LLM APIs are the fastest way to turn an idea into a working AI feature. However, this convenience comes with trade-offs, which we'll explore in the following slides. One of the biggest advantages of LLM APIs is speed. Teams can ship AI-powered features in days instead of months. There's no infrastructure to manage, and model quality is typically very high out of the box. Providers continuously improve their models, so performance often increases without any effort on your part. LLM APIs also come with mature tooling, documentation, and developer ecosystems, which lowers the barrier to entry. For startups, small teams, or early prototypes, APIs are often the most practical choice. They allow engineers to focus on product logic rather than model maintenance. Despite their convenience, LLM APIs have important limitations. Costs can grow quickly as usage scales, especially for high-volume or latency-sensitive applications. You also have limited control over the model's internal behavior, training data, and update schedule. Data privacy and compliance can be concerns, particularly in regulated industries. There's also the risk of vendor lock-in. Your system becomes dependent on an external provider's availability, pricing, and policies. As an AI engineer, it's important to recognize these trade-offs early and plan for them as systems mature. Open source language models take a very different approach. Instead of calling an external API, you host the model yourself on your own infrastructure or cloud environment. You have access to the model weights and full control over deployment. This allows for customization, fine-tuning, and tighter integration with internal systems. However, it also means your team is responsible for infrastructure, scaling, monitoring, and reliability. Open source models are powerful tools, but they require a higher level of engineering maturity. They shift responsibility from vendors to your own team. The biggest advantage of open source models is control. You can fine-tune models for specific domains, deploy them in private environments, and meet strict data privacy requirements. Over time, this can significantly reduce per-request costs compared to APIs. Open source models also offer transparency. You know exactly what you're running and can audit or modify systems as needed. For organizations with strong ML and infrastructure teams, open source models provide flexibility that APIs cannot. They're especially attractive in regulated industries or highly specialized use cases. Open source models come with real challenges. Hosting and serving large models requires GPUs, optimization, and careful system design. Engineering teams must handle scaling, latency, failures, and updates themselves. Upfront costs can be high, and performance may lag behind the latest proprietary models without significant tuning. Iteration speed can also be slower if tooling is immature. This doesn't make open source models inferior, but it does mean they're not always the right choice, especially for small teams or early stage products. Cost is one of the most common factors in this decision. LLM APIs typically use a pay-per-token model, which makes startup costs predictable but can become expensive at scale. Open source models require infrastructure investment, including GPUs and operational overhead. At low volume, APIs are often cheaper. At high volume, open source models can become more cost-effective. However, cost isn't just about money. It's also about engineering time, reliability, and opportunity cost. Good engineers evaluate total system cost, not just token pricing. Performance is often misunderstood in this comparison. Proprietary API models often lead in raw language capability, but open source models are improving rapidly. With good prompting, fine-tuning, and system design, performance gaps can shrink significantly. In many cases, overall system quality depends more on architecture than on the model itself. Retrieval, context management, and evaluation often matter more than choosing the best model. This is why experienced engineers focus on system-level performance, not just benchmark scores. Security and compliance are critical considerations in real-world systems. Using APIs may raise concerns around data residency, auditability, and regulatory compliance. Even when providers offer strong guarantees, some organizations require full control. Open source models allow deployment in private clouds or on-prem environments, making them easier to align with strict regulations. In many cases, this factor alone determines the choice. As an AI engineer, you must be able to identify when compliance constraints outweigh convenience. There is no universal rule for choosing between APIs and open source models. APIs are usually the best choice when speed matters, teams are small, or the use case is general. Open source models are often better when customization, privacy, or long-term cost control is critical. The key skill is aligning the choice with the problem, constraints, and stage of the product. Interviews often test this reasoning, not your familiarity with specific tools. Clear justification is more important than picking the right answer. Many mature AI systems use hybrid approaches. APIs might be used for complex reasoning or early prototyping, while open source models handle domain-specific or high-volume tasks. Some systems dynamically route requests based on cost, latency, or sensitivity. Hybrid architectures allow teams to balance speed, control, and cost over time. They also reduce dependency on a single provider. Understanding hybrid strategies demonstrates advanced system thinking, something interviewers and employers value highly. From an interview perspective, this topic is about thinking, not memorization. Interviewers don't expect you to memorize pricing tables or model specs. They want to see how you evaluate trade-offs and communicate decisions. You may be asked to design a system and justify your choice of models. The best answers clearly explain constraints, priorities, and risks. This lecture gives you the language and mental framework to handle those questions confidently. The key takeaway from this lecture is simple. Choosing an LLM is an engineering decision. There are trade-offs in cost, control, performance, and compliance. No single option is always best. Strong AI engineers understand these trade-offs and can explain their choices clearly. They focus on systems, not hype. As you continue through this course, you'll see how these decisions connect to prompting, RAG, agents, and production AI systems. In the next lecture, we'll explore the difference between prompt engineering and prompt programming. You'll learn why writing clever prompts isn't enough for production systems, and how engineers design structured, controllable behavior using prompts as part of larger systems. This transition from ad hoc prompts to engineered solutions is a key step in becoming a modern AI engineer. Before we talk about advanced architectures like RAG or agentic systems, we need to clarify an important distinction that many AI practitioners misunderstand. A lot of people today believe that writing better prompts is the same as engineering AI systems. That mindset works for demos and experiments, but it breaks down quickly in production. As AI engineers, our goal is not clever prompts. Our goal is reliable, controllable behavior. In this lecture, we'll clearly separate prompt engineering from prompt programming. Understanding this difference is essential if you want to build AI systems that scale, pass evaluations, and survive real-world usage. In this lecture, we'll explore the difference between prompt engineering and prompt programming. At first glance, these terms sound similar, but they represent very different levels of maturity in how AI systems are built. Prompt engineering focuses on improving outputs through wording. Prompt programming treats prompts as structured, testable components inside larger systems. By the end of this lecture, you'll understand why prompt engineering alone is not enough for production AI, and why modern AI engineers think in terms of prompt programming instead. This distinction will guide how you design every Gen AI system moving forward. Prompt engineering is the practice of writing natural language instructions to guide a model's behavior. It often involves experimenting with wording, examples, and formatting to get better responses. This approach is intuitive and accessible, which is why it became popular early on. Prompt engineering works well when stakes are low and humans are reviewing outputs. However, it relies heavily on trial and error, and results can change unexpectedly when inputs or models change. While prompt engineering is a useful starting point, it was never designed to support reliable, large-scale AI systems. Prompt engineering is most effective in early-stage or low-risk scenarios. It works well for prototyping ideas, exploring model capabilities, or supporting one-off tasks. It's also useful in human-in-the-loop systems, where variability is acceptable and outputs are reviewed manually. In these contexts, speed and flexibility matter more than predictability. Prompt engineering allows teams to experiment quickly without building complex infrastructure. However, as soon as systems need to scale, automate decisions, or operate without constant human oversight, the limitations of this approach become clear. Prompt engineering breaks down when systems move into production. Outputs become unpredictable, especially as prompts grow longer and more complex. Small changes in wording or model updates can lead to large behavior shifts. Prompts are difficult to test, version, and debug, making long-term maintenance challenging. Because logic is embedded in natural language, it's hard to reason about failures or enforce constraints. Over time, prompts become fragile and tightly coupled to specific models. These limitations make prompt engineering unsuitable for production systems that require reliability, safety, and consistency. Prompt programming takes a fundamentally different approach. Instead of treating prompts as text, it treats them as structured components, similar to code. Instructions are separated from data. Outputs follow defined formats, and behavior is constrained by clear rules. Prompt programming is designed for repeatability and predictability. It assumes that prompts will live inside larger systems and must interact cleanly with code, tools, and evaluation pipelines. This approach aligns with how engineers build reliable software, and it's essential for production-grade AI systems. The difference between prompt engineering and prompt programming is not just technical, it's philosophical. Prompt engineering is ad hoc and human-tuned. Prompt programming is structured and system-oriented. One relies on experimentation, the other relies on design. In production systems, maintainability and testability matter more than clever wording. Prompt programming supports versioning, evaluation, and debugging, while prompt engineering does not. Modern AI engineers are expected to move beyond prompt tweaking and toward designing controllable AI behavior within well-defined systems. Prompt programming relies on several core building blocks. System prompts define the model's role and constraints. Input schemas structure how data is passed into the model. Output formats, often JSON or schema-based, ensure predictable responses. Rules and constraints limit undesired behavior, while versioning allows prompts to evolve safely over time. Evaluation hooks make it possible to test outputs automatically. Together, these components turn prompts from fragile text into reliable system elements that can be tested, monitored, and improved like any other part of an AI pipeline. In production, prompts never exist in isolation. They are integrated with retrieval systems, tools, memory, and application logic. In these systems, prompts guide behavior, but they do not replace code. Business logic lives in code. Prompts provide instructions and context within clear boundaries. This separation is critical for reliability and safety. Prompt programming enables this clean separation, allowing systems to scale without becoming brittle. It ensures that prompts enhance systems rather than becoming their weakest point. Reliability is the main reason prompt programming exists. Structured prompts produce more predictable outputs, which makes systems easier to test and debug. They support automation and reduce the risk of unexpected behavior. By enforcing constraints and formats, prompt programming helps reduce hallucinations and unsafe outputs. It also makes it easier to detect failures and apply corrections. In production environments, predictability is more valuable than creativity. Prompt programming gives engineers the control needed to deploy AI systems with confidence. In interviews, prompt-related questions are rarely about clever phrasing. Interviewers want to see whether you understand how prompts fit into larger systems. They care about how you manage reliability, failure modes, and evaluation. Being able to explain the difference between prompt engineering and prompt programming demonstrates maturity. It shows that you think like an engineer, not a prompt hacker. This mindset is increasingly expected in senior AI engineering interviews, especially for Gen AI heavy roles. Consider a simple task like summarization. A naive prompt might just ask the model to summarize a document. This works sometimes, but outputs vary widely. A programmatic approach structures the input, defines the output schema, and specifies evaluation criteria. The model is the same, but reliability improves dramatically. Errors become easier to detect, and outputs become consistent enough for downstream systems. This example illustrates the core idea. Prompt programming transforms unpredictable behavior into something engineers can reason about and trust. One common mistake is trying to encode too much logic into prompts. Another is mixing instructions and data, which confuses models and increases failure rates. Many teams also skip versioning and testing, treating prompts as static artifacts. Perhaps the biggest mistake is believing prompts are magic. They are tools, powerful ones, but they must be used within well-designed systems. Avoiding these mistakes is essential if you want to build AI systems that last beyond demos and prototypes. The key takeaway from this lecture is simple. Prompt engineering is a useful starting point, but it is not sufficient for production AI systems. Prompt programming provides the structure, control, and reliability required for real-world use. Strong AI engineers design systems where prompts are one component, not the entire solution. They focus on behavior, evaluation, and integration rather than clever wording. This mindset shift is critical for building scalable, trustworthy Gen AI systems. Now that you understand the difference between prompt engineering and prompt programming, we're ready to move forward. In the next lecture, we'll explore Retrieval-Augmented Generation, or RAG. This architecture addresses one of the biggest limitations of language models: limited and unreliable knowledge. You'll learn how RAG systems ground models in real data and why they're foundational to modern Gen AI applications. This is where system-level AI engineering truly comes into focus. As language models became more powerful, many people assumed they could simply ask them anything and get reliable answers. In practice, that assumption breaks very quickly. Large language models don't truly know your data, your documents, or your business context. They generate text based on patterns, not facts. Retrieval-Augmented Generation, or RAG, emerged as a solution to this problem. RAG allows us to ground language models in real context, external data, while still leveraging their reasoning capabilities. In this lecture, we'll explore how RAG systems work, why they matter, and why they've become a core architecture for modern Gen AI applications. In this lecture, we'll focus on Retrieval-Augmented Generation, commonly known as RAG. RAG is one of the most important architectural patterns in modern AI engineering. It allows language models to work with up-to-date, private, and verifiable information instead of relying only on their training data. We'll walk through why standalone LLMs are unreliable, how retrieval improves accuracy, and what components make up a RAG system. By the end of this lecture, you should understand why RAG is foundational to production-grade Gen AI systems and how engineers reason about its design. Standalone language models have fundamental limitations. They are trained on static datasets and have no awareness of new information or private data. When asked questions outside their training distribution, they often hallucinate, producing confident but incorrect answers. For enterprise or high-stakes applications, this behavior is unacceptable. It's difficult to verify where answers come from, and users have no way to trace responses back to source documents. These limitations make pure LLMs unreliable for real-world systems. RAG addresses these issues by grounding model outputs in retrieved external information rather than relying solely on internal model knowledge. Retrieval-Augmented Generation combines two steps, retrieval and generation. Instead of asking a model to answer a question from memory, a RAG system first retrieves relevant documents or data from an external source. That retrieved context is then passed to the language model, which uses it to generate a response. This separation is important. Retrieval handles knowledge, while the model handles reasoning and language generation. This allows systems to stay up to date, work with private data, and produce more trustworthy answers. RAG doesn't make models smarter. It makes systems more reliable. At a high level, a RAG system follows a simple but powerful flow. A user submits a query. The system converts that query into an embedding and retrieves the most relevant documents from the data store. Those documents are then injected into the prompt as context. The language model uses this context to generate a response grounded in retrieved information. The final answer is not purely generated, it's informed by real data. Understanding this flow is critical, because most RAG failures happen when one of these steps is poorly designed. A RAG system is made up of several key components. You start with data sources, such as documents, databases, or knowledge bases. These are processed into embeddings and stored in a vector database. A retriever is responsible for finding relevant chunks of data based on similarity. The prompt template controls how retrieved context is presented to the model. Finally, the LLM generates a response using that context. Each component affects system quality. Strong models cannot compensate for weak retrieval or poorly prepared data. Data preparation is one of the most critical parts of RAG. Documents must be split into chunks that are small enough to retrieve accurately, but large enough to preserve meaning. Poor chunking leads to irrelevant or incomplete context. Metadata is often added to help filter results by source, date, or category. Versioning ensures that outdated content can be replaced cleanly. Many RAG failures trace back to poor ingestion pipelines. Good retrieval starts long before the model ever sees a prompt. Retrieval works by comparing embeddings. Text is converted into numerical vectors that represent semantic meaning. When a query arrives, its embedding is compared to stored embeddings to find the most similar items. Distance metrics and top case selection determine what context is retrieved. There is always a trade-off between recall and relevance. Retrieving too little context risks missing information, while retrieving too much overwhelms the model. Understanding these trade-offs is essential for designing effective RAG systems. Once documents are retrieved, they must be injected into the prompt carefully. Context placement matters. Instructions and retrieved data should be clearly separated to avoid confusion. Engineers must also manage context window limits to prevent truncation or overload. Good RAG prompts explicitly instruct the model to rely on retrieved content and avoid speculation. Prompt programming principles are especially important here. Even with perfect retrieval, poor prompt construction can undermine the entire system. RAG and fine-tuning solve different problems. RAG allows models to work with dynamic, frequently changing information. updates are fast and low risk because data lives outside the model. Fine-tuning modifies model behavior more permanently and is better suited for style, tone, or task-specific behavior. It's more expensive and slower to update. In practice, many systems use both. RAG handles knowledge while fine-tuning shapes behavior. Knowing when to use each is a key engineering skill. RAG systems fail in predictable ways. Poor chunking can fragment meaning. Weak embeddings or retrieval logic can surface irrelevant context. Too much retrieved text can overwhelm the model and reduce answer quality. Outdated or low-quality documents introduce incorrect information. Finally, over-trusting retrieved data without evaluation can propagate errors. Recognizing these failure modes helps engineers debug and improve RAG systems systematically rather than guessing at prompt changes. Improving RAG systems is an iterative process. Better embeddings improve retrieval accuracy. Hybrid search combines semantic and keyword-based approaches. Re-ranking helps prioritize the most useful documents. Metadata filters narrow retrieval scope, and continuous evaluation tracks performance over time. Feedback loops allow systems to learn from user interactions. Strong RAG systems are engineered, monitored, and refined, not built once and forgotten. Production RAG systems introduce additional challenges. Latency becomes critical, especially for interactive applications. Caching can reduce repeated retrieval costs. Cost trade-offs must be managed as usage scales. Monitoring retrieval quality is just as important as monitoring model outputs. Engineers also need feedback mechanisms to identify failures and improve performance over time. This is where RAG transitions from an architectural idea into a real engineering discipline. In interviews, RAG questions test system thinking. Interviewers want to know why you chose RAG, how you designed retrieval, and how you handle failures. They care about evaluation strategies and real-world constraints. Being able to explain RAG clearly and discuss trade-offs versus fine-tuning demonstrates practical AI engineering experience. This is a topic where clarity and structure matter far more than buzzwords. The key takeaway from this lecture is that RAG grounds language models in reality. It separates knowledge from reasoning, making systems more accurate, trustworthy, and maintainable. Retrieval quality often matters more than model choice. RAG is not optional in modern Gen AI systems. It's foundational. Engineers who understand RAG architecture are far better prepared to build production-grade AI applications. In the next lecture, we'll dive deeper into one of RAG's most important components, vector databases. You'll learn how systems like Face, Pinecone, and Weaviate store and retrieve embeddings, and how to choose the right option for different use cases. Understanding vector storage is essential for building scalable and reliable RAG systems. In modern AI systems, especially those using Retrieval-Augmented Generation, one component shows up again and again: vector databases. While many people focus on models and prompts, retrieval is often the real bottleneck in production systems. Vector databases exist to solve a very specific problem: how to store and retrieve semantic meaning efficiently at scale. If retrieval is weak, even the best language model will produce poor results. In this lecture, we'll focus on what vector databases are, how they work, and how engineers choose between different options like Face, Pinecone, and Weaviate. The goal is not tool memorization, but understanding the engineering trade-offs behind each choice. In this lecture, we'll explore vector databases and their role in modern AI systems. You'll learn why vector databases exist, how they differ from traditional databases, and why they are essential for applications like RAG and semantic search. We'll also compare three commonly used tools: Face, Pinecone, and Weaviate from an engineering perspective. By the end of this lecture, you should understand not just how vector databases work, but how to reason about which option makes sense given constraints like scale, cost, and operational complexity. Traditional databases are designed for exact matches. They work well when you know precisely what you're searching for, such as a user ID or a keyword. However, AI systems often need to search by meaning rather than exact text. Language models operate on embeddings, which represents semantic similarity. Two sentences can be meaningfully related even if they share no keywords. Traditional databases are not optimized for this kind of search. Vector databases fill this gap by enabling fast similarity search over high-dimensional embeddings, which is essential for modern AI applications. A vector database is a system designed to store and search embeddings efficiently. Instead of rows and columns, it works with high-dimensional vectors that capture semantic meaning. These databases are optimized for finding the closest vectors to a query vector, rather than exact matches. In addition to similarity search, vector databases often support metadata filtering, allowing engineers to narrow results by attributes like source, date, or category. Vector databases are a core building block of RAG systems, recommendation engines, and semantic search applications. Vector search works by comparing embeddings in a mathematical space. Text is converted into vectors using an embedding model. When a query arrives, its vector is compared to stored vectors using distance metrics like cosine similarity or dot product. Because exact nearest neighbor search is expensive at scale, most systems use approximate nearest neighbor techniques. These trade a small amount of accuracy for large gains in speed. Engineers must balance accuracy, latency, and cost. Understanding these trade-offs is key to designing effective retrieval systems. FAEUS is a high-performance vector search library designed for speed and flexibility. It runs locally or on your own infrastructure and gives engineers full control over indexing and search behavior. FAEUS is highly optimized and commonly used in research or custom pipelines. However, it does not provide a full database experience. There is no built-in persistence, scaling, or management layer. Engineers are responsible for handling infrastructure, storage, and updates. FAEUS is best suited for teams that want maximum control and are comfortable managing their own systems. Pinecone is a fully managed cloud-native vector database. It abstracts away infrastructure concerns like scaling, replication, and reliability, allowing teams to focus on application logic. Pinecone also provides strong metadata filtering and production-ready performance. The trade-off is reduced control and ongoing usage costs. Because it's a managed service, you're dependent on a third-party provider. Pinecone is often the best choice for teams that want to move quickly into production without investing heavily in infrastructure or operations. Weaviate sits between FAEUS and fully managed services, is open source and can be self-hosted, but it also offers managed options. Weaviate provides rich schema support, metadata filtering, and built-in hybrid search capabilities. This flexibility makes it attractive for teams with more complex data needs or custom deployment requirements. However, it also introduces operational complexity compared to fully managed solutions. Weaviate is a strong choice when flexibility and extensibility matter more than simplicity. Choosing a vector database is an engineering decision, not a popularity contest. FAEUS is a good fit when you want full control and are optimizing for cost or custom workflows. Pinecone is ideal when speed to production and low operational overhead are the top priorities. Weaviate works well when you need flexible schemas or hybrid search. The right choice depends on constraints like team size, scale, data sensitivity, and budget. Interviewers care less about which tool you choose and more about how clearly you justify that choice. In interviews, vector databases are usually discussed as part of a larger system. Interviewers want to know why vectors are needed, how similarity search works, and how retrieval impacts system quality. They also expect you to reason about scale, latency, and cost. You may be asked to justify a specific tool choice or describe how you would migrate as a system grows. Clear, structured explanations demonstrate system-level thinking. This lecture gives you the vocabulary and mental models needed to handle those questions confidently. Up to this point, we've focused on how language models generate text and reason over information. But real-world AI systems don't just talk, they act. They fetch data, call APIs, run calculations, and trigger workflows. This is where tool calling and function calling come in. Tool calling transforms language models from passive text generators into active participants in real systems. It allows models to decide when an action is needed, while the application controls how that action is executed. In this lecture, we'll break down what tool and function calling are, how they work, and why they are foundational to production AI systems and agentic workflows. In this lecture, we'll explore tool calling and function calling, two concepts that enable language models to interact with the real world. We'll look at why text-only AI systems fall short, how tools extend model capabilities, and how engineers design safe, controllable action pipelines. This topic sits at the intersection of reasoning and execution. By the end of this lecture, you should understand how modern AI systems move beyond conversation and into action, and why tool calling is a key building block for autonomous and agentic AI systems. Language models are extremely good at generating text, but that's all they do. They can describe an API call, explain a calculation, or suggest an action, but they cannot actually perform it. They don't have direct access to databases, external services, or file systems. In real workflows, this becomes a major limitation. Text-only systems require humans or brittle glue code to bridge the gap between reasoning and execution. Tool calling exists to close this gap. It allows models to request actions in a structured way while keeping execution under strict programmatic control. Tool and function calling provide a structured interface between language models and external systems. Instead of responding with free-form text, the model can choose to call a predefined function or tool. It generates structured parameters, and the application executes the action. The key idea is separation of responsibility. The model decides what action is needed, but the application controls how that action is performed. This design keeps systems safe, testable, and predictable, while still allowing models to reason dynamically about next steps. At a high level, tool calling follows a clear sequence. A user request comes in. The language model analyzes the request and decides whether it needs to call a tool. If so, it selects the appropriate tool and generates structured parameters. The application validates and executes the tool call, then returns the result to the model. The model can then use that result to continue reasoning or generate a final response. This loop allows systems to combine natural language reasoning with deterministic execution, a critical requirement for production AI. Tools and functions serve similar purposes but operate at different levels of abstraction. Tools often represent broad capabilities, such as searching the web, querying a database, or interacting with external APIs. Functions are typically more constrained, with clearly defined inputs and outputs. Both approaches rely on schemas and validation to ensure safety and reliability. The key difference is scope, not importance. In practice, modern AI systems use both, choosing the right abstraction based on the task, complexity, and risk involved. Tool calling fundamentally changes what AI systems can do. It allows models to retrieve real data, perform calculations, and automate workflows instead of guessing. This dramatically improves accuracy and reduces hallucinations. More importantly, it enables AI systems to move from assistants to operators. Systems can now complete tasks end-to-end with minimal human intervention. In production environments, this capability is essential. Without tool calling, AI systems remain limited to advisory roles and struggle to deliver real business value. Tool calling introduces power, but also risk. Common failures include ambiguous tool definitions, poorly specified parameters, and missing validation. over-trusting model decisions without safeguards can lead to incorrect or unsafe actions. Error handling is another frequent issue. Tools fail, APIs return unexpected results, and systems must recover gracefully. These failures are rarely caused by the model itself. They usually stem from weak system design. Good AI engineers anticipate these issues and design guardrails from the start. Reliable tool calling systems are engineered, not improvised. Tools should have clear descriptions and strict input and output schemas. Validation and permission checks must happen outside the model. Logging and observability are critical for debugging and auditing behavior. In higher risk systems, human-in-the-loop approval may be required before actions are executed. The goal is to combine model flexibility with engineering discipline. These best practices ensure that AI systems remain safe, predictable, and maintainable as they scale. In interviews, tool calling is often used to assess system-level thinking. Interviewers want to know why tools are needed, where decision boundaries lie, and how safety is enforced. They care less about specific APIs and more about design principles. Being able to explain how reasoning is separated from execution demonstrates maturity as an AI engineer. It shows that you understand both the power and the risks of autonomous systems. This lecture gives you the conceptual foundation to answer those questions confidently. Up to this point, you've learned the individual building blocks of modern GenAI systems: prompt programming, retrieval-augmented generation, vector databases, and tool calling. Now it's time to bring those pieces together. This mini project is where theory becomes engineering. The goal is not to build a flashy demo, but to design a system that behaves reliably, can be explained clearly, and could realistically be extended into a production product. As you work through this project, you should constantly ask yourself one question: would I feel confident explaining this system to a hiring manager? That mindset is exactly what this project is designed to develop. In this mini project, you'll build a production-grade retrieval-augmented generation application from end to end. This project is intentionally scoped to be small enough to complete, but realistic enough to reflect how real AI systems are built. You'll apply concepts from recent lectures and connect them into a single, cohesive system. The emphasis here is not speed or cleverness, it's clarity, structure, and reliability. By the end of this project, you should be able to explain every design decision you made and why it matters in a real-world AI system. The goal of this project is to build a question-answering system that produces grounded, reliable responses. Your system should retrieve relevant information from external documents and use that information to generate answers. It should not rely on the model's internal knowledge alone. This project mirrors a very common real-world use case: internal knowledge assistance, document search tools, and domain-specific AI copilots. If built well, this project can serve as a strong portfolio piece that demonstrates your understanding of modern GenAI system design. Before writing any code, you should think in terms of architecture. Your system will include a user interface, an embedding pipeline, a vector database, a retrieval layer, a prompt programming layer, and an LLM for generation. Each component has a clear responsibility. This separation of concerns is critical. When systems fail, engineers need to know where the failure occurred. Good architecture makes systems easier to debug, improve, and explain. Treat this diagram as a mental model you'll refer back to as you implement each part of the project. The quality of your RAG system depends heavily on your data. Choose documents that are meaningful and domain-specific rather than generic examples. This could include PDFs, markdown files, or structured text from a particular field. During ingestion, documents should be chunked thoughtfully, with attention to preserving context while enabling accurate retrieval. Adding metadata, such as source or category, will help later during retrieval. Remember, Poor data preparation is one of the most common reasons RAG systems fail, even when the rest of the pipeline is well designed. Once your data is prepared, it must be converted into embeddings and stored efficiently. Each chunk of text is transformed into a vector using an embedding model. These vectors are then stored in a vector database, such as FAISS, Pinecone, or Weaviate. Metadata should be stored alongside embeddings to support filtering and traceability. You should also think about how updates will be handled as documents change. This layer is the backbone of retrieval. If embeddings or storage are poorly designed, downstream components will struggle regardless of how good the model is. The retriever is responsible for selecting the most relevant context for each user query. When a query arrives, it is embedded and compared against stored vectors. The top K most relevant chunks are selected and passed forward. Design choices here matter. Retrieving too little context risks missing important information. Retrieving too much can overwhelm the model. Engineers must balance relevance, recall, and performance. This is one of the most important and most overlooked parts of RAG system design. Once context is retrieved, it must be injected into the prompt in a structured way. Your system prompt should clearly define the model's role and constraints. Retrieved context should be separated from instructions, and output formats should be defined explicitly. Avoid embedding business logic inside the prompt. Logic belongs in code. Prompts should guide behavior. This is where prompt programming principles matter most. A well-designed prompt layer turns retrieved data into consistent, grounded responses rather than unpredictable text. Optional enhancements can significantly improve system robustness. You might add tools for logging, tracing, or citation extraction. You could validate outputs, rewrite queries, or hook in evaluation functions. These additions move your system closer to production readiness. They also demonstrate engineering maturity, showing that you think beyond basic functionality. Not every enhancement is required, but understanding how tools integrate into the pipeline is valuable, especially for agentic and autonomous systems. A production-grade system must be evaluated. You should assess whether retrieved context is relevant, whether responses are grounded in that context, and whether outputs are consistent across runs. Identify common failure cases and understand why they happen. Evaluation doesn't have to be complex, but it must be intentional. Manual checks combined with simple automated tests are a good starting point. This step is often skipped in tutorials, but it's exactly what differentiates real engineering from experimentation. As an AI engineer, you should always think one step ahead. Consider latency and cost, especially if your system scales. Think about caching repeated queries, handling errors gracefully, and monitoring system behavior. Versioning prompts and data allows you to iterate safely. Observability helps you understand how your system behaves in the real world. These considerations may not be fully implemented in this project, but you should be able to discuss them clearly, and that matters a lot in interviews. Your final deliverable should reflect professional standards. Submit a working RAG application with a clean project structure. Include a README that explains what you built, why you made certain decisions, and how the system works. Provide example queries and outputs, and be honest about limitations and future improvements. This project isn't just about code, it's about communication. A clear explanation of your work is just as important as the system itself. This project is an excellent interview asset if you know how to talk about it. Be prepared to explain your architecture, justify your tool choices, and discuss trade-offs. Highlight failure modes and how you would improve the system over time. Interviewers care less about perfection and more about reasoning. This project gives you a concrete system to anchor those discussions. If you can clearly explain this RAG app, you're already operating at the level expected of modern AI engineers. Before we dive deeper into agent loops and autonomous systems, we need to clearly define what we mean by an AI agent. The term is used loosely across the industry, often to describe anything powered by a language model. But not every LLM powered application is an agent. Understanding this distinction is critical. It affects how systems are designed, how risks are managed, and how interviews are evaluated. In this lecture, we'll draw a clear line between traditional LLM applications and true AI agents. This mental model shift from reactive apps to goal-driven systems will shape how you think about modern AI engineering going forward. In this lecture, we're going to answer a deceptively simple question. What is an AI agent? We'll compare LLM applications with AI agents, explain why the distinction matters, and identify the core properties that make a system agentic. This is not about buzzwords, it's about system behavior. By the end of this lecture, you should be able to clearly explain what separates a chatbot or LLM app from an AI agent, and why agents are foundational to autonomous AI systems being built today. This understanding is essential for both real-world system design and technical interviews. An LLM application is typically a reactive system. It takes an input, sends it to a language model, and returns an output. The system may include some light state, but it does not persist goals or reason across multiple steps on its own. LLM apps respond to requests, but they don't act independently. They don't plan ahead, adapt over time, or decide what to do next without explicit user input. Examples include chatbots, summarization tools, and content generators. These systems are useful, but they are fundamentally limited when tasks become complex or require sustained decision-making. The limitations of LLM apps become clear when tasks go beyond a single step. LLM apps lack goal persistence. Once a response is generated, the system stops. There's no mechanism for evaluating outcomes, adjusting strategy, or continuing work autonomously. They also struggle with complex workflows that require multiple actions, coordination across tools, or adaptation to unexpected results. Humans are often required to guide each step. These limitations aren't flaws in language models. They're a consequence of how LLM apps are designed. To move beyond these constraints, systems must evolve from reactive applications into agents. An AI agent is a goal-driven system. Instead of simply responding to input, an agent is designed to pursue an objective. It can plan actions, execute those actions using tools, observe the results, and adjust its behavior based on feedback. Agents operate semi-autonomously or autonomously. They decide what to do next, rather than waiting for explicit instructions at every step. This shift from responding to acting is the defining characteristic of an AI agent. It's also what enables AI systems to handle complex real-world tasks that unfold over time. AI agents are composed of several key components. First, there's a goal or objective that guides behavior. Second, there's a reasoning or planning mechanism that determines what actions to take. Third, agents rely on tools or actions to interact with the world, such as APIs, databases, or external systems. Memory allows agents to retain context, learn from past actions, and avoid repeating mistakes. Finally, a feedback loop enables agents to observe outcomes and adjust their strategy. Together, these components transform language models into systems capable of sustained, autonomous behavior. The difference between an LLM app and an AI agent is best understood side by side. LLM apps are reactive. They operate in a single step and focus on text generation. AI agents are proactive. They operate over multiple steps and can act in the real world. LLM apps rely heavily on human guidance. Agents reduce that dependency by managing tasks autonomously. These are not incremental differences. They represent fundamentally different design philosophies. Understanding this distinction helps you design the right system for the problem and explain your choices clearly in interviews. AI agents are already being used in real-world systems. Examples include autonomous research agents that gather and synthesize information, coding agents that write and debug software, and operations agents that monitor systems and respond to incidents. Personal AI copilots and workflow automation agents are also becoming common, handling multi-step tasks across tools and platforms. These systems go beyond answering questions. They deliver outcomes. Recognizing these patterns helps you understand where the industry is heading and what skills modern AI engineers need to develop. AI agents matter because real-world work is not static. Tasks evolve, conditions change, and decisions must be made continuously. Businesses don't just want answers, they want results. AI agents are designed to meet that need. By reducing human coordination and enabling autonomous execution, agents unlock new levels of efficiency and scalability. As a result, agentic systems are becoming a core focus of modern AI development. For AI engineers, understanding agents is no longer optional. It's a foundational skill for building the next generation of intelligent systems. In interviews, AI agents are often used to assess system-level understanding. Interviewers expect you to clearly distinguish agents from chatbots and explain concepts like autonomy, control, and feedback loops. They also want to see awareness of risks, such as runaway behavior or poor guardrails. Strong answers focus on design principles rather than hype. They show that you understand both the power and responsibility that come with agentic systems. This lecture gives you the language and mental models needed to discuss AI agents confidently and credibly. Now that we understand what an AI agent is, we can look at the mechanism that actually makes agents work: the agent loop. Autonomous behavior doesn't come from a single prompt or a clever model. It comes from repetition, feedback, and adaptation. The plan, act, observe, reflect loop is the core pattern behind most modern agentic systems. It explains how agents decide what to do, take action, learn from results, and improve over time. In this lecture, we'll break this loop down step by step and explain why each phase is essential for building reliable autonomous AI systems. In this lecture, we'll explore the plan, act, observe, reflect loop, which sits at the heart of agentic AI systems. This loop explains how agents move beyond one-off responses and into continuous, goal-driven behavior. We'll look at why this structure exists, how each phase works, and how loops enable agents to adapt in dynamic environments. By the end of this lecture, you should understand not only what each phase does, but why skipping or weakening any part of the loop leads to fragile or unsafe systems. This loop is foundational to everything that follows in agentic AI engineering. Agent loops exist because real-world problems are not solved in one step. Tasks often involve uncertainty, partial information, and changing conditions. A single response, even a very good one, is rarely enough. Systems must take action, observe outcomes, and decide what to do next. Without a loop, AI systems are reactive and brittle. They cannot adapt when things go wrong or when new information appears. Agent loops provide structure for continuous decision-making. They allow systems to make progress toward goals over time, rather than hoping for a perfect first answer. The plan phase is where reasoning happens. In this phase, the agent interprets its goal and decides what to do next. This may involve breaking a larger objective into smaller steps, choosing a strategy, or prioritizing actions based on constraints. Planning does not mean generating a full solution upfront. In many systems, planning is incremental, focused only on the next best action. Good planning considers risks and uncertainties. Weak planning leads to wasted actions or dead ends. In production systems, planning quality often determines whether an agent behaves intelligently or chaotically. The act phase is where decisions turn into execution. During this phase, the agent performs actions using tools or functions. These actions might include querying a database, calling an API, running a calculation, or modifying an external system. Actions should be deterministic and controlled. The agent does not directly execute arbitrary code. It requests actions that the application validates and performs. This separation between reasoning and execution is critical for safety and reliability. The act phase is where agents interact with the real world, so strong guardrails are essential. After acting, the agent must observe what happened. Observation includes capturing tool outputs, reading system responses, and detecting errors in unexpected behavior. This feedback becomes new information for the agent. Without observation, agents operate blindly. They cannot tell whether an action succeeded, failed, or produced unintended consequences. Observation updates the agent's internal state and provides the context needed for the next planning step. High-quality observation is a prerequisite for meaningful adaptation and learning in agentic systems. Reflection is where agents learn from experience. In this phase, the agent evaluates whether the observed outcome aligns with its expectations or goals. It may decide to continue, revise its plan, retry an action, or stop altogether. Reflection can also involve updating memory, recording what worked, what failed, and why. Over time, this enables agents to improve their behavior across iterations. Skipping reflection leads to repetitive mistakes. Reflection is what turns loops into learning mechanisms rather than mechanical cycles. Agent loops can be executed in different ways depending on the system. Some loops run for a fixed number of iterations. Others stop when a goal is achieved or when confidence thresholds are met. In higher-risk systems, human-in-the-loop checkpoints may be required. Safety mechanisms such as timeouts, iteration limits, and validation checks are critical. Without them, agents can loop endlessly or take unintended actions. Designing loop execution patterns is an engineering decision that balances autonomy, safety, and efficiency. Agent loops can fail if not carefully designed. Common issues include infinite loops, poor planning logic, and over-reliance on faulty observations. Without clear stopping criteria, agents may continue acting even when progress is no longer possible. Missing guardrails can allow agents to take unsafe or unnecessary actions. Weak reflection leads to repeated mistakes rather than improvement. Understanding these failure modes is essential. Strong AI engineers design loops defensively, anticipating what can go wrong and building protections from the start. The plan, act, observe, reflect loop is the foundation of autonomous AI behavior. It enables systems to handle complex, multi-step tasks, adapt to new information, and improve over time. This loop separates reasoning from execution and learning from action. Most modern agentic architectures build on this exact pattern. If you understand this loop deeply, you understand the core of agentic AI. Everything that follows, react, multi-agent systems, autonomous workflows, extends from this fundamental structure. As AI systems become more autonomous, how they reason becomes just as important as what they produce. Not all reasoning is the same, and different problems require different reasoning strategies. In this lecture, we'll look at 3 important reasoning patterns used in modern agentic AI systems: chain of thought, react, and tree of thoughts. These are not buzzwords or tricks. They are structured approaches to guiding how models think, act, and explore solutions. Understanding when to use each pattern, and when not to, is a key skill for modern AI engineers, especially in system design interviews and real-world applications. In this lecture, we'll explore 3 reasoning patterns that show up frequently in agentic AI systems. We'll start by understanding why reasoning patterns exist at all, then break down chain of thought, react, and tree of thoughts individually. For each pattern, we'll discuss how it works, what it's good at, and where it falls short. The goal is not to memorize definitions, but to build intuition. By the end of this lecture, you should be able to choose the right reasoning strategy for a given task and clearly explain that choice in both system design discussions and interviews. Reasoning patterns exist because complex problems cannot be solved reliably in a single step. One-shot answers often fail when tasks involve multiple constraints, uncertainty, or dependencies between steps. Without structure, models may guess, hallucinate, or take fragile shortcuts. Reasoning patterns introduce discipline into how models think. They guide the order of operations, encourage intermediate reasoning, and reduce unpredictable behavior. For AI engineers, these patterns are tools, not magic. They help transform raw model capability into controlled, repeatable system behavior that can scale beyond simple demos. Chain of thought reasoning encourages the model to think step by step. Instead of jumping directly to an answer, the model generates a linear sequence of reasoning steps. This approach often improves accuracy on tasks that require logic, math, or multi-step reasoning. In practice, these reasoning steps may be hidden, summarized, or constrained to avoid exposing raw internal reasoning. The key idea is not transparency, it's structure. Chain of thought works best when there is a clear path from problem to solution and limited need for exploration or external interaction. Chain of thought has clear strengths. It's simple to implement, improves reasoning accuracy, and works well for problems with a single correct path. For many tasks, it's all you need. However, it has important limitations. Because reasoning is linear, mistakes early in the chain can propagate through the entire solution. There's no built-in mechanism for backtracking or exploring alternatives. As tasks become more open-ended or uncertain, pure chain of thought becomes fragile. This is where more advanced reasoning patterns are required. REACT stands for reasoning and acting. Instead of reasoning entirely in the abstract, the model alternates between thinking and taking actions, such as calling tools or querying external data. Each action produces observations that inform the next reasoning step. This pattern grounds reasoning in reality. Rather than guessing, the model can fetch data, verify assumptions, and adapt its plan. REACT is especially powerful in agentic systems where interaction with the environment is required. It reduces hallucinations and supports multi-step workflows that depend on real-world information. Tree of Thought's reasoning expands the idea of chain of thought. Instead of following a single reasoning path, the model explores multiple possible paths in parallel. These paths form a tree of possible solutions, which can be evaluated and pruned. This approach is useful for problems involving planning, strategy, or creative exploration. It allows agents to compare alternatives rather than committing too early. The trade-off is cost. Tree of Thoughts requires more computation and careful control to avoid combinatorial explosion. Each reasoning pattern serves a different purpose. Chain of thought is linear and efficient, making it suitable for structured problems. REACT combines reasoning with action, making it ideal for interactive and data-driven tasks. Tree of Thoughts enables exploration, which is valuable for complex or strategic problems. There is no universally best pattern. The right choice depends on task complexity, available tools, cost constraints, and acceptable failure risk. Strong AI engineers choose reasoning patterns intentionally rather than defaulting to one approach everywhere. Choosing a reasoning pattern involves trade-offs. More structure often means higher cost. More exploration means slower execution. More autonomy increases the need for guardrails. Engineers must balance accuracy, speed, determinism, and safety. They must also consider how reasoning interacts with tools, memory, and evaluation systems. These trade-offs are not theoretical. They show up in production systems every day. Understanding them helps you design systems that are both effective and practical. In interviews, reasoning patterns are used to evaluate system thinking. Interviewers want to see whether you understand when each pattern is appropriate and how to justify your choice. They are less interested in buzzwords and more interested in trade-off analysis. Strong answers explain why a pattern was chosen, what risks it introduces, and how those risks are managed. This demonstrates maturity and real-world experience. This lecture gives you the conceptual tools to discuss reasoning strategies clearly and confidently. As we move deeper into agentic AI systems, one capability becomes absolutely essential: memory. Without memory, agents are little more than reactive tools that repeat the same mistakes over and over again. Memory is what allows agents to persist context, learn from experience, and behave intelligently across time. It's also one of the most misunderstood and dangerous components if designed poorly. In this lecture, we'll clearly distinguish between short-term and long-term memory, explain how agents use memory within their decision loops, and discuss the engineering risks that come with storing and recalling information. Understanding memory design is critical for building autonomous systems that are both effective and safe. In this lecture, we'll explore memory in agentic AI systems. We'll start by understanding why memory is necessary for autonomy, and why stateless agents quickly hit limitations. Then, we'll distinguish between short-term and long-term memory, looking at how each serves a different purpose. We'll also discuss how memory fits into the agent loop, how it's typically stored, and what can go wrong when memory is misused. Finally, we'll cover how interviewers evaluate memory design in AI systems. By the end, you should be able to design memory intentionally, not accidentally. Stateless agents are fundamentally limited. Without memory, an agent cannot remember what it has already tried, what worked, or what failed. It loses context between steps and cannot adapt its behavior over time. As a result, it often repeats mistakes or asks the same questions again. Memory enables continuity. It allows agents to build on prior actions, refine plans, and make better decisions with each iteration. In real-world systems, autonomy without memory quickly becomes chaos. Memory is what transforms a sequence of actions into a coherent, goal-driven process. Short-term memory, often called working memory, holds recent context. This includes recent user inputs, actions taken by the agent, and observations from tools or the environment. In practice, short-term memory often lives inside the model's context window or in temporary session state. Short-term memory is fast and easy to access, but it's limited in size and duration. It's typically reset when a task ends or a session expires. This type of memory is essential for reasoning within a task, but it's not designed for long-term learning or personalization. Long-term memory persists across tasks and sessions. It may store past experiences, learned strategies, user preferences, or important facts discovered over time. Unlike short-term memory, long-term memory is not constrained by context windows. However, long-term memory is slower to access and has much higher impact. Incorrect or biased memories can influence behavior repeatedly. Because of this, long-term memory must be designed carefully. It should be deliberate, validated, and aligned with clear policies about what is worth remembering and what is not. Memory plays a role at multiple points in the agent loop. During planning, agents may recall similar past tasks or known constraints. During reflection, they may write new insights or outcomes back into memory. Over time, this feedback allows agents to improve their strategies. Memory also enables personalization. Agents can adapt their behavior based on prior interactions, making systems feel more intelligent and responsive. The key idea is that memory should inform decisions, not blindly control them. Good agents treat memory as guidance, not truth. There are several ways to store memory in agentic systems. Short-term memory may live directly in prompts or session state. Long-term memory is often stored in vector databases, structured databases, logs, or event stores. Vector-based memory allows semantic recall, while structured storage supports precise retrieval. Many production systems use hybrid approaches that combine multiple storage types. Choosing the right mechanism depends on access patterns, scale, and sensitivity. Engineers must think carefully about how memory is written, read, and updated over time. Memory introduces significant risk if not managed properly. Memory poisoning occurs when incorrect or malicious information is stored and reused. Stale memories can mislead agents long after conditions have changed. Privacy risks arise when sensitive data is stored without safeguards. Agents can also overfit to past behavior, becoming rigid instead of adaptive. Unbounded memory growth can degrade performance and increase cost. These risks are not hypothetical. They appear frequently in real systems. This is why memory design requires strict controls and ongoing evaluation. Safe memory design starts with clear policies. Engineers should define when memory is written, what can be stored, and how long it persists. Validation and filtering help prevent garbage or harmful data from entering memory. Expiration and decay rules prevent stale information from dominating behavior. Separating short-term and long-term memory reduces unintended coupling. For sensitive memory, human oversight or explicit user consent may be required. The goal is to make memory useful, bounded, and trustworthy. In interviews, memory design is a strong signal of system maturity. Interviewers want to see that you understand why memory is needed, how different memory types serve different purposes, and what risks they introduce. They are especially interested in how you prevent memory-related failures. Strong answers clearly explain design choices, trade-offs, and safeguards. They show that you think beyond just store everything. This lecture equips you to discuss memory in a practical, responsible way, exactly how modern AI engineers are expected to think. As AI systems grow more capable, a single agent is often no longer enough. Real-world problems involve multiple skills, parallel work, verification, and coordination, things that are difficult for one agent to handle reliably on its own. Multi-agent systems address this by breaking complex objectives into smaller responsibilities handled by specialized agents. However, adding more agents introduces new challenges around coordination, control, and safety. In this lecture, we'll explore why multi-agent systems exist, how agents communicate and collaborate, and why orchestration is essential for keeping these systems reliable. Understanding this is critical for building scalable, production-ready agentic AI systems. In this lecture, we'll introduce multi-agent systems and orchestration. We'll begin by explaining why a single agent often isn't sufficient for complex tasks. Then, we'll define what a multi-agent system is and how agents collaborate to achieve shared goals. We'll also focus on orchestration, the layer that coordinates agent behavior, manages task flow, and enforces system-level rules. Finally, we'll discuss risks and interview expectations. By the end of this lecture, you should understand when to use multiple agents, how to coordinate them, and how to explain these decisions clearly in interviews. Single agents work well for narrow tasks, but they struggle as complexity increases. As goals expand, agents become overloaded with planning, execution, verification, and error handling. This leads to brittle behavior and poor scalability. Multi-agent systems solve this by separating responsibilities. Different agents can specialize in planning, execution, analysis, or validation. This mirrors how human teams work and improves reliability. Parallelism is another advantage. Multiple agents can work simultaneously on different parts of a problem, reducing latency and improving throughput. In production systems, this separation of concerns is often the difference between a demo and a scalable solution. A multi-agent system consists of multiple agents working together toward a shared or coordinated objective. Each agent typically has a defined role or responsibility. Agents communicate with one another, share information, and contribute to the overall system outcome. Importantly, No single agent has full control over the entire system. Instead, intelligence emerges from collaboration and coordination. Multi-agent systems are commonly used in complex workflows such as research automation, code generation pipelines, monitoring systems, and enterprise operations. Understanding this definition helps clarify why orchestration, not just intelligence, is critical for system success. Multi-agent systems often include several specialized agent roles. A planner or coordinator agent may decompose goals and assign tasks. Executor agents perform concrete actions such as calling APIs or writing code. Specialist agents handle focused tasks like research or data analysis. Validator or reviewer agents check outputs for correctness, safety, or quality. Monitoring agents observe system behavior and detect failures. This role-based design improves clarity and reliability. Each agent is simpler and more focused, making the overall system easier to reason about and maintain. For multi-agent systems to work, agents must communicate effectively. Communication can take many forms: message passing, shared memory, event-driven signals, or structured outputs. Free-form text communication is flexible but risky. Structured interfaces are safer and easier to validate. Clear communication protocols reduce misunderstandings and prevent cascading errors. They also make systems easier to debug and extend. From an engineering perspective, agent communication should be treated like API design: explicit, versioned, and well documented. Poor communication is one of the most common failure points in multi-agent systems. Orchestration is the control layer that manages how agents work together. It determines execution order, handles dependencies, manages parallelism, and enforces system-level rules. Orchestration also plays a key role in failure handling, retries, and stopping conditions. Without orchestration, agents may work at cross purposes, duplicate effort, or enter unstable feedback loops. Good orchestration does not remove agent autonomy, it channels it. It provides structure so that intelligent behavior leads to reliable outcomes rather than chaos. There are several common orchestration patterns. In centralized orchestration, a single controller manages all agents. Hierarchical systems use layers of agents with different levels of authority. Event-driven orchestration reacts to signals and triggers. Some systems include human-in-the-loop checkpoints for high-risk decisions. Others combine multiple patterns in hybrid models. Each approach has trade-offs in flexibility, complexity, and control. Strong AI engineers choose orchestration patterns based on system requirements rather than defaulting to a single style. Multi-agent systems introduce new risks. Agents may pursue conflicting goals, leading to inconsistent behavior. Excessive communication can increase latency and cost. Errors in one agent can propagate across the system. Feedback loops and deadlocks can occur if coordination is poorly designed. Without strong orchestration, systems may lose global control. These risks are manageable, but only with intentional design. Understanding failure modes is essential for building safe, scalable multi-agent systems. In interviews, multi-agent systems are used to evaluate system-level thinking. Interviewers want to know why multiple agents were used, how responsibilities were divided, and how coordination's managed. They expect awareness of risks and trade-offs. Strong answers emphasize orchestration, communication, and control, not just intelligence. They show that you understand how complex systems behave in practice. This lecture gives you the vocabulary and mental models needed to discuss multi-agent systems clearly and credibly in technical interviews. As AI systems become more autonomous, safety stops being an abstract concern and becomes a core engineering responsibility. The question is no longer whether AI systems will fail, but how they will fail, and what happens when they do. Guardrails are not about limiting intelligence. They are about controlling risk, protecting users, and ensuring systems behave predictably under uncertainty. In this lecture, we'll examine common failure modes in AI systems, the different layers where guardrails can be applied, and how engineers design systems that fail safely rather than catastrophically. This mindset is essential for anyone building production AI systems in 2026. In this lecture, we'll focus on guardrails, safety, and failure modes in modern AI systems. We'll start by explaining why safety is fundamentally an engineering problem, not just a policy concern. Then we'll examine where AI systems commonly fail and what guardrails are designed to prevent. We'll cover safety controls at the model level, system level, and human-in-the-loop level, and discuss how engineers think about failure detection and recovery. By the end of this lecture, you should be able to design AI systems that behave responsibly, even when things go wrong. AI systems are probabilistic by nature. They generate outputs based on likelihood, not certainty. As systems become more autonomous, small mistakes can quickly scale into serious failures, especially when tools, APIs, or external systems are involved. Text-based validation alone is not enough. A system that sounds confident can still be wrong. Guardrails exist to prevent models from acting outside acceptable boundaries. Safety must be designed into the system architecture from the start. Retrofitting guardrails after deployment is costly and often ineffective. Good engineers assume uncertainty and design accordingly. AI systems fail in predictable ways. Hallucinations occur when models generate confident but incorrect information. Tool misuse happens when models call the wrong function or repeat actions unnecessarily. Runaway loops can cause systems to act indefinitely without progress. Incorrect assumptions, such as trusting unverified inputs, can cascade through a system. In multi-agent environments, errors in one component may propagate across others. Understanding these failure modes is critical. You can't prevent what you don't anticipate. Strong AI engineers explicitly design systems with these risks in mind, rather than hoping they won't occur. Model-level guardrails shape how models behave. System prompts define rules, constraints, and refusal behaviors. Output format enforcement ensures responses can be validated programmatically. Confidence thresholds help identify when a model is unsure. Different models may be chosen based on risk sensitivity. For example, using more conservative models for high-stakes decisions. These controls are important, but they are not sufficient on their own. Model-level guardrails guide behavior, but they must be supported by stronger system-level protections to ensure reliability. System-level guardrails enforce hard constraints. Input validation prevents malformed or malicious inputs from reaching the model. Tool permissions restrict what actions agents are allowed to perform. Rate limits and quotas prevent abuse and runaway behavior. Timeouts and iteration limits stop infinite loops. Logging and traceability provide visibility into system behavior for debugging and auditing. Unlike model-level controls, system-level guardrails are deterministic. They do not rely on model judgment, and that's exactly why they're essential for production AI systems. Some decisions are too risky to fully automate. Human-in-the-loop safeguards introduce checkpoints where human approval is required before actions are executed. This is common for financial transactions, legal decisions, or irreversible operations. Low-confidence outputs may trigger escalation instead of execution. Humans can also review edge cases or override system behavior when necessary. Human oversight should be intentional, not accidental. It's a design choice that balances autonomy with responsibility. In production systems, knowing when to involve humans is just as important as knowing when not to. No system is perfect, so failure detection is essential. Monitoring model outputs helps detect anomalies such as unusual language patterns or repeated errors. System metrics can reveal performance degradation or unexpected behavior. When failures occur, systems should degrade gracefully rather than collapse. Fallback strategies may involve switching models, reducing functionality, or escalating to humans. Retry logic must be used carefully to avoid compounding errors. In some cases, aborting safely is the correct choice. Recovery is not about persistence, it's about control. Safe systems assume failure will happen. They prefer no action over the wrong action. They minimize blast radius by isolating components and limiting permissions. They are tested not only for success, but for failure scenarios. Engineers who design for safe failure build systems that are resilient rather than fragile. They ask, what happens if this breaks before deployment? This mindset is a hallmark of mature AI engineering. It separates experimental prototypes from systems that can be trusted in real-world environments. In interviews, safety discussions reveal engineering maturity. Interviewers look for awareness of failure modes and guardrails beyond prompt-level fixes. They want to see system-level thinking, not blind optimism about model behavior. Strong candidates explain how autonomy is balanced with control and how risks are mitigated at multiple layers. They demonstrate respect for uncertainty and complexity. Being able to discuss safety clearly and realistically is increasingly expected for AI engineers working on production systems in 2026. This capstone represents the culmination of everything you've learned about agentic AI engineering. Up to now, we've explored individual concepts, agent loops, memory, tools, orchestration, and safety in isolation. Here, those pieces come together. The goal of this capstone is not to build the most complex agent possible. It's to build a system that behaves autonomously and responsibly, one you can reason about, explain clearly, and improve over time. As you work through this project, think like a production AI engineer. Every design choice you make should answer one question. Would I trust this system to operate without constant supervision? This capstone is your final project in agentic AI engineering. It is designed to integrate all the major concepts covered in this section into a single coherent system. You'll build an autonomous AI agent that can pursue goals, take actions, learn from feedback, and operate within defined safety boundaries. This project is intentionally open-ended. There is no single correct implementation. What matters is clarity of design, robustness of behavior, and your ability to explain trade-offs. When done well, this capstone becomes a strong portfolio artifact and a powerful interview discussion piece. The objective of this capstone is to build a goal-driven autonomous AI agent. Your agent should be capable of interpreting a high-level objective and executing multiple steps to achieve it. It should use tools to interact with the world, memory to persist context, and reasoning to adapt its strategy. Just as importantly, the agent must operate with guardrails. It should know when to stop, when to escalate, and how to handle uncertainty. This project is not about raw intelligence. It's about control, reliability, and explainability. Exactly what real-world AI systems require. Your agent must demonstrate a clear set of core capabilities. It should be able to interpret goals, plan actions, and replan when things don't go as expected. It must execute actions through tools or functions rather than guessing outcomes. Observation and reflection are critical. The agent should understand the results of its actions and adjust behavior accordingly. Memory updates allow it to learn from experience and avoid repeating mistakes. Finally, the agent must know when to stop. Autonomy without stopping conditions is a liability. These capabilities together define what makes the system truly agentic. That's all. Before implementation, you should define your agent's architecture. At a high level, the system starts with a user-provided objective. A planning module determines next steps. An execution layer carries out actions using tools. Observations feed back into reflection and memory. Guardrails operate across the system, enforcing limits and safety checks. This separation of concerns makes the system easier to reason about and debug. Strong architecture is not about complexity, it's about clarity. A clean design will make failures easier to diagnose and improvements easier to implement. Your agent must interact with an external environment. This might include APIs, search tools, retrieval systems, or local data sources. Tools should be accessed through structured interfaces with clear input and output schemas. Permissions matter. The agent should only be allowed to perform actions that are explicitly approved. This prevents accidental or unsafe behavior. Tool usage is where agents become powerful, but also where risk increases. Designing this layer carefully is essential for building an agent that can act effectively without causing unintended harm. Memory allows your agent to persist knowledge and context. Short-term memory supports reasoning within a task, while long-term memory enables learning across tasks. You must decide what information is worth storing, when it should be written, and when it should expire. Validation is critical. Incorrect or unverified memories can degrade agent behavior over time. Decay and expiration rules prevent stale information from dominating decisions. Good memory design improves performance. Poor memory design creates hidden failure modes. This is one of the most important and subtle parts of the capstone. Autonomy demands strong guardrails. Your agent should have clear action limits, timeouts, and stopping conditions. Tool permissions restrict what it can do. Logging and traceability allow you to understand and audit behavior. For higher risk actions, human-in-the-loop checkpoints may be required. Fallback logic ensures the agent fails safely rather than unpredictably. These controls are not optional. They are what make autonomy acceptable in real-world systems. In interviews, this is often the section that differentiates mature engineers from enthusiastic beginners. Your agent should be evaluated across multiple dimensions. Does it reliably achieve its goals? Does it behave consistently across runs? How well does it handle errors and unexpected inputs? Explainability matters. You should be able to explain why the agent took a particular action and how it reached its decisions. Safety under edge cases is just as important as success under ideal conditions. Evaluation doesn't need to be complex, but it must be intentional. This step transforms your project from a demo into an engineering artifact. This capstone is one of your strongest interview assets if you present it correctly. Focus on design decisions, trade-offs, and failure modes rather than just features. Be honest about limitations and explain how you would improve the system with more time. Interviewers want to see how you think, not whether your agent is perfect. This project gives you a concrete system to anchor that discussion. If you can explain this capstone clearly, you are demonstrating the mindset and skills expected of modern AI engineers in 2026. One of the biggest transitions AI engineers must make is moving from experimentation to production. Many strong candidates can build impressive models in notebooks, but struggle when asked to turn that work into a reliable, deployable system. Notebooks are powerful tools, but they were never designed for production environments. In this lecture, we'll explore why notebooks fall short, what production readiness really means, and how engineers refactor experimental code into maintainable systems. Understanding this transition is critical. It's one of the most common gaps interviewers see, and one of the most valuable skills you can develop as an AI engineer in 2026. In this lecture, we'll focus on the journey from notebook-based experimentation to production-grade AI systems. We'll examine why notebooks are useful, why they fail in production, and what changes when you start thinking like a production engineer. This includes code structure, testing, dependency management, and deployment considerations. By the end of this lecture, you should understand how to take an idea that works in a notebook and turn it into a system that can be deployed, monitored, and maintained over time. This mindset shift is essential for real-world AI engineering. Notebooks exist to support exploration. They allow rapid iteration, easy visualization, and flexible experimentation. Data scientists and researchers use notebooks to try ideas quickly, debug logic, and understand data. This flexibility is a strength, but it comes with trade-offs. Notebooks often rely on implicit state, ad hoc execution order, and manual intervention. These characteristics are fine for research, but problematic for production systems. Understanding the role notebooks play helps engineers appreciate why a transition is necessary, rather than treating production constraints as unnecessary friction. Notebooks fail in production because they hide complexity. Execution order matters, but it's often unclear. State is shared implicitly across cells, making behavior difficult to reproduce. Versioning notebooks is challenging, and testing individual components is awkward. Notebooks also lack clear interfaces. There's no obvious entry point, error handling is inconsistent, and scaling execution is difficult. These issues make notebook-based systems fragile. In production, reliability matters more than convenience. That's why engineers must refactor notebook code before deployment, rather than attempting to productionize notebooks directly. Moving to production requires a mindset shift. Instead of asking, "Does this work once?" engineers ask, "Will this work every time?" Production systems must be deterministic, observable, and resilient to failure. Inputs and outputs must be explicit. Dependencies must be declared. Failures are expected and handled gracefully rather than ignored. This mindset shift is often more challenging than learning new tools. It requires thinking ahead, anticipating problems, and designing systems that behave predictably under real-world conditions. Refactoring is a key step in moving to production. Core logic should be moved into functions and classes with clear responsibilities. Data processing, model training, and inference should be separated into distinct modules. Configuration should be externalized using files or environment variables rather than hard-coded values. Implicit state must be eliminated. Logging and error handling should be added to make behavior observable. This refactoring improves clarity, testability, and maintainability, making the system suitable for long-term use. Reproducibility is non-negotiable in production. Engineers must pin library versions to avoid unexpected behavior changes. Virtual environments or containers ensure consistent runtime environments across machines. Development, testing, and production environments should be clearly separated, each with its own configuration. Hardware dependencies, such as GPUs, must be explicitly managed. Without careful dependency management, systems may work on one machine but fail elsewhere. Production engineers design environments to be repeatable, predictable, and easy to recreate. Testing is how engineers build trust in systems. Unit tests verify core logic. Data validation checks ensure inputs meet expectations. Model sanity tests catch obvious failures early. Regression tests detect unintended changes over time. Tests are not a burden, they are signals. When a test fails, it provides valuable information about what broke and why. In production systems, testing is continuous. It protects reliability and allows teams to iterate with confidence rather than fear. Production readiness goes beyond it runs. Systems must have clear entry points, monitoring hooks, and configurable thresholds. There should be a rollback strategy in case something goes wrong. Documentation is essential, not just for users, but for operators who maintain the system. Deployment readiness means the system can be run, observed, and fixed by someone who didn't build it. This is a key distinction interviewers look for: the ability to think beyond code and consider the full life cycle of an AI system. Interviewers care deeply about this transition. They often ask candidates to describe how they would take a notebook and turn it into a production system. Strong answers highlight refactoring strategies, testing, dependency management, and monitoring. Interviewers want to see awareness of failure, scale, and maintainability, not just model performance. This lecture equips you to speak confidently about that transition and demonstrate production-first thinking, an essential skill for AI engineers in 2026. Once a model works, the next question is not how accurate is it, but how do other systems use it? This is where many AI projects break down. A model sitting in a notebook or script has no real value until it can be accessed reliably by applications, services, and users. Model packaging and APIs are what turn models into usable products. They define how models are loaded, how inputs are validated, and how outputs are returned consistently. In this lecture, we'll focus on how AI engineers expose models through APIs and how frameworks like FastAPI and Flask fit into production systems. In this lecture, we'll cover how AI models are packaged and exposed as APIs. We'll start by explaining why models must be treated as services rather than standalone artifacts. Then we'll discuss what model packaging actually involves and how APIs act as the contract between models and the rest of the system. We'll also compare FastAPI and Flask at a high level, focusing on engineering trade-offs rather than syntax. By the end of this lecture, you should understand how models move from code into reliable, production-ready services. Models do not live in isolation. In production, models are called by applications, pipelines, dashboards, and other services. APIs provide a standard interface that allows these systems to interact with models without knowing how they're implemented. APIs also decouple training from inference. Models can be updated, versioned, or replaced without breaking downstream systems. This separation is essential for scalability and long-term maintenance. From an engineering perspective, APIs turn models into reusable components. Without them, systems become tightly coupled, brittle, and difficult to evolve. Model packaging is about more than saving a file. It involves bundling the trained model, pre-processing logic, configuration, and inference code into a coherent unit. Clear steps must exist for loading the model, validating inputs, and producing outputs. Configuration, such as thresholds or model paths, should be externalized, not hard-coded. Models must be versioned so changes can be tracked and rolled back if needed. Good packaging ensures that the same model behaves consistently across environments. Poor packaging leads to hard-to-debug failures and deployment surprises. API design is a critical engineering skill. Inference APIs should have clear request and response schemas, so callers know exactly what to send and what to expect. Inputs must be validated explicitly to prevent unexpected behavior. Whenever possible, outputs should be deterministic or clearly documented when variability exists. Error messages should be meaningful, not cryptic. Business logic should live outside the API handler. The API's job is to translate requests into inference calls and return results cleanly. This separation improves maintainability and testability. FastAPI is a popular choice for production AI services. It is designed for high performance and supports asynchronous execution, which is useful for handling concurrent requests. One of its biggest advantages is automatic request validation based on defined schemas. FastAPI also generates interactive API documentation automatically, making services easier to test and integrate. Strong typing helps catch errors early during development. Because of these features, FastAPI is often preferred for new AI services where reliability, performance, and clarity matter. Flask is a lightweight and flexible web framework. It is easy to start with and gives developers full control over request handling. Flask has a large ecosystem and is widely used, especially in older or simpler systems. However, Flask requires more manual work. Input validation, schema enforcement, and documentation must be implemented explicitly. Flask is a good fit when simplicity or legacy compatibility is important. For larger production systems, engineers must be disciplined to avoid accumulating technical debt. Choosing between FastAPI and Flask is an engineering decision. FastAPI provides strong defaults for validation, typing, and performance, making it well-suited for production AI systems. Flask offers flexibility and simplicity, but places more responsibility on the developer. The right choice depends on team experience, project scale, and time constraints. There is no universally correct answer. In interviews, what matters is not which framework you choose, but how clearly you explain the trade-offs and justify your decision based on system requirements. Framework choice is only part of the story. Production systems must handle model loading efficiently, including warm-up and caching. Concurrency and throughput need to be considered, especially under load. Timeouts and rate limiting protect systems from abuse or runaway requests. Logging and monitoring provide visibility into system behavior. Security is also critical. Authentication and authorization ensure that only approved users can access model endpoints. These considerations apply regardless of the framework you choose. In interviews, API design is a proxy for production thinking. Interviewers look for clear service boundaries, well-defined input and output contracts, and awareness of scalability issues. They want to see that you understand how models fit into larger systems. Strong candidates can explain how they package a model, why they chose a particular framework, and how they would handle failures or scale. This lecture gives you the conceptual foundation to discuss model serving confidently and professionally in AI engineering interviews. As AI systems move into production, the biggest risk is not poor model accuracy, it's uncontrolled change. Models evolve, data shifts, and code updates happen constantly. Without automation, these changes introduce silent failures that are difficult to detect and expensive to fix. CI/CD for machine learning exists to bring discipline, safety, and repeatability to this process. Unlike traditional software, ML systems combine code, data, and probabilistic models, which makes deployment far more complex. In this lecture, we'll break down how CI/CD works for ML systems, what gets tested, what gets deployed, and how engineers reduce risk while still moving fast. This is a core skill for production AI engineers. In this lecture, we'll focus on CI/CD specifically for machine learning systems. We'll explain why ML systems require CI/CD, how ML pipelines differ from traditional software pipelines, and what components must be tested and deployed safely. We'll also explore how automation helps teams iterate quickly without breaking production systems. By the end of this lecture, you should understand how CI/CD reduces risk, improves reliability, and enables continuous improvement in AI systems. This topic is frequently discussed in interviews because it demonstrates whether a candidate understands real-world production challenges. Manual ML deployments are fragile. They rely on undocumented steps, inconsistent environments, and human judgment. This leads to errors that are hard to reproduce and even harder to debug. A model may work once, but fail silently the next time it's deployed. CI/CD replaces manual steps with automated pipelines. This ensures consistency across environments and reduces deployment risk. It also enables faster iteration because teams can deploy changes with confidence. For ML systems where behavior can change even without code changes, CI/CD is not optional, it's essential. ML CI/CD is more complex than software CI/CD. In traditional software, behavior is largely deterministic. In ML systems, behavior depends on code, data, and trained models. Even small changes in data can cause significant output differences. Models can regress in quality without breaking tests. Data distributions can shift over time. Performance must be measured, not assumed. Because of this, ML CI/CD must validate more than code. It must check data quality, model behavior, and system performance continuously. This is why ML pipelines require more safeguards and monitoring than standard software pipelines. Continuous integration for ML focuses on testing correctness and sanity. This includes code linting and unit tests, but also data validation to ensure schemas and distributions are as expected. Training pipelines should include basic sanity checks to catch obvious failures early. Reproducibility is critical. CI should verify that training runs can be repeated reliably with the same inputs. These tests don't guarantee a good model, but they prevent broken pipelines from progressing. CI acts as a quality gate that stops obvious issues before they reach production. Continuous deployment determines what gets released and how. In ML systems, deployment includes trained model artifacts, inference services, configuration files, and thresholds. Each deployment must be versioned and rollback ready. CG pipelines automate packaging, validation, and release steps. This reduces human error and ensures consistency across environments. Importantly, deployment does not always mean immediate production release. Models may be deployed to staging, shadow environments, or limited traffic scenarios before full rollout. CD enables controlled, gradual exposure rather than risky big bang releases. Model versioning is essential for traceability. Every trained model should be tracked with metadata, training data, parameters, metrics, and code versions. Model registries help manage this lifecycle. Promotion workflows move models from experimentation to staging and then to production. Approval gates, manual or automated, ensure quality checks are passed before promotion. Versioning allows teams to roll back quickly if issues arise. Without it, diagnosing failures becomes guesswork. Strong versioning practices are a hallmark of mature ML engineering teams. Automation is what makes CI/CD safe. Performance regression tests ensure new models don't degrade key metrics. Bias and fairness checks detect unintended impacts. Canary or shadow deployments limit blast radius by testing models on small traffic slices. Automated rollback triggers protect systems when metrics fall outside acceptable ranges. Alerts notify teams before failures escalate. These safeguards recognize an important truth: models will fail. CI/CD doesn't prevent all failures. It ensures failures are detected early and handled quickly. A wide ecosystem supports ML CI/CD. General-purpose CI tools like GitHub Actions or GitLab CI handle automation. ML-specific tools such as MLflow or Weights and Biases track experiments and models. Feature stores manage consistent data pipelines. Containers and registries standardize environments, while cloud-native pipelines orchestrate workflows at scale. The specific tools matter less than the principles behind them. Interviews focus on understanding why these tools are used and how they fit together, not on memorizing vendor details. CI/CD is a strong signal of production readiness in interviews. Interviewers want to see that you understand ML-specific risks and how automation reduces them. They look for clear testing strategies, safe deployment practices, and thoughtful rollback plans. Strong candidates explain how CI/CD supports experimentation without sacrificing reliability. They show awareness of data drift, model regressions, and monitoring needs. Being able to discuss ML CI/CD clearly demonstrates that you think beyond models and understand how real AI systems are built, deployed, and maintained in production. Shipping a model to production is not the finish line. It's the beginning of a new phase of risk. Once a model is live, the world starts changing around it. Data evolves, user behavior shifts, and assumptions made during training slowly become invalid. This is why monitoring and drift detection are critical parts of production AI systems. Without them, models can silently degrade for weeks or months before anyone notices. In this lecture, we'll explore what monitoring really means for ML systems, the different types of drift that occur in practice, and how engineers detect and respond to these changes before they cause real harm. In this lecture, we'll focus on model monitoring and drift detection. We'll explain why deployment is not the end of the ML lifecycle and why continuous monitoring is required to maintain trust in AI systems. You'll learn what aspects of a system should be monitored, how drift manifests in different forms, and how engineers design detection mechanisms. By the end of this lecture, you should understand how monitoring fits into production systems and how it enables teams to identify issues early before they turn into costly failures. Models operate in environments that change constantly. Input data distributions evolve as users, markets, and external conditions shift. Assumptions made during training slowly break, often without obvious errors or crashes. Unlike traditional software bugs, model failures are usually gradual. Accuracy degrades quietly. Predictions become less reliable, and business metrics drift downward. Monitoring exists to surface these changes early. Without it, teams may not realize a model is failing until significant damage has already occurred. Monitoring turns silent failures into visible signals that engineers can act on. Effective monitoring spans multiple dimensions. At the data level, engineers monitor input distributions and schema consistency. At the model level, they track prediction outputs, confidence scores, and error rates. At the system level, latency, throughput, and failure rates matter. Finally, business or task level metrics provide context about real-world impact. A technically accurate model that harms business outcomes is still a failure. Monitoring should be holistic. Focusing on only one layer leaves blind spots. Strong production systems combine technical and business signals to provide a complete picture of model health. Drift comes in several forms. Data drift occurs when input distributions change. Concept drift happens when the relationship between inputs and labels changes. Prediction drift reflects shifts in model outputs, even if inputs appear stable. Upstream pipeline changes, such as feature engineering updates, can also introduce drift. In many real systems, labels are delayed or unavailable, making drift harder to detect. Understanding these drift types helps engineers choose the right detection strategies. Not all drift is visible through accuracy metrics, and not all drift requires immediate retraining. Data drift detection focuses on input behavior. Engineers track feature statistics, monitor distributions, and compare current data to training baselines. Sudden changes may indicate upstream issues, while gradual shifts suggest environmental evolution. Statistical distance measures help quantify differences, and thresholds trigger alerts when changes exceed acceptable bounds. Schema checks catch missing or malformed inputs early. These techniques do not require labels, making them especially valuable in production environments where ground truth arrives late or not at all. Model and concept drift are harder to detect. Prediction distributions may shift even when inputs look normal. Confidence scores may decline, signaling uncertainty. When labels are available, delayed performance analysis can confirm degradation. In unlabeled environments, proxy metrics, such as agreement with baseline models, provide signals. Shadow models can be used to compare behavior without affecting production decisions. Detection is about patterns, not single events. Engineers look for sustained trends that indicate the model is no longer aligned with reality. Detection is only useful if it leads to action. Thresholds define what constitutes acceptable behavior. Alerts should be meaningful and actionable. Too many alerts lead to fatigue and ignored signals. Some responses can be automated, such as triggering retraining pipelines or rolling back to a previous model. Others require human review, especially for high-risk systems. Clear incident response playbooks define who responds, how decisions are made, and what steps follow. Monitoring without response plans is observability without control. Monitoring must be built into the system architecture. Logs and metrics flow through pipelines into dashboards that provide real-time and historical views. Some signals are monitored continuously, while others are analyzed in batches. Monitoring integrates closely with CI/CD, feeding data back into retraining and deployment workflows. Model registries track which versions are live and their performance over time. Good monitoring architecture provides visibility without overwhelming engineers. It surfaces the right signals at the right time. In interviews, monitoring questions reveal production maturity. Interviewers want to see that you understand drift, especially in environments without immediate labels. They care about practical strategies, not theoretical perfection. Strong candidates explain what they would monitor, how they would detect drift, and what actions they would take in response. They acknowledge uncertainty and describe how systems adapt over time. Being able to discuss monitoring clearly shows that you understand the full life cycle of AI systems, not just how to build models, but how to keep them reliable in the real world. Evaluating large language models is one of the hardest and most important problems in modern AI engineering. Unlike traditional ML models, LLMs are non-deterministic, context-sensitive, and often subjective in their outputs. There is rarely a single correct answer. This makes evaluation less about precision and recall and more about defining and measuring quality. In this lecture, we'll explore how engineers evaluate LLM systems both before and after deployment, how automated and human evaluations work together, and how quality metrics are operationalized in production. If you want to build reliable LLM-based systems in 2026, you must understand evaluation deeply. In this lecture, we'll focus on evaluation strategies and quality metrics for LLM-based systems. We'll start by explaining why evaluating LLMs is fundamentally different from evaluating traditional machine learning models. Then, we'll discuss what quality actually means in the context of language models and how it can be measured. We'll cover offline and online evaluation techniques, automated LLM-based evaluators, safety metrics, and how evaluations fit into CI/CD pipelines. By the end, you should be able to design evaluation strategies that support continuous improvement rather than one-time validation. LLMs are non-deterministic by design. The same prompt can produce different outputs across runs, even with identical inputs. Many tasks have no single correct answer, and quality often depends on context, tone, and user intent. Additionally, outputs are heavily influenced by prompt design, system instructions, and retrieved context. This makes it difficult to isolate whether changes in behavior are due to model updates, prompt changes, or data shifts. Because of this, evaluation must be probabilistic and comparative rather than absolute. Engineers must think in terms of trends, distributions, and relative improvements, not pass or fail correctness. Quality for LLMs is multidimensional. Helpfulness measures whether the response actually assists the user. Correctness and factuality assess whether information is accurate. Relevance ensures the response stays on task. Safety and alignment evaluate whether outputs follow policies and avoid harmful content. Consistency measures how stable outputs are across runs and inputs. Different applications prioritize different dimensions. A coding assistant values correctness, while a creative assistant values usefulness and tone. Defining quality explicitly is critical. Without clear definitions, evaluation becomes subjective and inconsistent, making it impossible to measure progress over time. Offline evaluation happens before deployment. It typically uses curated datasets containing prompts and expected behaviors. These datasets may include human-labeled examples or reference answers, depending on the task. Offline evals are useful for regression testing, ensuring that new models or prompts don't perform worse than previous versions. They are also used to compare models or prompt strategies. However, offline evaluations are limited. They represent a snapshot of expected usage and cannot capture all real-world scenarios. They should be treated as necessary but not sufficient validation. Online evaluation measures quality after deployment. This includes explicit user feedback, such as ratings, as well as implicit signals like retries, edits, or abandonment. A/B testing allows teams to compare prompts or models under real traffic. Canary or shadow evaluations expose new versions to limited traffic to observe behavior safely. Continuous measurement helps detect regressions and gradual quality decay. Online evaluation captures real usage patterns that offline tests miss. However, it requires careful design to avoid noisy signals and biased feedback. Both offline and online evaluations are essential for a complete picture. Automation plays a growing role in LLM evaluation. One common approach is the LLM as a judge pattern, where a model scores or compares responses based on a defined rubric. Pairwise comparisons often produce more reliable results than absolute scores. Automated evals scale well, but introduce risks. Evaluators may inherit biases from the model or be overly sensitive to phrasing. To mitigate this, engineers use structured rubrics, multiple evaluators, and spot checking with humans. Automated evaluation is powerful, but it must be used carefully and transparently. Not all evaluation focuses on success. Some focus on failure. Safety metrics measure hallucination rates, policy violations, toxic outputs, and inappropriate refusals. These metrics are especially important in high-risk domains. Evaluations may include adversarial prompts designed to probe system weaknesses. Coverage matters. Testing only happy paths gives a false sense of safety. Safety metrics should be tracked over time, not just at release. A system that becomes riskier over time is still a failure, even if average quality improves. Evaluations become most valuable when integrated into CI/CD. Eval suites act as quality gates that new models or prompts must pass before deployment. Regression detection identifies unintended changes early. Thresholds determine whether a model is promoted, rolled back, or flagged for review. Quality metrics are tracked over time to observe trends rather than single-point scores. This closes the feedback loop between development and production. Evals are no longer one-time checks. They become part of the system's ongoing health monitoring. In interviews, evaluation discussions reveal deep understanding. Interviewers want to see that you recognize LLM-specific challenges and can design practical evaluation strategies. They care about how you balance automated and human evaluation, and how you measure improvement over time. Strong candidates explain trade-offs clearly and acknowledge uncertainty. They focus on trends, guardrails, and feedback loops rather than perfect metrics. Being able to discuss LLM evals confidently signals that you understand not just how LLMs work, but how to operate them responsibly in production environments. One of the fastest ways AI systems fail in production is not accuracy. It's cost and performance. Many AI applications work technically but become unusable once traffic scales or latency frustrates users. This is especially true for LLM-based systems, where every token has a cost and every tool call adds delay. Cost optimization and latency management are not afterthoughts. They are core engineering responsibilities. In this lecture, we'll explore why these trade-offs exist, how engineers measure them, and how systems are designed to balance quality, speed, and cost. Understanding this is essential for building AI systems that can scale sustainably in the real world. In this lecture, we'll examine cost optimization and latency trade-offs in production AI systems. We'll start by explaining why cost and latency become critical once systems move beyond prototypes. Then, we'll explore how model choice, architecture, and system design influence both performance and spend. We'll also look at how engineers measure cost and latency, and how they make trade-offs explicit rather than accidental. By the end of this lecture, you should be able to reason clearly about efficiency, scalability, and sustainability, skills interviewers increasingly expect from AI engineers. AI system costs scale with usage. As traffic increases, LLM inference costs grow quickly. These costs are often non-linear, especially when retries, long probes, evaluations, and logging are added. Teams are frequently surprised by how fast spending accelerates. Hidden costs matter just as much as obvious ones. Poor prompt design, unnecessary tool calls, and lack of caching can dramatically increase spend without improving quality. Cost is not a finance problem, it's an engineering problem. Design decisions directly influence operational costs, which is why engineers must understand and manage them proactively. Latency directly affects user experience. Users care about how fast a system responds, especially for interactive applications. Time to first token often matters more than total response time. Even small delays can make systems feel unresponsive. Tool calls, retrieval steps, network hops, and cold starts all add latency. These delays compound in multi-step systems. Latency also impacts adoption. A highly accurate system that is slow will often lose to a slightly less accurate system that responds quickly. Engineers must design systems that meet both performance and usability expectations. Cost and latency are often in tension. Larger models may produce better results but cost more and respond more slowly. Smaller models are cheaper and faster but may require more retries or produce lower quality outputs. Caching can reduce both cost and latency but introduces complexity. Parallel execution improves latency but increases coordination overhead. There are no free optimizations. Every improvement comes with trade-offs. Strong engineers make these trade-offs explicit and intentional rather than discovering them accidentally after deployment. Model selection is one of the most powerful optimization levers. Different tasks require different levels of capability. Using the largest model for every request is rarely necessary. Tiered strategies route simple tasks to smaller models and reserve larger models for complex cases. Reducing prompt length, budgeting tokens, and tuning parameters like temperature and max tokens also reduce cost and latency. These optimizations often provide large gains with minimal impact on quality. They require thoughtful design rather than aggressive shortcuts. System architecture plays a major role in efficiency. Caching responses and embeddings avoids redundant computation. Batch inference improves throughput. Asynchronous execution allows systems to do useful work while waiting on external calls. Pruning unnecessary tool calls and adding early stopping conditions prevent wasted computation. These changes compound across the system. System-level optimizations often deliver larger gains than model tweaks. They require thinking holistically about how requests flow through the system rather than focusing on individual components. Optimization starts with measurement. Engineers track cost per request, cost per successful outcome, and total spend over time. Latency is measured using percentiles, not averages, to capture worst-case experiences. Token usage metrics reveal inefficiencies in prompt design. Correlating cost with quality helps teams understand where money is actually delivering value. Without measurement, optimization becomes guesswork. Production systems require data-driven decisions, not intuition. Good trade-offs require clear decision frameworks. Teams define acceptable latency budgets and cost targets based on business needs. Users may be segmented by service-level agreements with different performance expectations. Optimization focuses on business value, not just technical metrics. Trade-offs are revisited regularly as usage patterns change. Explicit frameworks prevent over-optimization and underinvestment. They help teams align engineering decisions with real-world priorities. In interviews, cost and latency discussions reveal practical experience. Interviewers want to see that you understand real-world constraints and can balance quality with efficiency. They look for measurement-driven reasoning, not vague optimization claims. Strong candidates explain trade-offs clearly, describe how they would measure success, and acknowledge that perfect solutions don't exist. Being able to discuss cost and latency intelligently signals that you think like a production engineer, not just a model builder. This is a key differentiator for AI engineering roles in 2026. This project represents the final step in becoming a production-ready AI engineer. Building models is only part of the job. What truly matters is whether those models can be deployed safely, observed continuously, and improved over time. In this project, you'll deploy an AI system as a real service and monitor it under realistic conditions. You'll track performance, quality, cost, and failures, just like a production team would. The goal is not perfection, but control. By the end, you should be able to explain not only what your system does, but how you keep it reliable once it's live. This is exactly the kind of thinking interviewers expect in 2026. This project is the capstone for the production AI engineering section. You'll deploy a working AI system and operate it as if it were running in production. That means exposing it through an API, monitoring its behavior, and responding to failures. Unlike earlier projects, success here is not measured only by correctness. Reliability, observability, and maintainability matter just as much. You are expected to think beyond, does it work? And ask, can this system be trusted over time? This project is designed to mirror real-world responsibilities of AI engineers working on live systems. The objective of this project is to build a deployable AI service that can be monitored and managed in production. Your system should accept real inputs, perform inference or agent actions, and return structured outputs. More importantly, it should be observable, meaning you can understand what it's doing and why. You will design the system so it can operate safely under real usage, handle errors gracefully, and provide the signals needed to detect problems early. This project focuses on operational excellence. It's about building something that works consistently, not just impressively. Your system must handle real-world behavior. It should accept user inputs, process them through a model or agents, and return responses in a predictable format. Errors should be handled explicitly rather than crashing the system. Logging is essential. Every important action, inputs, outputs, errors, and decisions should be recorded so you can trace behavior later. This scope ensures your system behaves like a real service, not a demo script. The goal is to expose the challenges that only appear once a system is running continuously and interacting with unpredictable inputs. Deployment is a core part of this project. Your model or agent must be packaged cleanly and exposed through an API. Configuration should be externalized, so environments can be changed without modifying code. Releases should be versioned, allowing you to roll back if something goes wrong. You should be able to redeploy the system reliably from scratch. These requirements reflect real production constraints. Interviewers care deeply about whether candidates understand how systems are actually deployed, not just how they're built. Once deployed, your system must be monitored. You should track input patterns, outputs, latency, throughput, and error rates. These signals help you understand whether the system is behaving as expected. Monitoring is not about collecting everything. It's about collecting the right signals. Too much noise makes problems harder to see. This project forces you to think carefully about what matters operationally. If something goes wrong, you should be able to detect it quickly and understand its impact. Over time, system behavior will change. Inputs may drift, outputs may shift, and quality may degrade. Your project should include mechanisms to detect these changes and compare current behavior to baselines. This may involve tracking distributions, proxy quality metrics, or delayed feedback. The goal is not perfect detection, but awareness, knowing when to retrain, adjust prompts, or rollback is a key production skill. This slide emphasizes that deployment is not a one-time event, it's an ongoing responsibility. Monitoring is only useful if it leads to action. You must define alert thresholds that indicate when something is wrong. Alerts should be actionable, not constant. Too many alerts lead to fatigue and ignored warnings. Some responses can be automated, such as restarting services or rolling back models. Others require human judgment. You should also think about incident response. Who responds, what steps are taken, and how the system is stabilized. This mindset separates production engineers from experimenters. Production systems must operate sustainably. You should track cost per request and enforce latency budgets. Optimization may include model selection, caching, or limiting expensive operations. The goal is not to minimize cost at all costs, but to balance efficiency with quality. These trade-offs should be explicit and measurable. This slide reinforces an important reality. Systems that are too expensive or too slow will not survive in production, regardless of how impressive they are technically. This project is a powerful interview artifact if framed correctly. When presenting it, focus on system design, monitoring choices, and how you handled failures or trade-offs. Be honest about what broke and how you fixed it. Interviewers care less about perfect results and more about how you reason under uncertainty. This project gives you a concrete example to demonstrate production thinking. If you could explain this system clearly, you are showing that you understand the full life cycle of AI systems, from deployment to long-term operation. One of the biggest misconceptions candidates have is believing that hiring decisions are purely technical. In reality, recruiters operate under intense constraints, limited time, high applicant volume, and pressure to reduce hiring risk. This lecture pulls back the curtain on how AI engineer candidates are actually evaluated, especially in the first stages of the hiring funnel. We'll separate myths from reality, focus on the signals recruiters truly care about, and explain why strong candidates are often rejected despite solid skills. Understanding this perspective allows you to design your resume, portfolio, and online presence to work with the hiring process, not against it. In this lecture, we'll focus on what recruiters actually look for when hiring AI engineers. We'll explore how hiring decisions are made under real-world constraints, and why many traditional credentials don't carry as much weight as candidates expect. You'll learn which signals recruiters rely on, which ones they ignore, and how early filtering really works. By the end of this lecture, you should understand how to position yourself clearly and convincingly so recruiters can quickly recognize your fit for a role. This is about reducing friction and ambiguity in the hiring process. Recruiters operate under severe constraints. For a single role, they may receive hundreds of applications. They often lack deep technical expertise and must make quick decisions based on limited information. Their goal is not to find the best candidate. It's to find safe candidates who are likely to pass later interviews. This creates a risk reduction mindset. Recruiters look for clear alignment, recognizable patterns, and signals that reduce uncertainty. Understanding these constraints is critical. If your profile requires careful interpretation, it's likely to be skipped, even if you're highly qualified. Recruiters prioritize clarity over complexity. They look for clear role alignment. Does this person obviously fit the job? Evidence of real-world impact matters more than theoretical knowledge. Production experience, even at small scale, is a strong signal. Communication is also critical. Can you explain what you've done clearly and concisely? Consistency across your resume, LinkedIn, and portfolio builds trust. Recruiters are not evaluating depth. They are evaluating signal strength. The easier it is for them to understand your value, the more likely you are to move forward. Many candidates overinvest in low signal credentials. Long lists of tools without context don't help. Generic certificates rarely differentiate candidates. Buzzwords without concrete examples raise red flags. Deep academic knowledge without application is often ignored at early stages. Overly complex side projects can actually hurt if their value isn't obvious. Recruiters are not impressed by difficulty, they are impressed by relevance. If a signal does not clearly map to the role, it is unlikely to help you pass the initial screen. Resumes are scanned quickly, often in under 15 seconds. Recruiters skim for relevance first. They look at titles, keywords, and bullet points to determine whether you're a match. Dense paragraphs slow this process and reduce clarity. Strong resumes focus on outcomes rather than responsibilities. They show what you built, why it mattered, and what changed as a result. Red flags, such as vague descriptions or inconsistent timelines, can eliminate candidates immediately. Your resume's job is not to tell your life story, it's to pass the first filter. Projects are one of the strongest signals when done correctly. Recruiters want to see clear problem statements, realistic constraints, and evidence of production thinking. They care less about novelty and more about execution. Measurable results, even simple ones, add credibility. The ability to explain trade-offs and decisions matters more than complexity. A strong project answers one question clearly. Would I trust this person to work on a real system? If that answer is yes, the project has done its job. Your online presence reinforces or undermines your resume. Recruiters often check LinkedIn to validate claims and understand your professional narrative. A clear headline, consistent messaging, and evidence of engagement all matter. Visible learning, thoughtful posts, or shared projects signal genuine interest and growth. Inconsistencies between LinkedIn and your resume create doubt. Your goal is credibility. Recruiters are not looking for influencers, they are looking for professionals who take their craft seriously and communicate clearly. Many strong candidates are rejected for non-technical reasons. Misaligned role targeting is common, applying broadly without tailoring. Vague experience descriptions force recruiters to guess, which they won't do. Lack of production exposure raises concerns, especially for senior roles. Poor communication during early conversations can outweigh technical ability. Weak storytelling, failing to explain why your work mattered, also hurts candidates. Rejection is often about uncertainty, not capability. Reducing that uncertainty is key. This lecture should change how you approach job applications. Instead of trying to impress, focus on clarity. Optimize your materials to make recruiter decisions easy. Show evidence, not claims. Think like a hiring team. Ask yourself, if I saw this resume quickly, would I understand why this person fits the role? Recruiters are gatekeepers, not enemies. When you understand how they evaluate candidates, you can align your strategy and dramatically increase your chances of moving forward. Many candidates build technically impressive AI projects, yet still struggle to get interviews. The problem is rarely skill, it's structure. Hiring teams don't have time to reverse engineer what your project means or why it matters. This lecture focuses on how to structure AI projects so their impact is immediately clear. We'll move beyond tools and models to focus on problem definition, system design, decision-making, and outcomes. When projects are structured correctly, they become powerful hiring signals that communicate readiness for real-world work. This is about making your effort visible, understandable, and credible to the people evaluating you. In this lecture, we'll explore how to structure AI projects for maximum impact. We'll explain why many projects fail to impress despite strong technical work, and what hiring teams actually look for when reviewing projects. You'll learn how to frame problems, show system-level thinking, and communicate decisions clearly. By the end of this lecture, you should be able to restructure existing projects or design new ones so their value is obvious within seconds. This clarity is what turns projects into interview opportunities. Most AI projects fail because they lack clarity. They jump straight into tools or models without explaining the problem being solved. They operate in unrealistic settings that don't resemble real-world constraints. Outcomes are often vague or undefined. Hiring teams don't want to guess why a project matters. If the value isn't clear immediately, they move on. This slide highlights common mistakes so you can avoid them. Strong projects are not necessarily complex. They are understandable, relevant, and grounded in real problems. Great projects start with a clear problem statement. Who is the user? What pain point are you addressing? Why does this problem matter? These questions should be answered before any technical details appear. Defining success criteria early shows maturity. It tells reviewers that you understand what good looks like. Constraints such as cost, latency, or data availability should be stated up front. When you lead with the problem, the rest of the project becomes easier to understand. The model becomes a tool, not the headline. Hiring teams care about systems, not just models. They want to see how data flows, how inference happens, and how failures are handled. Showing only a model notebook hides important engineering decisions. This slide emphasizes the importance of describing the full system: data ingestion, pre-processing, model selection, inference logic, and monitoring. System-level thinking signals readiness for real-world work. It shows you understand how models live inside larger applications and how things can go wrong in production. Trade-offs are where engineering judgment shows. Why did you choose this model instead of another? Why this architecture? What options did you consider and reject? Making trade-offs explicit demonstrates that decisions were intentional, not accidental. It also shows awareness of cost, latency, and complexity. Perfect solutions don't exist. Hiring teams want to see how you reason under constraints. This slide teaches you to surface that reasoning clearly, rather than hiding it. Impact must be measurable. Define metrics that matter for the problem you're solving. Compare before and after states. Show how quality, reliability, or efficiency improved. If metrics are imperfect, explain their limitations. Honesty builds credibility. Avoid vague claims like performed well without evidence. Clear impact measurement helps reviewers understand why your project matters. It turns effort into evidence and learning into results. Documentation is part of the project. A strong README includes a clear overview, architecture diagrams, setup instructions, and usage examples. It also documents decisions, known issues, and next steps. Professional documentation signals that you think beyond yourself. It shows you expect others to read, use, and maintain your work. This slide reinforces that documentation is not busy work. It's communication, and communication is a core engineering skill that hiring teams value highly. That matters more than quantity. One well-structured end-to-end project is more valuable than several shallow ones. Hiring teams prefer projects that show ownership and follow-through. Realistic scope demonstrates judgment. Overly ambitious projects often remain unfinished or unclear. This slide encourages you to focus on projects that reflect real constraints and could plausibly exist in production. Depth signals maturity and readiness for responsibility. Projects are conversation starters in interviews. Interviewers look for clarity of explanation, decision-making maturity, and how you handled constraints and failures. They are less interested in perfect outcomes than in thoughtful reasoning. Strong candidates use projects to tell clear stories: what they built, why it mattered, and what they learned. This lecture equips you to turn projects into narratives that demonstrate readiness for real-world AI engineering roles. Most AI projects don't fail because the code is bad. They fail because no one understands them. In hiring, reviewers rarely run your code. They read your README to decide whether your project is worth their time. That makes the README one of the most important artifacts you'll ever write as an AI engineer. It's not documentation for yourself. It's communication for strangers under time pressure. In this lecture, we'll break down how READMEs are actually read, what sections matter most, and how to structure them so your work is immediately clear. A strong README doesn't just explain your project, it earns you an interview. In this lecture, we'll focus on how to write README files that help you get interviews. We'll explain why READMEs often matter more than the underlying code, how recruiters and engineers actually read them, and what separates strong READMEs from forgettable ones. You'll learn a proven structure that makes projects easy to understand quickly. By the end of this lecture, you should be able to write READMEs that communicate value clearly, reduce reviewer uncertainty, and position your projects as evidence of real-world engineering readiness. For most reviewers, the README is the project. Hiring managers and recruiters usually don't have time to run code or explore notebooks. The README is what sets context, explains intent, and determines whether they keep reading. A weak README creates confusion, even if the project itself is strong. A clear README can elevate a simple project by making its value obvious. This is why READMEs matter so much. They act as a filter. If your README doesn't communicate relevance and clarity quickly, your project will likely be skipped, regardless of technical depth. READMEs are skimmed, not studied. Most reviewers spend 30 to 60 seconds on an initial scan. They look at headings, bullet points, diagrams, and short sections, not long paragraphs. Clear structure matters more than writing style. Headings help reviewers orient themselves. Visual separation reduces cognitive load. If reviewers feel lost or overwhelmed, they stop reading. Ambiguity causes drop-off. This slide emphasizes that your README should be designed for skimming first and deep reading second. Strong READMEs follow a predictable structure. They start with a concise overview that explains what the project does and why it exists. Then, they clearly define the problem, describe the system at a high level, and explain how it works. Results and impact come next, followed by instructions on how to run the project. Finally, limitations and next steps show maturity and honesty. This structure reduces guesswork. Reviewers know where to look for answers. A familiar structure makes your project easier to evaluate and more likely to be remembered. The project overview is the most important section. In the first 5 lines, reviewers should understand what the project does, who it's for, and why it matters. This is not the place for buzzwords or hype. A good overview focuses on the problem and the outcome, not the tools used. It sets expectations and invites the reader to continue. If the overview is unclear, the rest of the README won't be read. This slide reinforces that clarity upfront determines whether your project gets attention at all. After the overview, reviewers want to understand how the system works. This is where architecture diagrams shine, even simple ones. Explain how data flows, how models or agents are used, and how key components interact. You should also explain why certain choices were made. Why this model? Why this approach? Show that decisions were intentional. Mention failure handling where relevant. This signals production awareness. The goal is not exhaustive detail, but enough context to demonstrate system-level thinking. Professional READMEs are honest. They present results using meaningful metrics, but they also discuss trade-offs and limitations. What worked well? What didn't? What constraints influence decisions? This honesty builds credibility. Hiring teams don't expect perfect systems, they expect thoughtful engineers. Acknowledging limitations shows maturity and self-awareness. It also gives interviewers something concrete to discuss. This section often becomes the most valuable part of the README during interviews. Respect the reader's time. Setup instructions should be clear, concise, and complete. Dependencies must be listed explicitly. Example commands help reviewers understand how the system runs. Include expected outputs so users know what success looks like. Mention common failure points and how to fix them. Even if reviewers never run the code, this section signals professionalism. It shows you think about usability and reproducibility, core traits of strong engineers. Great READMEs make interviews easier. They reduce uncertainty, communicate competence, and give interviewers a clear mental model of your work. This shifts interviews from explain what you did to let's discuss your decisions. A strong README demonstrates communication skills, production thinking, and respect for the reader's time. These are senior level signals. If your README is clear, your project becomes an asset rather than a hurdle. This lecture equips you to turn your work into interview opportunities through effective documentation. Many candidates build solid projects, but struggle to talk about them in interviews. The missing piece is often not technical depth, it's narrative. Hiring teams don't just want to see what you built, they want to understand how you think, how you make decisions, and how you handle trade-offs. That's where case studies come in. Case studies turn projects into stories that highlight reasoning, impact, and growth. In this lecture, we'll learn how to transform your technical work into compelling case studies that are easy to discuss in interviews. This approach helps interviewers evaluate you quickly and remember you afterward. In this lecture, we'll explore how to turn AI projects into strong case studies. We'll explain why case studies are more effective than raw project descriptions and how hiring teams evaluate them. You'll learn what makes a case study compelling and how to structure one so it highlights your thinking, not just your output. By the end of this lecture, you should be able to present your projects as clear, decision-driven narratives that make interviews easier and more engaging for both you and the interviewer. Projects show what you built, but case studies show how you think. Hiring teams are trying to assess judgment, not just execution. They want to know how you approached the problem, what constraints you faced, and how you navigated uncertainty. Case studies provide context. They explain why decisions were made and what trade-offs were considered. This makes your work more memorable and easier to evaluate. A well-told case study can make a simple project impressive. Without one, even complex projects can feel flat or confusing to reviewers. Writing a case study requires a mindset shift. Instead of listing features or tools, you think like a consultant explaining a solution to a client. You start with the problem, clarify goals, and describe constraints. You then walk through key decisions and explain why certain paths were chosen over others. Finally, you reflect on outcomes and lessons learned. This mindset highlights reasoning and ownership. It shows that you didn't just follow a tutorial, you engaged with real-world ambiguity and made informed choices. Strong case studies follow a clear structure. They begin with background and problem context, followed by goals and success criteria. Constraints and assumptions come next, setting boundaries for decisions. The solution design explains the system at a high level, focusing on reasoning rather than implementation detail. Results and impact show what changed. Finally, trade-offs and lessons learned demonstrate maturity. This structure helps reviewers quickly understand what matters and why your decisions make sense in context. Decisions are the heart of a good case study. Explain why you chose one approach over another. What alternatives did you consider? What risks did you accept? Highlighting trade-offs shows that you understand engineering reality. There are always constraints, and perfect solutions don't exist. This is exactly what interviewers want to see. Avoid tool-centric storytelling. Tools are replaceable. Judgment is not. When you emphasize decisions, you make your case study about your thinking, not your tech stack. Impact turns effort into evidence. Show what changed because of your work. Compare before and after states. Use metrics where possible and explain why those metrics matter. Impact doesn't have to be massive. Even small improvements in reliability, efficiency, or clarity are meaningful when explained well. This slide reinforces that hiring teams care about outcomes. They want to know whether your work made something better and how you measured that improvement. Failures are powerful signals when handled correctly. Strong case studies don't hide what went wrong. They explain what broke, why it broke, and how it was fixed. This shows resilience and learning. Discussing failures also demonstrates responsibility. It signals that you understand the consequences of decisions and take ownership of outcomes. Interviewers often probe this section deeply. Honest reflection builds trust and creates meaningful discussion. Avoid defensiveness. Focus on learning and improvement. Case studies can live in many formats. They might be standalone pages on a portfolio site, sections within a README, blog-style write-ups, or slide decks used during interviews. What matters is consistency. The story should be clear regardless of format. Choose formats that fit your audience and make your work easy to access. Having case studies in multiple places reinforces your narrative and increases the chance that hiring teams will encounter and remember your work. Case studies transform interviews. They give interviewers a concrete system to discuss, reducing abstract questioning. They demonstrate senior-level thinking, ownership, and accountability. Strong case studies create natural follow-up questions and deeper technical conversations. They shift interviews from interrogation to collaboration. If you can walk through a case study clearly, you signal readiness for real-world AI engineering roles. This lecture equips you to turn your projects into stories that win interviews. Open source contributions are one of the most misunderstood signals in AI engineering careers. Many candidates think they need to build a famous library or rack up hundreds of commits to stand out. That's not how hiring teams actually evaluate open source. What matters is how you contribute, not how much. Open source is valuable because it exposes how you work with existing code, how you communicate with maintainers, and how you respond to feedback. In this lecture, we'll focus on building a strategic open source contribution approach that creates real hiring signal without burning yourself out or chasing vanity metrics. In this lecture, we'll talk about how to use open source contributions strategically. We'll explain why open source matters in hiring, separate myths from reality, and define what actually counts as a strong contribution. You'll learn how to choose the right projects, how to start contributing effectively, and how to communicate your work so it's visible and credible. By the end of this lecture, you should understand how to turn open source contributions into clear career leverage, not just GitHub activity. Open source signals real-world engineering behavior. It shows that you can read and understand existing code bases, follow conventions, and collaborate with others. Hiring teams value this because most engineering work happens inside existing systems, not greenfield projects. Open source also demonstrates comfort with feedback. Code reviews, comments, and revisions mirror how teams operate internally. Most importantly, open source shows initiative. You're choosing to engage with real problems without being assigned work. That combination of collaboration, discipline, and ownership makes open source a powerful hiring signal. Many candidates avoid open source because of misconceptions. You don't need to create a popular library. You don't need hundreds of commits. You don't need to solve the hardest problems or become a maintainer. These expectations are unrealistic and unnecessary. Hiring teams don't evaluate fame. They evaluate substance. A small number of thoughtful, well-executed contributions is far more valuable than a long list of superficial commits. This slide helps reset expectations so you can focus on contributions that actually matter. Strong contributions solve real problems. Bug fixes with clear impact, documentation improvements that reduce confusion, and tests that increase reliability all matter. Small features that improve usability are often more valuable than large, risky changes. Well-scoped pull requests are easier to review and more likely to be merged. They also show that you understand how to work within constraints. Quality, clarity, and relevance define strong contributions. Hiring teams care far more about what you contributed and why than how impressive it looks at first glance. Not all projects are equal for career impact. Choose projects that align with the roles you're targeting. Look for active repositories with maintainers who respond to issues and pull requests. Clear contribution guidelines signal a healthy project. Reasonably scoped issues make it easier to succeed. A supportive review culture increases learning. Strategic project selection maximizes return on effort. One relevant contribution to the right project can be more impactful than many contributions to projects no one recognizes. Starting is often the hardest part. Begin by reading the documentation and open issues. Look for good first issue labels. Try to reproduce bugs locally to understand the problem deeply. Ask clarifying questions before writing code. This shows respect for maintainer's time and reduces rework. When you submit a pull request, keep it focused and well explained. This process mirrors professional engineering workflows. The goal is not speed, it's correctness, communication, and learning. How you communicate matters as much as what you code. Clear commit messages explain intent. Thoughtful pull request descriptions outline the problem, the solution, and any trade-offs. Linking issues and discussions provides context. These communication artifacts become part of your public engineering record. They show how you reason and collaborate. When listing open source work on your resume, reference specific contributions and outcomes, not just repository names. This turns activity into signal. Open source can backfire if approached poorly. Overly large pull requests are hard to review and often rejected. Ignoring maintainer feedback signals poor collaboration. Drive-by contributions without context create friction. Contributing only for optics is transparent and rarely effective. Overcommitting can also lead to burnout. This slide emphasizes sustainability and professionalism. Open source should enhance your career, not drain your energy or damage your reputation. In interviews, open source discussions reveal a lot. Interviewers ask about contributions to understand how you navigate existing code, collaborate with others, and respond to feedback. They're less interested in volume and more interested in depth. Strong candidates can explain what they contributed, why it mattered, and what they learned. They treat open source as a learning environment, not a trophy case. This lecture equips you to use open source intentionally as a credible signal of readiness for real-world AI engineering work. A personal website is not about showing off design skills or building something flashy. For AI engineers, it's about control over how your story is told. Resumes are constrained. LinkedIn is noisy. A personal website is the one place where you can clearly explain who you are, what you build, and why you're a strong fit for a specific role. In this lecture, we'll focus on how hiring teams actually use personal websites, what sections matter most, and how to avoid common mistakes. When done right, a personal website quietly removes doubt, reinforces your narrative, and makes interviews easier before they even begin. In this lecture, we'll explore how AI engineers should approach building a personal website. We'll discuss why personal sites still matter, how recruiters and hiring managers actually use them, and what makes a site effective rather than distracting. We'll also cover common mistakes that reduce credibility instead of building it. By the end of this lecture, you should understand how to design a simple, professional website that reinforces your resume, highlights your work, and communicates your value clearly without unnecessary complexity. Your personal website is your controlled narrative. Unlike resumes or social platforms, it allows you to explain your work in your own words, at your own depth. You can connect projects, case studies, and writing into a coherent story. Hiring teams use personal websites to reduce uncertainty. When they can clearly see what you do and how you think, they feel more confident moving you forward. A strong website doesn't replace your resume. It amplifies it, it fills in the gaps, and makes your profile feel complete and credible. Recruiters don't explore websites deeply, they skim. Most spend less than 2 minutes looking for signals: role alignment, project relevance, and consistency with your resume. They're validating claims, not discovering hidden gems. If your site is confusing or vague, it works against you. If it's clear and focused, it builds trust quickly. This slide emphasizes that your website should be optimized for fast comprehension. Make it easy for reviewers to understand who you are and why you're relevant, without effort. A strong personal website doesn't need many pages, it needs the right ones. At minimum, you need a homepage that clearly positions you, an About section for context, a projects or case studies section, a resume or CV, and clear contact information. Each section should serve a purpose. If a page doesn't reduce uncertainty or add clarity, it probably doesn't belong. This slide reinforces that simplicity is a strength. Hiring teams value clarity far more than volume. Your homepage is the most important part of your site. Within a few seconds, visitors should know who you are, what roles you're targeting, and what kinds of systems you build. Vague taglines like AI enthusiast or tech innovator add no value. Strong homepages are specific. They name roles, domains, and strengths. They communicate confidence without hype. If a recruiter only sees your homepage, they should already have a clear sense of whether you're relevant. That's the goal of good positioning. Projects are where credibility is built. Your website should link to a small number of strong case studies rather than many shallow projects. Each project should show system design, decisions, and impact, not just screenshots or code links. Navigation should be simple. Reviewers should never wonder where to click next. This slide reinforces that your website is not a gallery, it's an argument. Every project exists to answer one question: would I trust this person to work on real systems? Writing is optional, but powerful when done well. Short blog posts, technical notes, or reflections on lessons learned can signal depth and growth. The goal is not volume, but insight. Posts grounded in experience are far more valuable than generic tutorials. Consistency matters more than frequency. This section is optional because poorly executed writing can hurt credibility. Only include it if you have something thoughtful to say and can maintain a professional standard. Design should never compete with content. Fast load times, clean typography, and minimal distractions matter more than animations or complex layouts. Your site should work well on mobile and be easy to read. Accessibility basics like readable contrast and simple navigation signal professionalism. This slide emphasizes restraint. A professional website feels calm, focused, and intentional. If reviewers notice the design more than the content, something is wrong. A good personal website makes interviews easier. It reinforces your narrative, gives interviewers context, and provides concrete examples to discuss. It also signals initiative and ownership, qualities hiring teams value. Strong websites quietly differentiate candidates. They don't shout for attention, they reduce doubt. If your website helps interviewers understand you before the first call, you've already done part of the job. This lecture equips you to build a site that works for you in the hiring process. Before you start applying for roles, there's one step that's often skipped, but makes a huge difference: an honest portfolio review. Many candidates are technically capable, yet their portfolios quietly signal confusion, lack of focus, or inexperience. This lecture is designed as a final quality gate. We'll walk through a practical checklist that hiring teams implicitly apply when reviewing portfolios. The goal is not perfection, it's clarity. By the end of this lecture, you should be able to look at your portfolio through a recruiter's eyes and make targeted improvements that increase your chances of getting interviews. In this lecture, we'll review a comprehensive checklist to evaluate your portfolio. we'll focus on why portfolios often fail at the last mile and how hiring teams actually assess them. You'll learn how to self-review your work objectively and identify gaps that create uncertainty for reviewers. This checklist is meant to turn a good portfolio into an interview-ready one. It helps you remove noise, highlight strengths, and align your materials with what hiring teams are looking for in AI engineers. Your portfolio represents much more than your projects. It signals how you think, how you communicate, and how seriously you take your work. Hiring teams infer your engineering judgment, production awareness, and ownership mindset from what you choose to include and what you leave out. A strong portfolio feels intentional. A weak one feels random or unfocused. This slide emphasizes that every element of your portfolio sends a signal, whether you intend it or not. Being deliberate about those signals is what separates interview-ready candidates from overlooked ones. Clarity is the first test your portfolio must pass. A recruiter should understand your target role, domain focus, and relevance within 30 seconds. If they have to guess what kind of role you're aiming for, you've already lost momentum. Consistency matters. Your resume, website, GitHub, and LinkedIn should tell the same story. Conflicting narratives create doubt. This slide reinforces that positioning is not about limiting yourself. It's about making your strengths immediately visible to the right audience. Projects are the core of your portfolio. Each project should start with a clear problem statement and operate under realistic constraints. Hiring teams look for evidence of end-to-end thinking, not isolated experiments. Outcomes matter. What changed because of your work? Even small improvements are meaningful when explained clearly. Honest discussion of limitations signals maturity. This slide helps you assess whether your projects demonstrate readiness for real-world AI engineering rather than just technical curiosity. Strong documentation is non-negotiable. Every project should have a clear README that explains the problem, the system, and the results. Architecture diagrams help reviewers understand your thinking quickly. Setup instructions should be easy to follow, even if reviewers never run the code. Trade-offs and decisions should be documented explicitly. This slide emphasizes that documentation is part of the work, not an afterthought. Clear documentation reduces reviewer effort and builds trust. Hiring teams look for production awareness. Do your projects include APIs or service interfaces? Have you thought about monitoring, error handling, or fallbacks? Are cost and latency considerations acknowledged? These signals show that you understand how AI systems operate beyond notebooks. Even simple acknowledgments of production concerns can significantly increase credibility. This slide encourages you to surface production thinking explicitly, rather than assuming reviewers will infer it. Claims without evidence are weak signals. Strong portfolios include proof, live demos, screenshots, GitHub links with context, open source contributions, or detailed case studies. External validation, such as merged pull requests or community feedback, adds credibility. What matters is not popularity, but substance. This slide reinforces that evidence reduces uncertainty. The easier it is for reviewers to verify your claims, the more confident they feel in moving you forward. Certain patterns trigger silent rejection. Tool dumping without explanation suggests shallow understanding. Over-engineered demos raise concerns about judgment. Vague project descriptions force reviewers to guess. Lack of production perspective is a common issue, especially for senior roles. Inconsistent or outdated content undermines credibility. This slide helps you identify and remove red flags before reviewers see them. Often, removing one weak element can significantly improve overall perception. The final mindset shift is simple. Think like a hiring team. Your goal is to reduce effort for the reviewer. Make strengths obvious. Remove unnecessary noise. Invite deeper discussion rather than forcing explanation. A strong portfolio makes it easy to say yes and hard to say no. It doesn't try to impress, it communicates clearly. This lecture equips you with a practical lens to evaluate your portfolio before applying, increasing your chances of moving forward in the hiring process. Not all AI engineer interviews are designed the same way, and preparing as if they are is one of the biggest mistakes candidates make. Companies interview the way they hire, and how they hire reflects their scale, risk tolerance, and operating model. In this lecture, we'll break down how interview formats differ across FAANG companies, startups, and large enterprises. You'll learn what each type of employer is really trying to measure, why certain interview styles exist, and how to tailor your preparation accordingly. Understanding this context allows you to focus your effort where it matters most and avoid preparing for the wrong signals. In this lecture, we'll explore the different interview formats used to hire AI engineers. We'll compare how FAANG companies, startups, and enterprises structure interviews and what each format is designed to evaluate. You'll learn why interviews look the way they do and how those structures reflect the organization's needs and risk model. By the end of this lecture, you should be able to recognize interview patterns quickly and adjust your preparation strategy to match what each company type values most. Interview formats are not arbitrary. Their primary goal is risk reduction, predicting how a candidate will perform on the job. Large companies rely on standardized formats to ensure fairness and consistency across thousands of hires. Smaller companies prioritize flexibility and speed. Interviews are designed to produce comparable signals across candidates, even if those signals don't perfectly reflect real work. Understanding this helps you avoid frustration and focus on what's being measured. This slide emphasizes that interviews test predictability, not brilliance. Preparation should target the signals the format is designed to extract. FAANG-style interviews are highly structured. Candidates typically go through multiple rounds covering coding, machine learning fundamentals, and system design. These interviews emphasize consistency and comparability across candidates. The focus is on core skills rather than specific tools. You're expected to reason clearly, communicate your thought process, and perform under time pressure. This structure allows large organizations to maintain a high bar while hiring at scale. Understanding this helps you prioritize fundamentals and structured problem solving when preparing for FAANG-style interviews. FAANG companies look for strong fundamentals. They evaluate algorithmic thinking, core ML and deep learning knowledge, and your ability to reason through unfamiliar problems. Communication is critical. Interviewers want to hear how you think, not just your final answer. System design rounds assess scalability and trade-off awareness. Can you design systems that work at massive scale? This slide reinforces that FAANG interviews reward depth and clarity, not shortcuts. Strong preparation focuses on fundamentals rather than memorizing frameworks or tools. Startup interviews are usually faster and less standardized. They often involve fewer rounds and rely heavily on projects, take-home assignments, or live problem-solving sessions. Candidates may interact directly with founders or engineering leads. The goal is to assess whether you can operate independently and deliver value quickly. Startups have less margin for error and fewer resources for onboarding. This structure favors candidates who can demonstrate end-to-end ownership and practical judgment. Understanding this helps you prepare stories and projects that show real-world impact. Startups prioritize execution and adaptability. They want engineers who can build, debug, and ship with minimal guidance. Production readiness matters more than theoretical depth. Speed and pragmatism are valued over perfection. Candidates are evaluated on how they handle ambiguity and constraints. Can you make reasonable decisions without perfect information? This slide highlights that startups look for evidence of ownership, learning ability, and judgment. Preparation should emphasize projects, trade-offs, and lessons learned from real systems. Enterprise interviews sit between FAANG and startups. They are often structured but less algorithm-heavy. Interviews focus on applied machine learning, system reliability, and cross-team collaboration. Behavioral interviews carry more weight, especially around communication and stakeholder interaction. Enterprises care deeply about stability, governance, and long-term maintenance. Hiring cycles tend to be longer and more conservative. This structure reflects the need to integrate new hires into large, established systems with minimal risk. Enterprises value reliability and consistency. They look for engineers who can work within constraints, communicate with non-technical teams, and maintain systems over time. Production experience and monitoring awareness are strong signals. Risk management, compliance, and incremental improvement matter more than aggressive experimentation. This slide emphasizes that enterprise interviews reward maturity and predictability. Candidates should prepare examples that demonstrate steady delivery, collaboration, and thoughtful decision-making. Effective interview preparation is targeted. Rather than preparing one generic way, align your preparation with the company type. Emphasize fundamentals for FANG, projects and ownership for startups, and reliability for enterprises. Use the same experiences differently depending on the audience. A project can highlight scalability, pragmatism, or governance depending on what's valued. This slide reinforces that smart preparation is about alignment. When you match your signals to the employer's expectations, interviews become far more predictable. Python coding interviews are one of the most misunderstood parts of the AI engineer hiring process. Many candidates believe these interviews are about clever tricks or memorizing problems. In reality, they are about clarity, correctness, and how you think under constraints. Interviewers are not just evaluating whether you reach the right answer. They are watching how you reason, how you communicate, and how you handle mistakes. In this lecture, we'll break down the most common Python interview patterns, the pitfalls that quietly eliminate candidates, and how to write code that interviewers actually want to see. This is about turning Python interviews into a predictable, manageable part of the process. In this lecture, we'll focus on Python coding interviews and how they're actually evaluated. We'll look at the most common question patterns, the skills interviewers are testing, and the mistakes that frequently cost candidates offers, even when the final solution is mostly correct. You'll also learn how interviewers think while watching you code. By the end of this lecture, you should understand how to approach Python interviews calmly, communicate effectively, and write clean, correct solutions that demonstrate strong engineering fundamentals. Python interviews test far more than syntax. Interviewers are evaluating how you approach a problem, how clearly you reason through it, and whether you consider edge cases. Code readability matters just as much as correctness, especially in Python. They're also observing how you communicate while coding. Do you explain assumptions? Do you clarify requirements? Do you recover gracefully from mistakes? This slide emphasizes that Python interviews are about thinking, not tricks. Clean logic and clear communication consistently outperform clever but fragile solutions. Most Python interview questions fall into familiar patterns. Arrays, strings, and hashmaps appear frequently. Sliding window and two-pointer techniques are common because they test reasoning about state and efficiency. Basic recursion or iteration often shows up as well. Interviewers reuse these patterns because they reliably reveal problem-solving ability. Recognizing the pattern helps you choose the right approach quickly. This slide reinforces that preparation should focus on mastering patterns, not memorizing solutions. When you recognize the structure of a problem, you can reason confidently and adapt. Python interviews rely heavily on a small set of core data structures. Lists, dictionaries, and sets appear constantly. Knowing when to use each is critical. Stacks and queues often show up implicitly, even if not named directly. Basic familiarity with heaps can be useful, but deep implementation knowledge is rarely required. Interviewers care less about obscure structures. and more about whether you choose appropriate ones. This slide emphasizes mastery over breadth. Strong candidates use simple structures effectively, rather than forcing complex ones unnecessarily. Interviewers want readable idiomatic Python. Clear variable names, straightforward control flow, and simple logic are preferred. Over-optimization or overly compact code can hurt clarity. Explain what you're doing as you write code. This helps interviewers follow your thinking and builds confidence in your approach. Avoid clever shortcuts unless they genuinely improve clarity. Python interviews reward maintainable code, not clever one-liners. This slide reinforces that your goal is not to impress. It's to be understood and trusted as someone who writes reliable code. Many candidates fail interviews due to small but critical mistakes. Off by one errors, incorrect loop boundaries, and missed edge cases are common. Mutable default arguments in function definitions are a classic Python trap. Incorrect indentation can subtly break logic. Overcomplicating a solution often introduces bugs and confusion. This slide emphasizes awareness. Knowing these pitfalls helps you slow down, check assumptions, and catch mistakes early. Interviewers care more about how you recover from errors than whether you make them. You don't need perfect big O analysis, but you need reasonable awareness. Interviewers expect you to explain time and space complexity in plain language. Compare approaches and explain trade-offs when relevant. Know when optimization matters and when it doesn't. Python has performance quirks, but interviewers usually accept reasonable solutions. This slide reinforces that complexity analysis is about judgment, not memorization. Demonstrating that you can reason about performance builds confidence in your engineering maturity. How you communicate during coding matters a lot. Clarify assumptions before writing code. Walk through examples to validate understanding. Narrate decisions so interviewers know why you chose an approach. Ask before optimizing or changing direction. If you make a mistake, acknowledge it calmly and correct it. Interviewers view coding interviews as collaborative problem-solving sessions. This slide emphasizes that clear communication can often compensate for small technical mistakes. Python interviews are judged holistically. Correctness matters, but clarity, consistency, and composure matter just as much. Interviewers look for candidates who can recover from mistakes and maintain a collaborative mindset. Strong candidates demonstrate reliable thinking across multiple questions, not brilliance on one. This slide reinforces that Python interviews are predictable when approached correctly. Focus on fundamentals, communicate clearly, and treat the interviewer as a teammate, not an adversary. Machine learning theory interviews are not about memorizing formulas or reciting textbook definitions. Interviewers are trying to answer a much simpler question. Do you actually understand how models behave in the real world? They want to see whether you can reason about trade-offs, explain concepts clearly, and connect theory to practical decisions. In this lecture, we'll break down the most common ML theory questions you'll encounter, what interviewers are really listening for, and how to answer confidently without over-theorizing. If you approach theory interviews correctly, they become conversations about judgment, not exams. In this lecture, we'll focus on machine learning theory questions commonly asked in interviews. We'll explain why theory is tested, how interviewers evaluate understanding, and which topics appear most frequently. You'll also learn how to answer theory questions in a way that demonstrates depth without unnecessary complexity. By the end of this lecture, you should be able to explain core ML concepts clearly, connect them to real-world behavior, and avoid the common mistakes that cause candidates to sound either unprepared or overly academic. ML theory interviews measure understanding, not memorization. Interviewers want to see if you grasp the intuition behind concepts and can explain trade-offs. They care about whether you understand when a method works, why it fails, and how you would respond. Being able to connect theory to practical decisions, like model selection or evaluation, is critical. Clear communication matters just as much as correctness. This slide reinforces that theory questions are about reasoning. If you can teach a concept simply, you likely understand it well enough for real-world work. Certain ML concepts appear repeatedly in interviews. Bias variance trade-off, overfitting versus underfitting, and train validation test splits are foundational. Interviewers expect you to explain what these concepts mean and how they affect model performance. Feature importance and generalization are also common topics. You may be asked how to detect overfitting or improve generalization. This slide emphasizes that these concepts are not trivia. They form the backbone of decision-making in ML systems, which is why interviewers revisit them so often. Supervised learning theory questions focus on understanding models and their behavior. Interviewers may ask about differences between linear and nonlinear models, loss functions, and optimization. Regularization, especially L1 versus L2, is a frequent topic. Evaluation metrics are also critical. You should understand when accuracy is misleading and when metrics like precision or recall matter more. This slide highlights that interviewers want to know whether you can choose the right model and metric for a given problem, and explain why. Unsupervised learning questions test intuition rather than formulas. Interviewers often ask about clustering assumptions, such as those behind k-means. Distance metrics and the curse of dimensionality come up frequently. PCA is another common topic, especially understanding what it does intuitively rather than mathematically. This slide reinforces that unsupervised learning theory is about understanding structure in data and knowing when these techniques are appropriate or inappropriate in practice. Model evaluation is a core theory topic. Interviewers want to know how you validate models, avoid data leakage, and choose appropriate metrics. Cross-validation is frequently discussed, but understanding why it's used matters more than knowing the mechanics. Class imbalance is another common pitfall. You should be able to explain how it affects metrics and model behavior. This slide emphasizes that trusting a model requires thoughtful evaluation. Interviewers look for candidates who treat metrics as tools, not absolute truths. Many candidates fail theory interviews by overcomplicating answers. Reciting definitions without intuition sounds shallow. Ignoring assumptions makes explanations incomplete. Overly mathematical answers can confuse rather than clarify. Another common mistake is failing to connect theory to real-world decisions. Interviewers want examples, not abstract proofs. This slide helps you recognize and avoid these pitfalls. Strong answers balance intuition, simplicity, and relevance to practical problems. Strong theory answers follow a clear pattern. Start with intuition. Use a simple example to ground the concept. Mention trade-offs and limitations. Then connect the idea to practical decisions. Avoid going deeper than necessary. Stop once you've made the point clearly. Let the interviewer guide further depth. This slide emphasizes that good answers feel conversational, not rehearsed. The goal is to demonstrate understanding, not to prove how much you know. Interviewers evaluate ML theory holistically. They value understanding over formulas, clarity over complexity, and confidence without arrogance. Being able to teach a concept clearly is a strong signal of mastery. Strong candidates adapt explanations to the interviewer's level and context. They treat theory as a tool for decision-making, not an academic exercise. This slide reinforces that ML theory interviews reward reasoning and communication. When approached correctly, they become an opportunity to demonstrate judgment rather than memorization. Deep learning and transformer interviews are where many candidates either shine or fall apart. The challenge isn't knowing the buzzwords. It's showing that you actually understand how these models behave, where they fail, and how engineers work with them in practice. Interviewers aren't looking for someone who can recite architecture diagrams from memory. They're looking for intuition, reasoning, and judgment. In this lecture, we'll break down the most common deep learning and transformer interview questions, what interviewers are really listening for, and how to answer in a way that sounds confident, grounded, and practical, rather than rehearsed or superficial. In this lecture, we'll focus on deep learning and transformer interviews. We'll explain why these topics are often tested separately from general ML theory, and what interviewers are actually evaluating when they ask these questions. You'll see common deep learning and transformer question themes and learn how to avoid answers that sound shallow or memorized. By the end of this lecture, you should feel comfortable explaining deep learning concepts clearly, reasoning about transformer behavior, and discussing real-world trade-offs with confidence. Deep learning interviews measure depth of understanding. Interviewers want to know if you understand how models behave, not just how they're built. They're listening for intuition about training dynamics, failure modes, and trade-offs. Can you explain why something works? Can you reason about what happens when it doesn't? Can you connect theory to practice? This slide emphasizes that these interviews reward thinking over memorization. Candidates who demonstrate calm, clear reasoning consistently outperform those who rely on jargon or rote explanations. Interviewers frequently ask about foundational deep learning concepts. You should understand how neural network architectures work at a high level, how activation functions affect learning, and why loss functions matter. Backpropagation is often discussed intuitively rather than mathematically. Optimization challenges, such as convergence and stability, are also common topics. Interviewers want to see whether you understand how these elements interact. This slide reinforces that mastery of fundamentals allows you to reason about more complex systems later, including transformers and large language models. Training dynamics are a major focus in interviews. You may be asked about gradient descent variance, learning rate selection, and why training can become unstable. Vanishing and exploding gradients are classic discussion points. Overfitting in deep networks and the role of regularization often come up. Interviewers care about how you would diagnose and fix training issues. This slide emphasizes that training questions are about judgment. Knowing how to respond when models don't behave as expected is more valuable than knowing idealized training setups. Transformers are tested because they underpin modern AI systems. Interviewers expect you to understand why attention replaced recurrence, how self-attention works intuitively, and why multi-head attention exists. Positional encoding is often discussed conceptually rather than mathematically. You should also understand the roles of encoders and decoders and how they differ across tasks. This slide reinforces that transformers are evaluated as systems. Interviewers care about how they scale, why they work, and what problems they solve, not just their components. LLM behavior is a critical interview topic. Interviewers may ask about pre-training versus fine-tuning, how tokenization affects outputs, and why context windows matter. Hallucinations and failure modes are especially important to understand. You should also be able to discuss inference time trade-offs like latency, cost, and temperature settings. This slide emphasizes that understanding LLM behavior separates users from engineers. Interviewers want candidates who can reason about model behavior in real deployments. Many candidates struggle by focusing on the wrong things. Reciting architecture diagrams without explanation sounds superficial. Overusing jargon without intuition raises red flags. Ignoring limitations makes answers feel incomplete. Treating models as black boxes suggests lack of understanding. Interviewers want candidates who can reason, not just describe. This slide helps you recognize these pitfalls so you can avoid them. Strong answers are simple, grounded, and thoughtful, not overloaded with technical vocabulary. Effective answers follow a consistent structure. Start with intuition. Use a simple analogy if helpful. Explain key trade-offs and limitations. Then, connect the concept to real-world behavior or decisions. Avoid going deeper than necessary unless prompted. Let the interviewer guide the level of detail. This slide emphasizes that great answers feel natural and conversational. They demonstrate understanding without trying to impress. When you explain clearly, interviewers gain confidence in your ability to work with complex systems. Deep learning and transformer answers are judged holistically. Interviewers look for understanding, clarity, and the ability to debug or reason through unexpected behavior. Confidence matters, but humility matters too. Candidates who can teach concepts clearly stand out. Those who admit uncertainty and reason through it often perform better than those who pretend to know everything. This slide reinforces that interviews reward thoughtful engineers. When you approach deep learning discussions as problem-solving conversations, you turn a difficult topic into a strong advantage. System design interviews are where AI engineers are evaluated as engineers, not just model builders. Interviewers want to see whether you can think beyond notebooks and reason about real systems operating under real constraints. AI system design adds layers of complexity that traditional software design doesn't. Non-deterministic behavior, data drift, evaluation challenges, and ongoing model lifecycle management. In this lecture, we'll break down how AI system design interviews are structured, what interviewers are actually evaluating, and how to communicate your thinking clearly. The goal is not to design a perfect system, but to demonstrate structured reasoning, trade-off awareness, and production readiness. In this lecture, we'll focus on system design interviews for AI engineers. We'll explain why system design is such a critical part of AI hiring and how AI system design differs from traditional software system design. You'll learn what interviewers evaluate, how to structure your answers, and how to avoid common mistakes. By the end of this lecture, you should be able to walk through an AI system design problem confidently. Explain your assumptions clearly and adapt your design when interviewers introduce new constraints. AI system design interviews measure how you think at scale. Interviewers want to see end-to-end reasoning, from data ingestion to user experience. They evaluate whether you understand trade-offs, can reason under constraints, and communicate clearly. Production readiness is key. Can you anticipate failure modes? Can you design systems that can be monitored, evaluated, and improved over time? This slide reinforces that system design interviews are not about drawing the biggest diagram. They are about demonstrating judgment, structure, and the ability to reason through complexity calmly. AI systems introduce challenges that traditional software systems don't. Their behavior is non-deterministic, meaning the same input doesn't always produce the same output. They depend heavily on data quality and distribution, which can change over time. Models have life cycles, training, deployment, monitoring, retraining that must be managed explicitly. Evaluation is probabilistic, not binary. This slide emphasizes that interviewers expect you to acknowledge these differences. Treating AI systems like deterministic software systems is a common red flag in design interviews. Strong system design starts with a clear, high-level architecture. Interviewers want to see that you can identify core components, data ingestion and storage, feature or embedding pipelines, inference layers, APIs, and monitoring systems. You don't need every detail, but you do need a coherent flow. How does data move through the system? Where are decisions made? Where are failures observed? This slide reinforces that structure matters more than completeness. A clean, logical architecture builds confidence quickly. Operational constraints are central to AI system design. Interviewers expect you to reason about throughput, latency budgets, and cost. Trade-offs should be explicit. Faster responses may cost more, and cheaper systems may sacrifice quality. Caching, batching, and scaling strategies should be discussed at a high level. Horizontal versus vertical scaling decisions matter. This slide reinforces that strong candidates don't optimize blindly. They tie design decisions back to user experience and business requirements. Interviewers care deeply about what happens when things go wrong. AI systems can fail due to model errors, hallucinations, data drift, or infrastructure issues. Strong designs include fallback mechanisms and graceful degradation. You should explain how the system behaves under partial failure. Does it return cached results? Does it escalate to humans? Does it degrade functionality? This slide emphasizes maturity. Acknowledging failure modes and designing for them signals real production experience. Evaluation doesn't stop at deployment. Interviewers want to know how you measure quality offline and monitor performance online. Drift detection, alerting, and human-in-the-loop reviews are common discussion points. You should explain which metrics matter and why. Not everything needs to be monitored, but critical signals must be visible. This slide reinforces that AI systems are living systems. Monitoring and evaluation are ongoing responsibilities, not afterthoughts. Evaluation doesn't stop at deployment. Interviewers want to know how you measure quality offline and monitor performance online. Drift detection, alerting, and human-in-the-loop reviews are common discussion points. You should explain which metrics matter and why. Not everything needs to be monitored, but critical signals must be visible. This slide reinforces that AI systems are living systems. Monitoring and evaluation are ongoing responsibilities, not afterthoughts. System design answers are judged holistically. Interviewers value clear structure over exhaustive detail. Explicit assumptions help guide discussion. Thoughtful trade-offs matter more than perfect solutions. They will challenge your design to see how you adapt. The ability to adjust calmly and explain reasoning is a strong signal. This slide reinforces that system design interviews are conversations. When you focus on clarity, judgment, and practicality, you demonstrate readiness for real-world AI engineering roles. Take-home assignments can feel intimidating, frustrating, or even unfair, but they're one of the most revealing parts of the hiring process. Companies use them to see how you work when no one is watching, how you scope problems, make decisions, write code, and communicate trade-offs. The goal of a take-home assignment is not to build the biggest or most impressive system. It's to demonstrate judgment. In this lecture, we'll break down how take-homes are evaluated, the mistakes that quietly disqualify strong candidates, and how to submit work that reviewers actually enjoy reading. Done right, take-homes can become one of your strongest advantages. In this lecture, we'll focus on how to approach take-home assignments strategically. We'll discuss why companies use take-homes, what they're actually measuring, and how candidates are evaluated. You'll learn common mistakes that cost offers and how to stand out without over-engineering or burning excessive time. By the end of this lecture, you should understand how to treat take-home assignments as structured communication exercises, not unpaid labor, and how to submit work that signals professionalism and strong engineering judgment. From the employer's perspective, take-home assignments simulate real work. They reduce interview bias, allow candidates to work at their own pace, and reveal how people think independently. Hiring teams can observe how you interpret ambiguous requirements, make trade-offs, and communicate decisions. Unlike live interviews, take-homes show how you work without pressure. They answer a key question: would this person be effective on our team without constant guidance? This slide emphasizes that take-homes are not about speed. They're about clarity, ownership, and judgment. Take-home assignments measure far more than correctness. Hiring teams evaluate how well you understand the problem, how you scope the solution, and how cleanly you structure your code. They look closely at communication, both in documentation and in comments. Decision-making matters. Why did you choose this approach? What trade-offs did you consider? How did you prioritize? This slide reinforces that take-homes are holistic evaluations. Strong submissions feel intentional and thoughtful, even if they don't implement every possible feature. Many candidates fail take-homes before they write a single line of code, misunderstanding the problem, ignoring constraints, or missing evaluation criteria are common issues. Before coding, you should clarify objectives, identify requirements, and understand how the assignment will be judged. If questions are allowed, ask them. This shows professionalism, not weakness. This slide emphasizes that careful reading and clarification save time and prevent wasted effort. A correct solution to the wrong problem is still a failure. Strong take-home submissions are well scoped. Define a clear baseline solution that meets core requirements. Prioritize correctness and clarity over additional features. Avoid unnecessary complexity. Time box your work. Hiring teams can usually tell when candidates overinvest. Explain what you chose not to implement and why. This slide reinforces that scoping is a signal of judgment. Engineers who know what not to build are often more valuable than those who build everything without direction. Your code should be easy to read and review. Clear structure, descriptive naming, and simple abstractions matter more than clever optimizations. Idiomatic Python is preferred. Dependencies should be minimal and justified. Reviewers often skim code. If they can understand intent quickly, you've succeeded. This slide emphasizes that take-home code is read like production code. The goal is not to impress. It's to be trustworthy and maintainable. Documentation is where strong candidates separate themselves. A clear README should explain what you built, how it works, and how to run it. Include architecture overviews, assumptions, trade-offs, and limitations. Explain your thinking. Reviewers want to understand why decisions were made. This slide reinforces that documentation is not extra. It's essential. Clear communication often outweighs additional features in hiring decisions. Many strong candidates fail due to avoidable mistakes. Overengineering is common. Adding features that weren't asked for. Ignoring instructions or missing requirements is another major issue. Poor documentation creates frustration for reviewers. Some candidates spend excessive time polishing instead of focusing on clarity. Others submit work without explaining decisions. This slide helps you avoid these traps. A clean, focused, well-explained submission almost always beats an overbuilt, confusing one. Take-home assignments are judged like real work. Hiring teams ask themselves, was this easy to review? Did this person show good judgment? Would we want to work with them? Clarity beats complexity. Thoughtfulness beats completeness. Communication matters as much as code. This slide reinforces that winning take-homes is about professionalism and trust. When your submission makes reviewers feel confident, you dramatically increase your chances of moving forward. Mock interviews are one of the highest leverage tools in interview preparation and one of the most underused. Many candidates prepare in isolation, only realizing their weaknesses when it's too late. Mock interviews expose those gaps early. They simulate real interview conditions, pressure, time limits, and the need to explain your thinking clearly. More importantly, they turn preparation into performance. In this lecture, we'll break down how to run effective mock interviews for both technical and behavioral rounds, what interviewers are actually evaluating during these sessions, and how to turn feedback into measurable improvement. Done right, mock interviews transform interviews from stressful events into familiar conversations. In this lecture, we'll explore how to use mock interviews effectively. We'll explain why mock interviews matter, what they reveal about your readiness, and how to practice in a way that actually improves performance. You'll learn how to simulate both technical and behavioral rounds and how to extract useful feedback from each session. By the end of this lecture, you should understand how to treat mock interviews as structured training, not casual practice, and how to use them to build confidence and consistency before real interviews. Mock interviews work because they recreate real conditions. They introduce time pressure, force you to think out loud, and expose gaps in explanation that don't appear during solo study. They also reveal habits, such as rushing, over-explaining, or freezing, that only show up under pressure. This practice builds familiarity. The more often you experience interview-like situations, the less intimidating real interviews feel. This slide emphasizes that mock interviews are about stress inoculation. Confidence comes from repetition, not just preparation. Technical mock interviews should mirror real interview rounds. These include coding problems, ML or DL theory questions, system design discussions, and walkthroughs of take-home assignments. You should practice reasoning aloud and explaining decisions clearly. Mock technical interviews help you identify weak explanations, unclear assumptions, and gaps in fundamentals. They also help you practice pacing, knowing when to pause, clarify, or move forward. This slide reinforces that technical skill alone isn't enough. Communication and structure are equally important during technical interviews. In technical interviews, interviewers evaluate more than correctness. They look for structured problem solving, clear reasoning, and thoughtful trade-off discussion. How you handle mistakes matters as much as whether you make them. Recovery is a strong signal. Candidates who notice errors, explain them, and adjust calmly often perform better than those who panic. This slide emphasizes that technical interviews are collaborative. Interviewers want to see how you think, not just whether you arrive at the correct answer. Behavioral mock interviews are just as important as technical ones. They simulate questions about past experiences, conflict, failure, collaboration, and decision-making. These interviews assess how you work with others and how you reflect on your experiences. Mock behavioral interviews help you refine stories, eliminate rambling, and ensure your examples clearly demonstrate ownership and learning. This slide reinforces that behavioral interviews are not about saying the right thing. They're about telling honest, structured stories that reflect maturity. Behavioral interviews evaluate self-awareness and professionalism. Interviewers listen for accountability, communication clarity, and a learning mindset. They pay attention to how you describe failures and conflicts. Blaming others or avoiding responsibility is a red flag. Reflective, balanced answers build trust. This slide emphasizes that behavioral interviews are about judgment and values. Strong candidates show they can work well within teams, handle feedback, and grow from experience. Not all mock interviews are equally effective. Use realistic questions and time box each round. Practice aloud, not silently. Treat the session like a real interview. No stopping to retry. Recording sessions can be extremely valuable. Watching yourself later reveals habits you might not notice in the moment. Rotate interviewers when possible to expose yourself to different styles and perspectives. This slide emphasizes intentional practice. The goal is not comfort, it's growth through realistic simulation. Feedback is where improvement happens. After each mock interview, capture specific feedback. Look for patterns, recurring weaknesses, unclear explanations, or common mistakes. Refine your answers and practice weak areas deliberately. Track progress over time rather than judging a single session. This slide reinforces that improvement is iterative. Small adjustments made consistently lead to major gains in interview performance. Mock interviews turn preparation into performance. They reduce cognitive load, build consistency, and help you stay calm under pressure. Over time, interviews start to feel familiar rather than threatening. Strong candidates don't just prepare, they rehearse. They know their stories, explanations, and problem-solving patterns. This slide reinforces that interview success is rarely about brilliance in the moment. It's about being practiced, prepared, and confident when it matters most. Most resumes don't fail because the candidate isn't qualified. They fail because the resume never reaches a human. Applicant tracking systems, or ATS, act as the first and often most ruthless filter in the hiring process. In this lecture, we'll demystify how ATS systems actually work and how AI engineer resumes get screened before a recruiter ever sees them. The goal is not to game the system, but to design resumes that communicate clearly to both machines and humans. When your resume passes ATS cleanly, recruiters can focus on your skills instead of struggling to interpret your experience. In this lecture, we'll focus on building an AI engineer resume that passes ATS filters. We'll explore why resumes fail before human review, how ATS systems parse and rank candidates, and the most common mistakes that silently eliminate strong applicants. You'll also learn how to structure your resume so it sends clear signals to both automated systems and recruiters. By the end of this lecture, you should understand how to design a resume that survives ATS screening and presents your experience clearly and credibly to hiring teams. ATS systems don't hire people, they filter resumes. Their primary function is keyword matching and scoring based on job descriptions. They parse resumes to extract titles, skills, and experience, then rank candidates accordingly. ATS systems are imperfect. Complex formatting, tables, or unusual layouts can break parsing. If key information isn't extracted correctly, your resume may be ranked lower or ignored entirely. This slide emphasizes that ATS is a gatekeeper. If your resume can't be parsed cleanly, your qualifications may never be evaluated by a human, no matter how strong they are. Your resume must work for three audiences. ATS systems look for keywords and structure. Recruiters look for clarity, relevance, and fit. Hiring managers look for depth, impact, and problem-solving ability. A resume optimized only for ATS may look robotic. A resume optimized only for humans may never pass the filter. This slide reinforces the need for balance. Strong resumes use ATS-friendly structure, while still telling a clear, compelling story for human readers. Designing for all three audiences dramatically increases your chances of moving forward. But structure matters more than most candidates realize. ATS systems work best with simple, single-column resumes, using standard headings like experience, skills, and education. Chronological ordering helps both machines and humans follow your career progression. Avoid tables, graphics, columns, icons, or decorative elements. These often confuse parsers and hide content. This slide emphasizes that readability is not boring, it's strategic. A clean layout ensures your experience is extracted correctly and makes your resume easy for recruiters to scan quickly. Keywords are how ATS systems understand relevance. Strong resumes mirror the language used in job descriptions, especially role titles, core skills, and domain-specific terms. Keywords should appear naturally in experience bullets, not just in the skills section. Avoid keyword stuffing. ATS systems and recruiters can detect unnatural repetition. Focus on skills you've actually used and can explain. This slide reinforces that keyword optimization is about alignment, not manipulation. When your resume speaks the same language as the role, it becomes easier to match and rank. Experience bullets are where resumes succeed or fail. Strong bullets start with action verbs and describe what you built or delivered. They include context, what problem you are solving, and end with outcomes whenever possible. Metrics help, but clarity matters more than perfect numbers. Mention tools only when they're relevant to the impact you're describing. This slide emphasizes that recruiters look for evidence of contribution, not task lists. Well-written bullets turn experience into proof of capability. The skills section should reinforce, not replace, your experience. Group skills by category, such as programming languages, NL techniques, or tools. List only skills you can explain confidently in an interview. Avoid long, unstructured lists. They create noise and weaken signal. Prioritize skills that align with your target role. This slide reinforces that skills are supporting evidence. The strongest resumes show skills in action within experience bullets, with the skills section acting as a concise summary. Many resumes fail due to avoidable mistakes. Complex PDFs with graphics or columns often break ATS parsing. Missing role-specific keywords reduces ranking. Generic job titles make experience harder to interpret. Dense paragraphs slow down human reviewers. Inconsistent terminology confuses both ATS systems and recruiters. This slide helps you identify and remove hidden blockers. Fixing formatting and language issues alone can significantly improve your resume's performance. Before submitting your resume, do a final check. Ensure your resume mirrors the job description's language where appropriate. Confirm the format is ATS-friendly and easy to skim. Verify that your target role is clear and your bullets focus on outcomes. Ask yourself, can a recruiter understand my value in 30 seconds? If the answer is yes, your resume is doing its job. This slide reinforces that resume success is about clarity and alignment, not cleverness. Resumes don't fail because candidates lack experience. They fail because the experience isn't communicated clearly. Bullet points are the smallest unit of meaning on a resume, and they carry an outsized amount of weight. Recruiters skim them quickly to decide whether someone is worth a deeper look. In this lecture, we'll focus on how to write bullet points that communicate impact, not just activity. You'll learn why most bullets fail, how recruiters actually read them, and a simple structure you can use to turn everyday work into strong evidence of value. When your bullets are clear and outcome-focused, your resume becomes much harder to ignore. In this lecture, we'll focus on writing impact-driven bullet points. We'll break down why most resume bullets fail, what recruiters are actually looking for, and how to turn your work into clear hiring signals. You'll learn a simple, repeatable structure for writing bullets that communicate value quickly. By the end of this lecture, you should be able to rewrite existing bullets so they highlight impact, decision-making, and relevance, making your resume easier to skim and far more compelling to both ATS systems and human reviewers. For most reviewers, bullet points are the resume. Recruiters skim quickly, often spending only a few seconds per role. Bullet points determine whether they continue reading or move on. Weak bullets hide strong experience, while strong bullets make average experience look impressive. Good bullets reduce guesswork. They answer key questions immediately. What did this person do? Why did it matter? What changed because of their work? This slide emphasizes that bullet points are not a formality. They are the primary mechanism through which your experience is evaluated. Many bullets fail because they describe activity instead of impact. Phrases like responsible for or long lists of tools don't communicate value. Vague verbs and missing outcomes force recruiters to guess why the work mattered. Internal jargon can also be a problem. If only people from your team understand a bullet, it won't land with recruiters. This slide helps you identify patterns that weaken bullets. Avoiding these mistakes is often the fastest way to improve a resume without adding new experience. Strong bullets follow a simple structure. Start with an action verb. Describe what you built or changed. Provide brief context about the problem. Then explain the outcome or result. Metrics are helpful when available, but not required. This structure keeps bullets focused and readable. It guides the reviewer through your contribution without unnecessary detail. This slide reinforces that bullet writing is a skill. When you consistently apply a clear formula, your resume becomes more coherent and much easier to evaluate. Action verbs set the tone for each bullet. Verbs like built, designed, implemented, or deployed signal ownership. Words like optimized, reduced, or improved highlight impact. Leadership verbs show collaboration and responsibility. Avoid passive language that downplays your role. Strong verbs help recruiters quickly understand your contribution. This slide emphasizes intentionality. The verb you choose influences how your experience is perceived before the rest of the bullet is even read. Metrics strengthen bullets, but they must be honest. Quantification can include performance improvements, cost or time reduction, reliability gains, or scale. Exact numbers are helpful, but directional metrics are acceptable when precision isn't available. Avoid exaggeration. Recruiters and interviewers often probe metrics later. Credibility matters more than impressive figures. This slide reinforces that metrics are supporting evidence, not the headline. Clear outcomes paired with reasonable numbers build trust and make your impact tangible. More senior bullets reflect judgment, not just execution. They hint at constraints, trade-offs, and decisions. You might reference scalability limits, cost considerations, or why a particular approach was chosen. You don't need long explanations. Small signals are enough. Showing awareness of production concerns elevates bullets significantly. This slide emphasizes that impact is not only about results, it's also about how thoughtfully those results were achieved under real-world constraints. Seeing transformations makes the difference clear. Weak bullets often describe tasks. Strong bullets describe outcomes. They shift focus from tools to decisions, from internal activity to external impact. This slide encourages you to rewrite bullets systematically. Ask, what changed because of my work? Who benefited? How would an outsider understand this? Turning noise into signal is the goal. Even small rewrites can dramatically improve how your experience is perceived. Before finalizing your resume, review each bullet carefully. Does it have a clear action and outcome? Is its relevance to the role obvious? Can it be skimmed quickly? Are there unnecessary words or vague phrases? Most importantly, ask, why does this matter? If the answer isn't clear, revise. This slide reinforces that strong resumes are built bullet by bullet. When each one carries impact, the whole resume becomes far more effective. For many AI engineers, LinkedIn feels optional, or worse, uncomfortable. But in reality, LinkedIn is one of the most powerful tools in the hiring process. Recruiters use it to validate resumes, search for candidates, and decide who to contact. Personal branding doesn't mean becoming an influencer or posting constantly. It means communicating clearly who you are professionally, what you work on, and where you're headed. In this lecture, we'll break down how recruiters actually use LinkedIn, how to position yourself authentically, and how to turn your profile into a passive job pipeline without sacrificing credibility or professionalism. In this lecture, we'll explore how AI engineers can use LinkedIn strategically. We'll explain why LinkedIn matters beyond resumes, how recruiters evaluate profiles, and what personal branding really means in a professional context. You'll learn how to position yourself clearly and avoid common mistakes that weaken credibility. By the end of this lecture, you should understand how to turn your LinkedIn profile into a supporting asset that reinforces your resume and attracts relevant opportunities, without feeling like self-promotion. Recruiters use LinkedIn as a validation and discovery tool. After reviewing a resume, they often check LinkedIn to confirm role titles, timelines, and experience. They also use keyword searches to find candidates proactively, especially for niche AI roles. LinkedIn helps recruiters assess whether a candidate is actively engaged in their field and aligned with the role. Profiles that are incomplete or inconsistent raise doubts. This slide emphasizes that LinkedIn is not optional. It's part of how recruiters build confidence before reaching out or deciding not to. Personal branding is often misunderstood. It's not about posting every day, chasing likes, or becoming an influencer. It's about clarity and consistency in how you present yourself professionally. A strong personal brand communicates what you work on, what you're good at, and what direction you're moving in. It's supported by evidence, projects, experience, and thoughtful engagement. This slide reinforces that personal branding is about trust. When your profile tells a coherent story, recruiters and hiring managers feel more confident reaching out. Your headline is the most important line on your LinkedIn profile. It's what recruiters see first and what LinkedIn's search algorithm prioritizes. A strong headline is role-focused, specific, and free of vague buzzwords. Include your current or target role, your domain or system focus, and one or two core strengths. Avoid generic phrases like AI enthusiast or passionate engineer. This slide emphasizes that a clear headline increases discoverability and sets expectations immediately. Ambiguity reduces inbound opportunities. The About section is your professional summary. Use it to explain who you are as an engineer, what problems you solve, and the kinds of systems you build. Mention domains or industries where relevant. This is not a biography, it's a positioning statement. Be clear about your career direction and interests. This slide reinforces that recruiters read this section to understand fit. When written well, it answers key questions before a conversation even starts. Your experience section should reinforce your resume. Use impact-driven bullets that focus on outcomes, not tool lists. Ensure consistency with your resume. Discrepancies raise red flags. Highlight scope and ownership clearly. Avoid internal jargon and vague descriptions. This slide emphasizes that LinkedIn experience is not filler. It's proof. When recruiters see clear, outcome-focused experience, they're more likely to reach out with relevant roles. Posting on LinkedIn is optional, but strategic engagement helps. Sharing project learnings, trade-offs, or lessons shows expertise without self-promotion. Commenting thoughtfully on others' posts can be just as powerful as posting. Consistency matters more than frequency. One high-quality post per month is better than daily noise. This slide reinforces that content is about signal, not visibility. Thoughtful engagement builds credibility over time and keeps you top of mind for recruiters. Networking on LinkedIn should be intentional. Send targeted connection requests with thoughtful messages. Engage with people's content before asking for anything. Follow hiring managers and teams you're interested in. Relationships compound over time. Not every connection leads to a job immediately, but many do eventually. This slide emphasizes patience and professionalism. Strong networks are built through genuine interest, not transactional outreach. LinkedIn plays a quiet but powerful role in hiring. It reinforces your resume, reduces uncertainty, and makes outreach warmer. A strong profile signals professionalism and direction. Recruiters often decide who to contact based on how confident they feel after reviewing a profile. When LinkedIn aligns with your resume and portfolio, it amplifies your chances. This slide reinforces that LinkedIn is a credibility layer. When done well, it works for you in the background, bringing opportunities to you rather than forcing you to chase them. Networking has a bad reputation, especially among engineers. It often feels awkward, forced, or inauthentic. But the truth is, networking is simply how trust is built in professional communities. In AI hiring, networking matters because many roles are filled through referrals or warm introductions long before they're posted publicly. This lecture focuses on practical, low-pressure networking strategies that actually work, without cold pitching, mass messaging, or pretending to be someone you're not. We'll break down who to connect with, how to start conversations naturally, and how to turn short interactions into long-term professional relationships that lead to opportunities. In this lecture, we'll talk about networking strategies that work in real hiring scenarios. We'll cover why networking matters in AI roles, common myths that discourage engineers, and what effective networking actually looks like in practice. You'll learn how to build momentum without awkwardness, and how to approach networking as relationship building, not job begging. By the end of this lecture, you should feel more comfortable using networking as a tool that supports your job search and long-term career growth. Networking works because hiring is fundamentally about trust. Many AI roles are filled before they're ever posted publicly. Referrals help hiring teams reduce risk by relying on trusted signals. Engineers are more likely to hire people recommended by other engineers. Networking amplifies your signal. It provides context beyond a resume and helps teams understand where you might fit before an interview even begins. This slide emphasizes that networking doesn't replace skill. It helps your skills get seen. When done well, it shortens hiring cycles and improves role alignment. Networking is often misunderstood. It's not cold pitching strangers for jobs or sending mass messages. It's not asking for favors before building rapport. And it's definitely not transactional. Effective networking is about building professional relationships over time. It starts with curiosity, shared interests, and mutual respect. This slide helps reframe networking as something engineers already do, collaborating, learning, and sharing knowledge, just extended beyond your immediate team. Not all connections are equally valuable. High-impact networking focuses on people who understand the roles you're targeting: engineers in similar positions, hiring managers, tech leads, and domain-specific recruiters. Open-source maintainers are also valuable connections. These individuals can provide insight, context, and referrals, often organically. This slide emphasizes intentionality. Effective networking is targeted, not broad. Connecting with the right people makes your efforts more meaningful and less exhausting. Networking doesn't only happen at formal events. LinkedIn comments, open source communities, conferences, meetups, and alumni networks are all powerful channels. Often, the best networking happens through ongoing interaction rather than one-off messages. Internal referrals and past colleagues are especially valuable. They already know how you work. This slide reinforces that networking is about presence and engagement. Being consistently visible in the right spaces matters more than attending every event. Starting conversations doesn't have to be awkward. Comment on someone's recent work. Ask a thoughtful question. Reference a shared interest or experience. Keep messages short and specific. Avoid asking for a job or referral up front. Focus on learning and connection first. This slide emphasizes low-pressure openers. When you lead with curiosity rather than need, conversations feel natural and people are more willing to engage. Relationships are built through follow-up. Thank people for their time. Share useful resources. Provide updates occasionally without spamming. Be genuinely helpful when opportunities arise. Consistency matters more than intensity. A few thoughtful interactions over time build stronger relationships than one long conversation. This slide reinforces that networking is a long game. Trust compounds through repeated positive interactions. Many networking efforts fail due to avoidable mistakes. Asking for referrals too soon puts people in uncomfortable positions. Copy-paste messages feel impersonal. Over-explaining your background can overwhelm readers. Disappearing after one interaction breaks momentum. Treating people like leads instead of peers damages trust. This slide helps you recognize behaviors that quietly undermine networking. Avoiding these mistakes makes your outreach feel professional and respectful. Networking improves interviews before they begin. Warm introductions provide context, reduce uncertainty, and improve role alignment. Hiring teams often approach referred candidates with more openness. Over time, networking creates long-term career leverage, not just immediate opportunities. This slide reinforces that networking isn't about shortcuts. It's about building a professional reputation that works for you across roles, companies, and years. Many candidates believe that job searching is a numbers game. Apply to hundreds of roles and hope something sticks. In reality, that approach often leads to burnout, frustration, and silence. The problem isn't effort, it's strategy. Hiring pipelines reward clarity, relevance, and context. When you apply strategically, you increase signal instead of noise. In this lecture, we'll break down why mass applying fails, how hiring pipelines actually work, and how to apply in a way that consistently leads to interviews. The goal is not to apply more, It's to apply smarter and regain control of the process. In this lecture, we'll focus on how to apply strategically rather than at scale. We'll explain why mass applications rarely work, what strategic applying actually looks like, and how hiring pipelines filter candidates. You'll learn how to turn effort into interviews by improving relevance and context. By the end of this lecture, you should be able to design a focused application strategy that produces better results with fewer applications, saving time, energy, and motivation. Mass applying fails because it creates low signal. Applicant tracking systems filter aggressively, and generic resumes blend together. Recruiters reviewing hundreds of applications experience fatigue, making it harder for any single resume to stand out. Candidates often burn out without feedback, mistaking silence for personal failure rather than systemic inefficiency. This slide emphasizes that applying more doesn't increase visibility. It often decreases effectiveness. Strategic applying focuses on alignment and clarity, which improves conversion rates at every stage of the pipeline. Understanding the hiring pipeline changes how you apply. Applications move through multiple stages: ATS screening, recruiter shortlisting, hiring manager review, interviews, and finally an offer. Each stage filters for different signals. Most candidates are filtered out early due to misalignment or unclear resumes, not lack of ability. This slide reinforces that success depends on passing each stage. Strategic applying improves signal at the earliest steps, where most candidates are eliminated. Strategic applying means fewer, better applications. It involves targeting roles that match your skills, aligning your resume deliberately, and adding context wherever possible. Warm introductions and thoughtful outreach dramatically increase visibility. Follow-up matters, but it should be intentional, not spammy. This slide emphasizes that strategic applying treats job searching as a system. Each application is a deliberate bet, not a lottery ticket. Not every open role is worth applying to. Strong candidates evaluate role fit before applying. This includes skills alignment, system or domain relevance, seniority expectations, and team maturity. Applying to roles that don't match your profile lowers conversion rates and wastes energy. This slide reinforces that saying no to misaligned roles is a strength. Strategic applying prioritizes roles where your experience clearly fits the problem being solved. Customization doesn't mean rewriting your resume from scratch. High-leverage customization includes adjusting headlines, mirroring job description language, reordering bullets, and emphasizing the most relevant projects. Small, intentional changes improve alignment without consuming excessive time. This slide emphasizes efficiency. Strategic applying optimizes for impact per hour, not perfection. Applications perform better when supported by relationships. Applying after a conversation, mentioning internal referrals, or reaching out to hiring teams provides context that cold submissions lack. Timing matters. Applying shortly after engagement increases visibility and recall. This slide reinforces that networking and applying are not separate activities. Together, they create warmer, higher signal applications that convert more reliably. Treat applying like an experiment. Track applications, responses, and interview rates. Look for patterns. If you're not getting interviews, adjust targeting or resume signals. If interviews stall, refine preparation. Iteration turns rejection into data rather than discouragement. This slide emphasizes control. Strategic applicants learn from outcomes and continuously improve rather than repeating the same approach blindly. Strategic applying changes the entire interview experience. Higher interview rates reduce pressure. Better role alignment leads to stronger conversations. Fewer applications mean less burnout and more focus. Candidates who apply strategically feel more confident because they understand why they're a good fit. This slide reinforces that success comes from clarity and intent. When you apply strategically, you stop chasing opportunities and start choosing them. Salary negotiation is one of the most uncomfortable but most important parts of landing an AI role. Many candidates avoid it out of fear of losing the offer, fear of sounding greedy, or fear of saying the wrong thing. The reality is very different. Negotiation is expected. Companies build flexibility into offers, especially for in-demand AI roles. How you negotiate signals your seniority, confidence, and professionalism. In this lecture, we'll break down how AI compensation actually works, when and how to negotiate, and how to maximize long-term value, not just base salary. Done correctly, negotiation strengthens your position rather than hurting it. In this lecture, we'll focus on salary negotiation for AI roles. We'll address common fears and myths, explain how AI compensation packages are structured, and walk through how to negotiate confidently and professionally. You'll learn what to negotiate, when to do it, and how to avoid common mistakes that weaken your position. By the end of this lecture, you should feel prepared to approach negotiation as a normal, respectful conversation, one that helps you secure fair compensation and start your role with confidence. Negotiation is a standard part of hiring, especially for AI engineers. Companies expect counteroffers and often leave room in initial offers. Negotiating professionally signals experience and confidence, not greed. Declining to negotiate usually means leaving value on the table. Hiring teams rarely rescind offers because of reasonable negotiation. What matters is how you communicate. Clear, respectful, and data-driven. This slide emphasizes that negotiation is not risky when done correctly. It's a normal step in reaching a mutually beneficial agreement. AI compensation goes beyond base salary. Packages often include bonuses, equity or RSUs, signing bonuses, and benefits. Early-stage startups and large companies structure compensation very differently. Understanding how these components work and their trade-offs is critical. Equity may have upside, but also risk. Bonuses may be variable. Benefits and flexibility can significantly affect quality of life. This slide reinforces that smart negotiation looks at total compensation, not just the headline number. Preparation is your strongest leverage. Before negotiating, research compensation benchmarks for your role, seniority, and location. Understand how company stage affects pay. Consider how scarce your skills are in the market. Competing offers strengthen leverage, but they're not required. Even without them, data-driven ranges support reasonable asks. This slide emphasizes that confidence comes from information. When you know the market, negotiation becomes a discussion, not a gamble. Timing matters in negotiation. The right time to negotiate is after you receive a written offer, but before you accept. Avoid discussing compensation too early in interviews. First, establish mutual interest. When negotiating, express enthusiasm for the role. Separate excitement from compensation discussions, so neither undermines the other. This slide reinforces that patience is strategic. Waiting for the right moment increases leverage and keeps conversations positive. Strong counteroffers are professional and specific. Start by expressing appreciation for the offer. Anchor your request with market data or role expectations. Frame your ask as a question or discussion, not a demand. Be clear about what you're requesting and why. Leave room for dialogue. This slide emphasizes tone and clarity. Negotiation is not confrontation, it's collaboration. How you ask often matters more than what you ask for. Salary is only one negotiation lever. You can negotiate base pay, equity, signing bonuses, level or title, start dates, and flexibility. Sometimes companies can't move on base, but can adjust other components. Understanding which levers matter most to you helps guide discussions. This slide reinforces that negotiation is about finding value, not winning a single number. Flexible thinking often leads to better outcomes. Many candidates weaken their position through avoidable mistakes, negotiating too early, over-anchoring, issuing ultimatums without leverage, or using emotional language can hurt credibility. Accepting immediately under pressure also limits outcomes. Silence is not rejection. Often, it's internal discussion. This slide helps you recognize and avoid behaviors that create unnecessary risk. Calm, measured negotiation builds trust rather than tension. Negotiation affects how teams view you. Professional negotiation builds respect and signals maturity. Reasonable asks rarely hurt offers. Clear communication reassures hiring teams that you'll be thoughtful and fair as a colleague. Companies also think about long-term retention. Candidates who feel valued and fairly compensated are more likely to stay and perform well. This slide reinforces that negotiation is part of starting strong. Done well, it sets a positive tone for your entire role. Your first 90 days as an AI engineer matter more than most people realize. This is the period where teams form their initial perception of you, how you think, how you communicate, and how reliable you are. It's not about proving you're the smartest person in the room. It's about showing that you can learn quickly, collaborate well, and deliver steadily. In this lecture, we'll break down what strong performance actually looks like in the first 30, 60, and 90 days. You'll learn how to avoid common early mistakes, build trust with your team, and turn onboarding into momentum rather than confusion. A strong start sets the foundation for long-term growth. In this lecture, we'll focus on how to succeed in your first 90 days as an AI engineer. We'll discuss why this period is so important, what teams actually expect from new hires, and how to avoid common early missteps. You'll learn how to approach your first 3 months with intention, balancing learning, execution, and communication. By the end of this lecture, you should have a clear mental model for how to ramp up effectively. Build credibility with your manager and teammates, and position yourself for long-term success from day one. Teams don't expect perfection in your first 90 days, but they do expect progress. Success is measured by how quickly you ramp up, the quality of questions you ask, and how reliably you follow through. Clear communication matters more than raw output early on. Teams notice whether you take ownership and whether people can depend on you. This slide emphasizes that early success is about trust. When teammates feel confident in how you think and communicate, they're more willing to give you responsibility. That trust compounds over time. The first 30 days are about understanding before acting. Focus on learning the system architecture, data flows, models, and tools. Read existing code and documentation carefully. Observe how decisions are made and how teams collaborate. Meet stakeholders and teammates to understand context beyond the code. Ask thoughtful questions, but avoid jumping to conclusions. This slide reinforces patience. Strong early performance comes from building a mental map of the system before attempting to change it. Learning deeply now prevents costly mistakes later. Alongside learning, you should focus on setting up strong foundations. Get your development environment working smoothly. Understand deployment pipelines, monitoring dashboards, and evaluation metrics. Clarify expectations with your manager early. What does success look like in the first few months? Identify gaps in your knowledge and start closing them intentionally. This slide emphasizes preparation. Investing time in foundations early allows you to contribute more effectively later and reduces friction when real work begins. In days 31 to 60, you transition from observer to contributor. Start owning small but meaningful tasks. Fix bugs, improve reliability, or ship incremental features. Focus on writing clean, reviewable code and incorporating feedback. Communicate progress clearly and consistently. If you're blocked, say so early. This slide reinforces momentum. Consistent, visible progress, no matter how small, builds confidence in your abilities and signals that you're ready for greater responsibility. Trust is built through reliability and transparency. Deliver on what you commit to. If something slips, communicate early. Ask for feedback and act on it. Collaborate openly and support teammates when possible. Show learning velocity. Demonstrate that feedback leads to improvement. This slide emphasizes that trust is earned through behavior, not titles. Teams invest more in engineers they trust, accelerating your growth and influence. By day 61 to 90, you should start thinking beyond assigned tasks. Propose improvements to systems, workflows, or documentation. Identify recurring pain points and suggest thoughtful solutions. Optimize small parts of the system where you now have context. Leadership here doesn't mean authority, it means initiative. This slide reinforces that impact grows with understanding. When you combine context with initiative, you begin to shift from contributor to trusted problem solver. Many new hires struggle due to avoidable mistakes. Trying to prove brilliance too fast often backfires. Making changes without context creates risk. Staying silent when confused slows progress. Ignoring non-technical stakeholders limits effectiveness. Overpromising and under-delivering damages trust early. This slide helps you avoid these traps. Strong early performance is about humility, clarity, and consistency, not showing off technical depth prematurely. The first 90 days shape your long-term trajectory. They influence how managers perceive you, what opportunities you're given, and how quickly you grow. Early momentum compounds. Good impressions lead to more trust, autonomy, and impact. This slide reinforces that onboarding is not a waiting period. It's an opportunity to establish your reputation as a thoughtful, reliable engineer. When you start strong, you don't just land a job, you build the foundation for a lasting AI engineering career.